Alrighty folks, so right off the bat in this video, I'm just going to let you know, if you open this video in YouTube, if you're accessing from the Google Classroom, you might have to right click the link and then click open in new tab to make it open up in YouTube. Otherwise, you won't see the description, but if you do that, if you open it in YouTube, in the description below the video, I'm just going to put timestamps for each individual question. That way, if you're looking for help with a specific question, you can just kind of click on that one and it'll bring you straight to the part of the video where I start that question. Rather than trying to skip through the whole thing and find it. Probably the purpose of this video is more along that lines. I wouldn't really recommend just sitting here and watching the whole thing front to back. Also, if you're noticing the length of this video, don't panic. It's me going through and kind of really explaining what I'm doing for the most part. So don't think that's how long it's going to take you to write the diploma. It probably will be shorter than that because you're not going to be sitting there explaining each question. Okay, so just wanted to say that right off the bat. Okay, so starting out with number 1 here on the diploma, the point P38 is on the graph of y equals b to the power of x, where they're telling us our b value is greater than 1. Okay, that's always the case for an exponential function. If we want to work with it, that b needs to be, it doesn't need to be greater than 1, but it does need to be positive, and it can't be 0 or 1. Otherwise, we're just dealing with 0 to the power of something, which is always going to be 0, or 1 to the power of something, which is always going to be 1. So the fact that it's 1 tells us it's greater than 1 tells us this is an increasing exponential function. Don't know if that's super relevant to this question, but just a reminder of why they might tell us that. So the corresponding point P prime on the graph of y plus 3 equals b to the power of x plus 1. Okay, so just a transformations question here, right? Exponential, but really it's just asking us to think about what does changing the equation in this way mean that we did to this point on the graph of the original function? Where would we have moved it to? So, little reminder, right? This is the general form. If we want to transform any function, we take its original equation, f of x, we replace x with b times x minus h, and then we multiply that by a, and we add k. Okay, so we got our vertical stretch A, horizontal stretch would be 1 over B, remember. Horizontal translation would be H, vertical translation would be K. So if we were to take this and we were to think about it in the characteristic of an exponential function, what does that mean we're going to do? Well, we're going to replace x in the original function with bx. Okay, that's not the same b as this. Sorry, that's a little confusing, but b to the power of, it'll be b times x minus h, if we were going to transform this, right? And then we would multiply that by a, and we would add k. So this is just the general form of how to transform any function, turned into the general form of how to transform any exponential function, just applying these ideas to y equals b to the x, okay? So if we compare this now to what we've got here, we should always or at least I like to always rewrite it in a way where I can really see what the k's are or the b's are, for example, right? Basically make it actually look like this. So that's going to be pretty quick here, because if we have y plus 3 equals b to the x plus 1, that really means if I just subtract 3 from both sides to really isolate the y there, now it's a little more clear. We can see, aha. So our k is actually just negative 3, right? We do have a k value. It's negative 3. And no b, or b is 1. But we do have an h value. Be very careful. Remember, it's always x minus h, right? And so that means that our h is actually negative 1. Because in order to get this, we would have had to do x minus negative 1 to get an x plus 1. Right? And again, that just comes from the fact that x is not isolated in our equation. So really, whatever we're doing to x here, if we were to isolate x, we would see that it's having the opposite effect. We would undo that operation, right? To isolate x here, I would subtract 1 from both sides eventually. And that's why the x is actually being moved to the left. It's being reduced by 1. Anyway, so that tells us our h is 3. Whoa, no, sorry, I was looking at the wrong number. Our h is negative 1, okay? And therefore we have a horizontal translation 1 unit left, and here we have a vertical translation negative 3, so 3 units down. So essentially no stretches going on here. So all this means we're doing with every point is moving the x value 1 left, or subtracting 1 from the x value, you can think of it as, and moving the y value 3 down, or subtracting 3 from the y value. So if we think about 3, 8, where will it have been mapped to, right? It's going to be 3 minus 1, comma, 8 minus 3. Showing it with the mapping notation. And that's going to give us 2, 5. Again, probably a little more work there than you might need to show to get to the same result, but since I'm going through and explaining them here, that's the thought process. So B. So now that we've got our answer of B on the diploma, we would go to our Scantron or bubble sheet and find multiple choice number 1, and we would fully fill in the letter B with our pencil. All right, so multiple choice number 2 here, pretty similar to number 1, except slightly different things going on in terms of the transformations. So the function y equals f of x has a domain of all values of x such that 2 is less than or equal to x, which is less than or equal to 6. X is an element of the real numbers. So in other words, the domain of this is just the x's between 2 and 6, including 2 and 6. Okay, and a range of all values of y such that -4 is less than or equal to y, which is less than or equal to 8. Okay, so the range is between y being -4 and +8. The function then undergoes the transformation y equals -f of 1/2 x. Now remember, this is in our function notation for the transformations, and it basically acts like instructions for what we're going to do to this, right, if we know how to look at it. So just going back up here to where I wrote it, right, it's saying we're going to vertically stretch it by a, horizontally stretch it by 1 over b, horizontally translate it by h, and vertically translate by k. So we can kind of see here, if we look at this, right, I do see an a value here. Do you see it? Looks like a is -1, right? What's in a's spot? A -1. A equals -1. So for a vertical stretch, remember, that means we're multiplying all of the y values by that a. That's what a vertical stretch does. It multiplies the y's by a. So if a is negative, we end up with a vertical reflection across the x-axis, right? Because we're multiplying all of the y values by -1. So if y values were negative, they become positive when we multiply them by a negative. If they were positive, they become negative when we multiply them by a negative. So if you think of what that means, if we had a y value up here, maybe, now it's down here, right? Or down here, now it's up here. And you can see that just means it's getting reflected across the y-axis. So a is -1. We have a reflection across x-axis. And really, what we're actually effectively doing is multiplying y's by -1, okay? Now, our b value here, we can see, again, comparing to the equation, b is the stuff being multiplied by x in the function notation. So it looks like b here is 1/2. Okay, now be very careful. That doesn't mean that the horizontal stretch is 1/2. Again, because of that inverse operation effect, right? Since x is not isolated, it's really, if we were to solve for x in the ultimate equation, what we would end up doing is multiplying both sides by 2, right? If I had, y equals 1/2 x, for example, we might be tempted to say the horizontal stretch is 1/2. But if I were actually looking at how did going from this to this affect the x's, in order to figure that out, I'd have to isolate x, right? See what x is now equal to. And to do that, I would multiply both sides by 2, or divide both sides by 1/2, same thing. And I would see that, oh, now x is 2y, right? X used to be y, now it's 2y. So just be careful. Again, just a reminder of that fact that if we're multiplying the x by 1/2 in this notation, that means really what we're actually doing to each individual x value is multiplying it by 2. So we have a horizontal stretch by a factor of 1 over b. In this case, that means a horizontal stretch by a factor of 1 over 1/2, or 2 over 1, or 2, right? Meaning that our x's get multiplied by 2. Each individual x value for each individual point on the graph gets multiplied by 2. All right, so what does that actually mean for our domain and range? Well, if we think about it, right, our original domain we know was 2 is less than or equal to x is less than or equal to 6. So the lowest it ever got was 2, the highest it ever got was 6 on the x-axis. And we're about to multiply every single x value by 2 because of this horizontal stretch, right? So if we think about what that means, it's not like, you know, we get like a graph that's going to have, you know, a totally different shape. I mean, it will have a different shape, but what we're essentially doing is multiplying the min by 2 and the max by 2 and everything in between by 2. So all that's going to mean is that our new min is going to be at, if I do the new domain, right, I'll have x's such that, well, 2 times 2, right, 2, if I multiply every x by 2, multiply by 2, I'm going to get 4. If I multiply 6 by 2, I'm going to get 12. So our new domain is just going to be 4 is less than or equal to x, which is less than or equal to 12. X is an element of the reals. So looking at our options here, okay, right off the bat, kind of looks like D is the only right one, right? We can eliminate A, B, C just based on the domain. Good test-taking strategy there if we were, you know, pressed for time. But let's just double check. Let's check if the new range also fits. And sure enough, right, our new range, we're multiplying all the y values by -1. So we got to be a little more careful here, but I'm multiplying -4 by -1. That's going to give me +4, right? So if we think about what we're doing here, multiplying by -1 to get +4. And multiplying 8 by -1, I'm going to get -8. So notice when we do a reflection, our max and min end up switching, right? Old max becomes new min becomes old max, which actually makes a ton of sense when you think about what reflecting a graph actually does. Just to, you know, keep it simple with a parabola. Here I would have a min at that value. If I reflect it in the x-axis, that min has now become a max, right? Again, if I had something a little more like closed, where it actually did have a range from, you know, this min to this max, let's say, same thing happens when I reflect it in the x-axis. My old min here, right, this min has now become the new max here because everything got flipped upside down. My old maxes up here have now become the new mins down here, right? Makes sense. We flipped it upside down. So we still just multiplied everything but by -1, and then we can recognize that, okay, but that means now our range is from what used to be +8 has now become -8. That's actually our new min. -8 is less than or equal to y, which is less than or equal to +4. And if you had missed that, if you had flipped them out, you would kind of notice and correct it pretty quickly, because you would have 4 is less than y is less than -8. But how could y be between, bigger than 4 but smaller than -8, right? So that's the effect of flipping the graph there. So sure enough, we can double confirm that D is correct. Already kind of knew it from the domain, but now that the range is also correct, we're feeling pretty good about 2 being D. So on our Scantron bubble sheet, whoops, not B, we would fully fill in 2 being D. So multiple choice number 3 here, moving on. The graph of y equals f of x is transformed into the graph of y equals g of x, shown below. So looking at the labeling here, looks like the little one is f, the bigger looking one is g. And what are they actually asking us to do? We want to write an equation for g of x in terms of f of x. So basically they want us to do, you know, this. Fill this in to go from f to g, right? What would our vertical stretch need to be? Or is there a vertical reflection and it also needs to be negative? Horizontal stretch, b, or a reflection across the y-axis. Horizontal translation h, vertical translation k, right? What would those values be to properly go from f to g? Okay, so taking a look here, whoops, I counted that wrong earlier. If we take a look here, okay, right off the bat, I can actually kind of tell that there must be some kind of stretching going on, at least one kind of stretch, right? It's not just translations. I can't do this completely with H's and K's, which none of my options give me anyway. But if it were just H's, just K's, just translations, we wouldn't notice the shape of it changing in this way, right? If all I had done was taken F and slid it around, right, shuffled it around, shifted it, it would still look the same. It would just be in a different spot. And that's not the case here. So definitely some stretching going on. Let's start to look at the, can we figure out the stretch? I'll just look horizontally first. Doesn't really matter the order we think of the stretches, but I'll do horizontal first. I can see here we've kind of got, 1, 2, 3, 4 grid lines originally for how wide it was, so to speak. Just be careful, it's not actually 4 units, it's 5, 10, 15, 20 units. Right, because it's going up by 5s there. But either way, we would still notice that, well, hang on, this is the new one, g of x is 1, 2, 3, 4, 5, 6, 7, 8. 8 of those grid lines wide, or 8 times 5 is 40 units wide. So right off the bat, we can see, okay, to go from F to G, I would need to make it essentially 2 times wider. Right? Now, how do we make a graph 2 times wider? We need to mess around with the x values. We need to multiply the x values by 2, right? If we multiply every x value by 2, if I multiply, we can even check our work here. 5 by 2 gives me 10. Negative 15 by 2 gives me negative 30, right? So multiplying every x value by 2 would achieve this result of making it 2 times wider. Now, just be careful. If we have a horizontal stretch by a factor of 2, don't forget, that means B is really 1 over the horizontal stretch, right? 1 over 2. Again, comes from the fact that x is not isolated in our equation. So if we wanted to solve for x to find the actual effect of changing B, we would end up multiplying the other side by 2, and that's why all the x's are being multiplied by 2 when B is 1/2. Okay, so I'm feeling pretty good about that. B should be 1/2. I can kind of take a look here and say that eliminates A, that eliminates C. They're trying to trick us with A and C, right? We would notice the horizontal stretch was a factor of 2, but we got to remember that means B, our B parameter is 1/2. All right, let's look vertical now. Let's look vertical because it also has had its height changed. Right? So F originally was, I'm just going to do it off to the side here. We can see F was 10 units high, right? 2 squares on the grid. So 2 units high for F. Well, sorry, not 2. I shouldn't say 2. It's 10 units high. Okay. And G, the taller one, G is now 20 units high. So how do we go from 10 units tall to 20 units tall? We have to multiply every y value by 2, right? 10 multiplied by 2 would give me a new max of 20. So it looks like our vertical stretch, A, is 2, right? Vertical stretch factor of 2. And no funny business with A, no having to turn that into 1 over 2 or anything like that. Because again, y is isolated in this equation, right? Y is equal to this stuff. So multiplying this stuff by 2 really does multiply y by 2. So it's a vertical stretch by a factor of 2. A equals 2. So we're looking for something with a 2 in A's spot. And looks like our only option left, now that we've eliminated A and C, it's going to have to be D, right? Let's just confirm, though. I mean, why is it not B, for example, right? Well, we already know that A needs to be 2, but we can eliminate it as well for K, a vertical translation of 10. Did we actually slide this thing 10 units up? Let's see. Did we actually slide it 10 units up? Well, I don't think so, right? We know we vertically stretched it, by 2, so that would take this 10 and move it to 20. If I then translated it 10 units up, it should have ended up at 30, right? So that point wouldn't line up if we had done that. Now, you might be saying, but that one doesn't have the vertical stretch by a factor of 2. So is it possible to have just horizontally stretched it by a factor of 1/2 and then translated it 10 units up? Could that have worked? Well, I mean, not really, right? We can test it out here. Think about it. Let's just try ours. Let's do the vertical stretch by a factor of by a factor of 2, and then apply our vertical stretch by a factor of 2. If that gives us the right points on the new graph, then it should work out. So if I have, this point that's at -5, 10, if I first multiply the x by 2, it's going to be at -10, 10, right? So I just multiplied the x of -5 by 2 to get -10. And now if I multiply the y value by 2, so 10 by 2, I get 20. So that explains where this point ended up. The biggest reason I know there is no k value here is look at the points that would be invariant to a vertical stretch. So that's where y is 0. Because if we multiply 0 by a, it doesn't matter what a is, we still get 0. So after vertically stretching these, they would still be at 0. If I were to then vertically translate them 10 units up, those points should have ended up 10 units up. But they didn't, right? So that's the biggest clue that we have no vertical translation here. How did this point stay on the x-axis if it got shifted 10 units up after being stretched? Because after being stretched, it would still be on the x-axis. A y value of 0 times any a would still be at 0. So there's no way this could have been vertically translated. And again, just triple checking our work. If I take this point and can it be explained how it got to here with our equation, what we came up with? Well, yes, right? If I take the x value, -15, multiply the x by 2, it ends up at -30. Perfect. That's where the x value is on this one. If I then multiply the y value, 0, by 2, I get 0. So we would expect this point to end up at -30, 0. And we can explain that with our stretches, sorry. No translations needed. So definitely feeling pretty good about 3 being D. So on our bubble sheet, 3D. Alrighty, so moving on to number 4 here, multiple choice. Looks like another transformation one. Let's just see what we've got here. So we're starting with a point A that's at an x of -3, a y of 4, and it's a point on the graph of y equals f of x. And they want to know where is the corresponding image point, A prime, if we change the equation y equals f of x into this, right? So they've written it in function notation. Kind of nice when they do that because we can usually pretty quickly pick out A, B, H, and K. We just have to be careful that it's actually written in that format. So remember, we have y equals a times f of, and this is on your formula sheet, the general form for transforming stuff, x minus h plus k. And we can see that this is close to that, but it's not quite the same. This is a classic way they try to trick you, right? We got to notice here, this is not, the f of stuff is not actually in the form we would want it to be in to really be able to tell what b and h are, right? We have to have b times x minus h. That's an order of operations issue. That's an RST type thing, right? So this is not actually how we want it to be, but it's pretty quick to fix it. Let's just rewrite ours. All we would need to do to make it look like this is factor out the 3, right? Because then we would have 3 times x plus stuff, whatever it might be. So really, this is y equals 1/2 f of, if I factor out the 3, well, 3x divided by 3 is just x, plus 12 divided by 3 is 4, minus 1. All right, and so now this makes it pretty easy to see what we're working with. What is our A? So we've got A equals 1/2. That means vertical stretch, factor of 1/2. It's positive, so no reflection across the x-axis. B is 3. Again, though, be careful, right? Because of the fact that x is not isolated. If we were to isolate x, we'd have to do the opposite. This is actually a horizontal stretch by a factor of not 3, but 1/3. And similar reasoning here, it's supposed to be x minus h, one way to look at it. Also, we can understand that if in the real equation, if we were to isolate x, what we would end up doing to get it by itself is eventually subtracting 4 from each x to see what the effect on x really was. So our h is not 4, it's -4. right? X minus negative 4 could give me x plus 4. So our h must be negative 4. So that means we have a horizontal translation 4 units left, moving every x value, subtracting 4 from every x value, giving us moving it to the left. And same for k here, but no funny business with the opposite sign stuff. K is negative 1. We really are subtracting 1 from all of the y values. We can even see that in the equation, right? It's telling us take our y's, but we'll subtract 1. What's that going to do? Well, if we subtract 1 from y's, they get moved downward. 1 unit down. All right. So a couple options you could take to start approaching this, right? I mean, you could kind of just take this and start thinking about it. Don't forget the RST stuff though, right? RST, that's just order of operations. Since reflections and stretches are multiplications, we have to do them before translations, which are additions or subtractions, right? That's just following BEDMAS. Order of operations, we have to do any multiplications and divisions, so any reflections or stretches, before we do any translations, which are additions and subtractions. So one really good strategy for these is to just rewrite it in mapping notation. Remember, mapping notation takes the original point and it just kind of rewrites it as what's going to actually happen to those values. Okay, so it's not quite the same as this function notation, but it's telling us the same information in a slightly more like practical way. It's saying, so here's what you actually end up doing to every x, right? And to every y. So in general, what do? We take x's, we multiply them by 1 over b, right? And then we add our h to it, right? We add our h to it. That's the mapping notation part. If h is negative, we subtract an h as a result. And then for the y's, we go a, we multiply all the y's by a, then what do? We add k to them. So since we picked out a, b, h, and k, mapping notation gives us a nice little set of instructions here on what to do. So let's just jump right in and do it to our point a, negative 3, 4, right? That means we're going to take negative 3, 4, and since our 1 over b is 1 over 3, right? That's what we said we were going to do, multiply every x by 1/3, because that's our horizontal stretch. And our x is negative 3. And then we're going to add h, but that means we're going to, since h is negative 4, we're going to subtract 4, right? Plus negative 4 is subtract 4. And this all checks out, right? What did we say this meant? We were going to multiply every x by 1/3, and then we were going to move it 4 to the left. To move it 4 to the left, we have to subtract 4, right? If it's at 4, we have to move it to 0. That's 4 units left. So that's subtracting 4. And then for the y1, what do we get? Well, we're going to multiply it by our a, which is 1/2. Our y is 4 for our original point. And we're going to add k. K is negative 1, so we're going to subtract 1. Okay, so what does this give us? Negative 3, 4 will now become, so 1/3 times negative 3 is negative 1 minus 4. And then 1/2 times 4 is 2 minus 1. So negative 3, 4 becomes negative 5. 2 minus 1 is 1. So negative 5, 1. So it looks like C. Again, do you need to use the mapping notation here? No, that's just one way to kind of show my thinking. But you could also just take these and start thinking about it, right? Take negative 3, multiply it by 1/3. Then subtract 4, right? Mapping notation just gives a more visual demonstration of that. And then do the same process, but for y value with your a and your k. And either way, we should get the same result, that it is now at negative 5, 1. So option C. So here's kind of an interesting one, multiple choice 5, okay? They're giving us the graph of y equals f of x, and they're asking us the number of points that would be invariant. Remember, that means they don't change when we do something to them. So we do some transformation and they don't end up actually moving. When the graph of y equals f of x is reflected in the line y equals x. Okay, so we got to remember, reflecting in the line y equals x, right? That's just going to swap the y's for the x's. This is the same as taking the inverse which literally means if you start out with a point x, y, how do you get your new point? You switch the y value to become the x value, and vice versa. You switch the x value to become the y value, right? So literally, if we had a point at 1, 2, that point is now at 2, 1. That's not on this graph, I don't think, but just to give an example. Okay. So, and again, that makes sense, right? If we reflect it in the x-axis separates the positives from the negatives, so we end up switching negative y's to positive y's and vice versa. So similarly, reflecting in the line y equals x swaps the y's for x's. So I would actually just approach this as thinking about where would points not change if we did this? And if you look at this, you can realize, well, it's just points where, right? The invariant points will just be invariant points where x and y are the same, right? Because then if I switch them, it doesn't matter. Just to give an example, if 1, 1 were on my graph and I switch x and y, well, I've still got 1, 1, right? If negative 5 is on my graph and I swap x and y, guess what? My new point is still negative 5, so it's invariant. It hasn't varied. It's still in the same spot. So taking advantage of that lets me realize, well, then I just need to look for points where the y is already equal to the x. And there's a really quick and easy way to check if something has a y equal to x. Of course, you could individually try to find points, but that's probably harder than just recognizing that any point on the line y equals x satisfies this condition, right? Any point on the line y equals x has a y value equal to the x value. That's why it's on the line y equals x, right? That line is showing us everywhere where y equals x. So for example, 0, 0 would be on that line because y equals x at 0, 0, right? 1, 1, y equals x. 2, 2, right? Negative 1, negative 1, negative 2, negative 2. So the line y equals x essentially just looks like, I mean, I should probably use a ruler here to make it a bit better, but do my best, you know, something like that. And so that pretty quickly lets us see, well, where on our graph, how many places are invariant when we take the inverse? Well, how many places on our graph intersect with the line y equals x is really what this question becomes. Because this point is on our graph, but it's also on, this point is on the graph, but it's also on the line y equals x. So at that point there, y equals x. Taking the inverse is not going to change that point. We can even really see it here, right? It's at negative 2, negative 2. And then there's another point over here, right? I mean, we can see the intersection, but even if we couldn't, we can kind of tell that this is going to eventually have to intersect with that, even if we couldn't actually notice the intersection happening. So I see two places on our graph where the y value equals the x value, because I see two places where our graph intersects with the line y equals x. And then we can kind of tell this is going down like this is going down like this, it's a straight line, so they should never intersect again, right? There's no reason for these to intersect again based on what they've shown us. And then over here, same thing. This is headed up forever, this is headed down forever, never going to intersect again, okay? The arrows indicate that this is the continued behavior of the graph. So with that in mind, I see 2 points. I don't see any chances for other points. I see 2 places where we could get invariant points if we were to reflect this in the line y equals x to take the inverse. So that means for number 5, I feel pretty good about our answer being B. All right, so number 6 here, let's take a look. Kind of a classic one. How do we restrict the domain? A restriction on the domain of the graph of the quadratic function f of x equals a times x minus c squared plus d that would ensure the inverse of y equals f of x is always a function is, and then we got 4 options there. Okay, so honestly one we can kind of like think about and get there, but I'll go into the thought processes involved here, what we got to think about. Okay, first things first, let's just notice here, what type of graph is this? This is actually just a parabola, right? This is a good old Math 20 looking parabola, right? Where we're taking an x value and ultimately squaring it, And that's it, right? I mean, we're multiplying it by, in terms of like what changes, what type of graph this would be, that's it. All we're doing is squaring an x, okay? So we're going to have a times x minus c squared plus d, okay? We'll think about, what that means for the shape of that parabola and where it is and all that in a second, but now we kind of know we're dealing with a parabola. And it says we want to ensure the inverse is always a function. To remind ourselves of what that's saying, let's first remind ourselves of what it means to be a function. And the key characteristic of a function is that it has one y output for each x input. So whenever you put in an x, you're always going to get out one and only one y, right? You can't sometimes put in x is 1 and get out y is 3, and then other times put in x is 1 and get out y is 4, right? We should always get the same y output when we put in the same x input, okay? So with that in mind, that's where what you probably know as the vertical line test comes from. So the vertical line test, what we say for the vertical line test is if it's a function, it should only intersect the graph in one spot if we draw a vertical line anywhere. Why that is a good test for if something's a function is because what you're actually doing is you're checking every x value and seeing if there really is only one y, right? So this is a function, because when I draw a vertical test, I can see that it only intersects the graph once, meaning that at every individual x value, my graph only has one y value output, right? For every x input, there's only ever one y output. Something that is not a function would look, like this, let's say. Like a sideways parabola, maybe. That's actually not a function, and it fails the vertical line test. We can see, right? If I draw a vertical line there, intersects my graph in two places. And so we say it fails the vertical line test, but really what that means is that at 1x here, I have two y outputs. That's why the vertical line test works as a test of if something's a function or not. We're checking individual inputs and making sure we only get one output. That didn't happen here. We input 1x, two y's on the graph at that x. No good, not a function. Okay. So now that we've reminded ourselves of the vertical line test and what it means to be a function, let's think about what it means for the inverse to be a function, right? What that's essentially saying is how do we ensure that the inverse passes a vertical line test? How do we ensure that the inverse will be a function, right? Now, when we take the inverse, we essentially swap x and y. We swap vertical and horizontal. So we absolutely could. I mean, we couldn't here because we don't actually have the equation of the graph, but we could graph out the whole inverse ourselves and then do the vertical line test and say, aha, so no, it's not a function because it doesn't pass, the inverse didn't pass a vertical line test. But we could save ourselves some time and not actually have to graph the whole inverse by recognizing that, well, for an inverse, we swap x and y. So we swap horizontal and vertical effectively. So if I wanted to quickly check without actually graphing the inverse, will the inverse of this be a function? I can just make use of a horizontal line test. If the original passes a horizontal line test, then the inverse will be a function. Once we swap x and y, it would pass a vertical line test, right, is what we're saying there. So we can actually just cut out that step of actually graphing the whole inverse by saying, well, will the inverse of this be a function? Yes, it is a function, but will its inverse be a function? Let's just check with a horizontal line test. Oh, no, it won't. Once I swap x and y, that horizontal line basically becomes a vertical line, and that tells me that the inverse of this would not be a function. It itself is a function, but the inverse would not because it fails a horizontal line test. Okay, so that just means what we're essentially looking for here is how could we restrict the domain to make it so that it would pass a horizontal line test? And for any parabola like this, right, we're just looking for, okay, the whole thing definitely we can see does not pass a horizontal line test. But are there sections of it that could if we limited it to only a certain domain? Well, I mean, yeah, for example, what if I just use this part of it, right? From the minimum, from the vertex there to the right. If I only use those x's, if I said we're going to use this function, but only for x is greater than this vertex value, that part does pass a horizontal line test, right? If I just took this part, this could pass a horizontal line test, meaning that if I took the inverse of it, which would end up looking something like that, the inverse would pass a vertical line test. The inverse would be a function if I only used that section of the parabola. So let's put this all together now. We need our original function. We need the sections of it that could pass a horizontal line test in order to ensure that the inverse of it will be a function. For a parabola, we can kind of see it's just from the vertex to the right or from the vertex to the left. Not both, but one or the other would both pass a horizontal line test. We can't do them both at the same time because then we're just taking the whole parabola again. But we could say one or the other, right? To the right of the vertex or to the left of the vertex would work. And so we can remind ourselves, I mean, we could use Math 20 knowledge here, see that this is in vertex form, and therefore C is the x-coordinate of my vertex. We can also just use our transformations knowledge, right? We know that the base parabola, y equals x squared, has a vertex at 0, 0, because 0 equals 0 squared, right? And we're translating it by C units horizontally. Looks like C units to the right if C is positive, or C units to the left if C is negative. But either way, our graph is going to end up with its vertex at C, right? Where essentially, if I took this and moved it around, if I took y equals x squared, our graph's going to look something like, it would depend obviously on the sign and on the size of C and D, but let's just pretend it ends up looking like that, right? Its new x coordinate for the vertex would now be at C. I've moved it C to the right. Again, maybe I've moved it C to the left, but just to visualize, I'm picking and pretending we know that it's to the right. And I've moved it D up. And again, if D were negative, I would have moved it D down. But just so we can visualize a bit here, I'm pretending they're positive and negative. It's not like it changes anything about how we would approach this. So our new vertex is at CD, just like we learned in Math 20, right? Vertex form. That's our x-coordinate of our vertex. That's our y-coordinate of our vertex. So in order to guarantee that the inverse of this would be a function, which values of x would we need to include, right? Which values of x, for which values of x would our function pass a horizontal line test? Well, I think, right, from here to here, that could work. So we could say x must be greater than or equal to c, right? That's where c is. Could also say, couldn't say both, but we could say, or x is less than or equal to c. That would be for this little section here, right? That would also pass a horizontal line test, okay? However, they only gave us 4 options, so we got to pick, again, there might be more than one right answer, but out of the options they gave us, the only one that would work is x must be greater than or equal to c. For those values of x, our function passes a horizontal line test. So if we strict the domain to those values of x, the inverse of our function will itself be a function. So number 6, C. Okie doke, number 7 here. We are given the function f of x equals 4 times 1/3 to the power of x minus 16. And then we're asked the y-intercept of the graph of y equals f negative 1 of x. Again, that's not saying we're putting f to the power of negative 1. That is the notation we use when we're taking the inverse, which literally means we're going to swap x and y. Okay, so to the nearest hundredth is, and then we got to figure it out. So we're given the original function. We've got options here. We could take the inverse of the equation, swap x and y, and then go ahead and solve for x when y is 0, okay? We could also, though, since we're taking the inverse, we could find the x-intercepts of the original and use that to get the y-intercept of the inverse. Because again, we're swapping x and y, right? Swapping x and y when we take the inverse. So that's going to change the old x-intercepts into the new y-intercepts. For example, if we used to have an x-intercept at, I don't know, just making it up, 1, 0, when we swap y and x, we're going to end up with the point 0, 1. Well, that's a y-intercept now because x is 0. right? Again, 1, 0 is here, x-intercept. 0, 1 is here, y-intercept. And that's how those points would change if we took the inverse. So we can recognize it that way as well, that if I could find the x-intercepts of this, then there'll be the y-intercepts of this. Or again, you could swap x and y, use your logs to solve for y, and then get the y-intercept that way. Either way, we're going to have to end up using logs here, so it's kind of just a matter of preference. I might go with what I described there. I might say, let's first find the original x. Sorry, I think the video got a little bit cut off there. I'll just finish that thought. I'm going to find the original x-intercepts because I know once I take the inverse, swap x and y, those will be my new y-intercepts, which is what we're trying to find, the y-intercepts of the inverse. So let's find the original x-intercepts. And for an x-intercept, y equals 0. So I'm just going to take our equation, I'm going to make y equals 0 and solve for what x would need to be. So if I say 0 equals 4 times 1/3 to the power of x minus 16, okay, I just got to solve for x. So, reverse order of operations. I'm going to add 16 to both sides to get 16 equals 4 times 1/3 to the power of x. Continue working away at getting x by itself. I'm going to first just divide both sides by 4. Again, just undoing the stuff that's happening to our x, following reverse order of operations. 16 over 4 is 4, so now I know that 4 is equal to 1/3 to the power of x. And before Math 30, we would kind of be stuck. We wouldn't know what to do. We didn't have the inverse operation of exponentiation. We don't know how to undo the fact that something is being raised to the power of x. But now that we've learned about logarithms, we actually can deal with this. So a couple ways. We could just take the log of both sides. We could also rewrite this in its logarithmic form, and that'll let us start solving that way. I might just, in this case, we could do this. So again, all we're doing with a log, if I say log, I'm just going to write it up here, log base b of a equals x. All that's saying is that b to the power of x equals a, right? This to the power of this equals this. So we kind of have that here. 1/3 to the power of x equals 4, right? So that means I could just go ahead and say log base 1/3, right? 1/3 to the power of x equals 4, right? Saying the same thing, but in a logarithmic form. 1/3 to the power of x equals 4. And this is now solvable. We could use our change of base formula to be able to put it in our calculator, because our calculator can only do base 10, right? So we could write it as log base 10 of 4 over log base 10 of 1/3 equals x. And that's now something that we can actually punch into our calculator, right? If you do that, again, now we can put it in our calculator. Our calculator, at least older calculators, the newer, fancier ones, you can change the base, but for most calculators, the base is stuck at 10. But now, once we have our change of base formula, we can do anything, right? We can put anything into our calculator as long as we don't need an exact value, which we don't here. We just need nearest hundredth. So log base 10 of 4 divided by log base 1/3, log base 10 of 1/3 on my calculator gave me that x would be negative 1.2619. Okay. That totally works. Again, you could also have taken the log of both sides. Just quickly show you what that'll look like. Log of 4 equals log of 1/3 to the power of x. Then our exponent laws tell us we can put x down there. So log 4 equals x log 1/3. Okay. And then divide both sides by log 1/3. You'll notice we get the exact same equation. X equals log 4 over log 1/3. All right. But either way, now that we know our original x-intercepts, how do we get the new y-intercept? Well, like we said, swap x and y, right? Original x-intercept is at negative 1.2619, 0. That's why it's an x-intercept. Y is 0. So our inverse's y-intercept is going to be at 0, negative 1.2619. Or option A to the nearest hundredth, right? So tenths, hundredths. So negative 1.26. A is negative 1.26. Options, number 7 is option A. All right, so numerical response number 1, our first numerical response in this diploma. Let's take a look. If log base 2 of k equals 1/2 and cosecant of theta equals k, where 90 degrees is less than theta, which is less than 270, so we're between 90 and 270, then the value of theta to the nearest degree is blank. Okay, so we're trying to figure out what this angle theta would have to be. Now this is hopeless if we don't know k, right? Right now, cosecant theta could equal anything, so how are we ever supposed to figure out what theta is? So that's why they gave us this equation. So our brains are probably thinking, okay, maybe I can find k using this information. And then once I know k, it's a regular trig problem where cosecant theta equals something. And then I use that something to figure out what theta itself would be. And we also know that we're between 90 and 270. So it won't come up until we're actually finding theta, but maybe we should make note of that right off the bat. Right, we got 0, 90, 180, 270. And it's telling us we're between 90 and 270. So our angle, whatever it is, we're only going to take angles as solutions if they are in quadrant 2, right? Quadrant 2 or quadrant 3. So our solutions are only Q2 and Q3 only. So that'll come up when we're actually finding the angle. But like I said, we can't find the angle until we know what K is. So before any of that stuff, we got to figure out what K is. So let's see if we can use this to do that. So let's just write out what this is telling us. Step 1, find K. Okay, well, if log base 2 of K equals 1/2, remember, all this is saying, all a log is doing is representing an exponential function or equation in a different form. So this is just saying 2 to the power of 1/2 equals k. Well, that's great because we're trying to figure out what k is. So rewriting this in its exponential form, 2 to the power of 1/2 equals k. And remember, something to the power of 1/2 is just the square root of that number, right? Root 2 just equals k. Again, if you're not sure why, right? I mean, think about it. 2 to the 1/2 times 2 to the 1/2. That's just saying our exponent laws tell us, right? We have an exponent of half on 2 and an exponent of half on 2, and then we're multiplying those together. So our exponent laws tell us it makes sense to just add those exponents. So 2 to the 1/2 plus 1/2 is 2 to the power of 1. Half plus half is 1. So if we think about what that's saying, this is just the number that when we multiply it by itself, we get an answer of 2. Well, that's just the definition of the square root of 2, right? The square root of anything is the number that if you multiply it by itself, gives you the thing inside the square root. That's why the square root of 4, for example, is 2, or plus or minus 2. Because if I multiply 2 by itself, I get 4. So that's why 2 to the 1/2 is the same as root 2. Okay, anyway, now we know k is root 2. So life's looking pretty good for figuring out what this means. So now we can start working on, actually starting to find theta. Because now I know that k is root 2. K is just the square root of 2. So that means cosecant of theta equals k, but that means it equals root 2. And whenever we see a root 2, right, time to, at least think about one of our special angles. 1s, root 2s, root 3s, 2s, all of those get us thinking about special angles. I might just rewrite this just to think about it in maybe a slightly more intuitive way. Cosecant, remember, that's just 1 over sine, right? So this means 1 over sine theta equals root 2, or in other words, sine theta just equals the reciprocal of this. Cosecant is the reciprocal of sine, so sine is the reciprocal of cosecant. This just means sine theta equals 1 over root 2, right? So we're dealing with a reference triangle anyway that has an opposite of 1 and a hypotenuse of root 2. Sine theta equals opposite over hypotenuse. So we're kind of thinking about, like, if this is my reference angle, theta r, we know that this side, opposite is 1, hypotenuse is root 2, or y and r are 1 and root 2, and we might be able to figure out this is our 1, 2, 3 triangle. Oh, sorry, no it's not. No, it's not. I was mixed up there. Sorry about that. This is our 1, 1 root 2, right? That was my mistake there. I was thinking this was a 2. I forgot about the root there. So no, this is our 1, 1 root 2 triangle. Again, if you're thinking, oh boy, do I have to memorize that? I mean, it doesn't hurt to memorize the 2 triangles, but we could always check, like say if you only had these 2 sides and you're writing the diploma and you're really struggling to remember, notice we can just use the Pythagorean theorem to figure out what this would be, right? We know that whatever this side is, when I square it and add it to this side, a squared plus b squared equals c squared, right? The hypotenuse squared. Well, 1 squared plus the other side squared has to equal root 2 squared. So 1 plus whatever that other side is squared equals 2. Root 2 squared is just 2. So b squared equals 2 minus 1. So b squared equals 1. So b equals 1, right? Again, just a quick reminder of if you can only remember 2 sides, or you only know 2 sides of a special triangle, you can still get there even if you've forgotten one of the sides using Pythagorean theorem or SOHCAHTOA or whatever it might be. Anyway, now we know for sure, okay, this is our special triangle. It's the 45, 45, 90 triangle, right? 2 equal sides means 2 equal angles. So 45 and 45 is the only way to make a 90-degree triangle where the 2 other angles are equal. So our reference angle, now we know, is 45 degrees. So whatever theta is, it has a reference angle of 45. Now, let's think about, we're almost there, okay? Let's think about which quadrants our angle itself could be in if the reference angle is 45 degrees, and more importantly, sine theta is positive 1 over root 2. So sine theta is positive 1 over root 2. So it's greater than 0. Can use cast to help us out here. Again, cast is really just based on where x is positive and y is positive and where they're both negative and what that means for each ratio, since each ratio just divides x over r for cos, or y over r for sine, or y over x for tan, right? But a quicker way to, get quicker answers is just to use cast here, even though cast is based on those ideas we were just talking about. So if sine theta is positive 1 over root 2, that means, again, sine is positive. So everything is positive in quadrant 1, and sine, only sine, is positive in quadrant 2. So normally that would mean, okay, we've got to look for the angle in quadrant 1 that has a reference angle of 45 degrees, and the angle in quadrant 2 that has a reference angle of 45 degrees. And those would be our 2 solutions. But don't forget, they told us our domain is just limited from 90 to 270. So that eliminates quadrant 1. So is there an angle in quadrant 1 that could make this true? Yes, but we're only looking between quadrant 2 and quadrant 3 based on the limitations of our domain. Quadrant 3 is eliminated because of cast, right? If we were in quadrant 3, sine theta should equal negative 1 over root 2. And same goes for quadrant 4. So that means we really only have one quadrant to look in. It's quadrant 2. So we can actually now find that angle theta. And honestly, for me, just a quick diagram is the easiest way to think about it. Once you do it enough, you start to just know the rules, but when in doubt, a diagram will always back you up. So if we're in quadrant 2 and we have a reference angle of 45 degrees, we want to know what is the actual rotation angle itself. So what is that angle? It has a reference angle of 45. Well, 0, 90, 180, right? Hopefully we can see that. That angle theta, the orange part, is just 180. Here's a full 180, but minus 45, right? We need to take a full 180 in purple there, and if we subtract off 45, we'll be left with theta, the orange there. So theta equals 180 minus 45, which equals 135 degrees. So for a numerical response question like this, always check the form that they want your answer in carefully, but here they just want us to say the angle. So the value of theta to the nearest degree is 135 degrees. So we'll go to the Scantron, the bubble sheet here, okay? Now, we don't need all 4 boxes, right? Our answer is only 3 digits. So whenever that happens, we start in the first box, and if we don't need any, great. but we always start in the first, okay? So I'm going to do 135. And now I don't need that last box. That's fine. I just bubble in. So 1, 3, and then for the third one, 5. Make sure you fill in those bubbles. You can't just write in your answer. You've actually got to fill in the bubbles for the machine to mark it. Okay, so this is good. This would get marked correct. Be careful. This would not. So you don't want to ever leave the first box blank and fill in the last 3. Okay, always the other way around. Always start in the first box. If you don't need any over here, that's fine. Okay, and don't forget to actually bubble in your answers. Don't just write it here because it's marked by a machine that looks for the bubbles. There we go. All right, let's take a look at number 8 here. So if log base 3 of 5 equals 3y, log base 3 of 4 equals 2x, and log base 3 of m squared equals 6, then log base 3 of 100 times m to the 4th is equivalent to what? Okay, so we don't know anything about what log base 3 of log base 3 of 100 m to the 4th is, right? They didn't give us any information on that. But they did tell us about log base 3 of 5. That's just 3y. Log base 3 of 4 is just 2x. And log base 3 of m squared is just 6. Okay? And we can kind of see in here that, maybe we could rewrite this to start looking more like these. We basically need to make these show up in our equation, our expression, I should say, right? Because we know stuff about log base 3 of 5. So if we can make log base 3 of 5 show up, rewriting this so that log base 3 of 5 shows up, then we know, well, log base 3 of 5 is just 3y, right? So we can replace log base 3 of 5 with 3y in our equation. Same goes for these ones. If we can make them show up, then we can just replace them with 2x or 6, respectively. So this problem essentially becomes, how do I rethink of log base 3 of 100 m to the 4th in terms of these things, these expressions that I do know stuff about, okay? And so let's just think about how can we rewrite 100 and m to the 4th so that, we've split it up a bit and we've written it in terms of how it's related to these. So this is going to come down to expanding this logarithm using our log laws. Okay, so I have log base 3 of 100 m to the power of 4. Now we have the log law on our formula sheet that log of m times n can be rewritten as log m plus log n, right? We can add the logs individually. Again, the proof of all that might not be really worth the time right now, but you can check out that lesson if you really want to rehear why this rule works. Okay, but important note here, they do have to have the same base. I kind of left that out here, but to use any log laws, they need to all have the same base. Here, I'm not too worried about that because everything's in log base 3, so I feel like we're probably going to be able to use our log laws quite a bit here without having to worry about same base. Okay, so I'm going to use that to start just splitting this up. Let's just do it kind of, see what we get. If I first, this is 100 times m to the power of 4, so I could think about that as, m and n, so to speak. So my first step, I might just split this up into log base 3 of 100 plus log base 3 of m to the power of 4. By the way, folks, there's definitely more than one approach you could take here. You might notice different relationships that jump out at you in different ways, but here's one way we could do it. They're all based on the same things, but you just might, recognize the relationships in a different order than I do, for example. Okay, so getting back into it here. Now, again, we're not done, obviously, but we're getting closer. I need log base 3 of a number, log base 3 of a number, and I need log base 3 of an m squared to show up. At least we've split up the number times m stuff, right? So I can start now focusing on how do I make this look a little bit more like log base 3 of 5 and log base 3 of 4? Well, if we could rewrite 100 as a product of 5 and 4, then we could kind of make use of this again, right? 100, if we think about it, is really just, can we factor 100 in such a way that we get 4s and 5s? Well, 100 is 20 times 5, for example, right? 100 is just 20 times 5, and then, hey, 20 is just 4 times 5. So this is really like you could do 20 times 5, and then you might recognize, hang on a sec though, 20 is just 4 times 5. So 100 is just 4 times 5 times 5. Right? I haven't broken any rules. 100 is the same thing as 4 times 5 times 5. And same thing here, we could recognize that this is, again, I'm trying to make log base 3 of m squared kind of show up. I have log base 3 of m to the power of 4. But m to the power of 4 is just m squared squared. Okay, so we're getting somewhere. Getting a little bit closer. I'm going to use this product law again to split this up. Log base 3 of 4 times 5 is the same as log base 3 of 4 plus log base 3 of 5 plus log base 3 of 5. And then for this one, if I want to make it look like log base 3 of m squared, right now I'm squaring it. I've got options. I could split this up. This just means m squared times itself, right? So I could rewrite it as log base 3 of m squared plus log base 3 of another m squared. I could also use my exponent law. I could bring that 2 down here, right? Maybe I'll do that for this one just to mix things up a bit. Plus 2 log base 3 of m squared. Okay. And now look at this, folks. What were we trying to make show up? Log base 3 of 5, because we knew that that was just equal to 3y. Well, hang on a sec. Log base 3 of 5 is just 3y, right? Log base 3 of 5 is just 3y. So I've just rewritten it now. Whoa, I've just rewritten it now in a way where I actually know stuff. I know what these things are equivalent to, right? Log base 3 of 4 is 2x. So this is just equivalent to 2x. Okay, so working through that, let's just keep track here. Log base 3 of m squared is just 6. So I have 2 times, well, this is 6. So let's go ahead and make those substitutions then. Log base 3 of 4 is just 2x. Log base 3 of 5 is just 3y. Log base 3 of 5 is just 3y. And then plus 2 times log base 3 of m squared, but log base 3 of m squared we know is just equivalent to 6. So what have I got? I've got 2x, 3y plus 3y is 6y, and 2 times 6 is 12. So 2x plus 6y plus 12, or in a slightly different order there, 6y plus 2x plus 12. So it looks like option B. So for number 8, we're going to bubble in on our sheet B. So for number 9, we've got another one here with our log law stuff going on. Okay, the expression log base a of b plus 4 times log base a of ac minus 4. Okay, we'll talk about that. Where a, b, and c are all greater than 1. Written as a single log is which one? Okay, so obviously this is about condensing logarithms, right? We've got a log plus a log minus a number, and we've got to think about how to condense that down so that it's just one logarithm, right? Log base a of stuff, okay? So this minus 4 here, we'll talk about it when we get there, but it's going to pose a problem, right? Because remember, for all of the laws of logarithms, they only work when we have a log with the same base. So if you look at your formula sheet, right, you'll notice they're all written out with the same base. We can't do, like if I have log base 2 of 7 plus log base 3 of 4, I am not allowed to do this. I'm not allowed to combine them. Kind of makes sense too, right? Because then what would our base be? You kind of notice that, oh, hang on, can I do this? Because we can't actually combine those logs. They have a different base. What would our new base be, right? So they need to be logs with the same base. And this one, not only is it not a log with the same base, it's not even a log. So that 4 is going to pose a problem. We're going to have to think about that when we get there. Let's just start with the easier stuff, though. We know how to combine these using our log laws. Okay, so I've got log base a of b. Now be careful, right? The 4 here, just to make it a little clearer what we're doing, I'm just going to move that 4 up. So use the exponent law that we have of log base b of m to the n is equivalent to n times log base b of m. I'm going to use that to actually just rewrite that 4 up in my exponent, just to make it a little bit easier here to think about how do I then combine log base a of b with log base a of something else, whatever I get once I do that. So I'm just going to take this 4 and put it up here. So this is plus log base a of ac to the power of 4. And then we've still got this minus 4, minus that constant that we're going to have to worry about at some point. So let's just, might do one more step here just to make it super clear before I combine the logs. This is really giving me log base a of a to the 4th, c to the 4th, right? I'm doing ac times itself 4 times. So I'll have a to the power of 4 times c to the power of 4, minus 4. Again, not mandatory to do it in the exact same order and steps as me. You can take different paths to the same result, but that's how I'm going to approach it here, is this way. So now we can use this log law, right? I'm adding 2 individual logs, so I can combine them into one log where the arguments are multiplied. So that means I really have here log base a of b times a to the 4th, c to the 4th, right? Or a to the 4th, b, c to the 4th, however, whatever order you write it there, minus 4. Okay, so now the time has come. We've combined the 2 logarithmic ones into one log. They both had a base of a, so that was no problem. How are we supposed to deal with this 4? Because it is not even a log, let alone a log with the same base. But that gives us some ideas, right? Because we could rewrite, remember, a logarithmic expression is equivalent to just some number, right? So can we think of a way to rewrite 4 so that it's equivalent to a log with a base of a, right? I need to rethink, how do I write 4 as a log base a of something? So if we think about this, I want log base a of something equals 4. Because then I could just rewrite 4 as log base a of something, and then once this is rewritten as log base a of something, I can combine it with this. So what could we have here? A to the power of 4 equals what? Well, I mean, a to the power of 4 equals a to the power of 4. We're totally allowed to do that, right? I mean, that's just saying what a log says. This to the power of this equals this. So if I had log base a of a to the power of 4, that would equal 4. We're not saying anything that isn't true here. A to the power of 4 does equal a to the power of 4. So that means if I wanted to rewrite 4 as a log base a, it's just log base a of a to the power of 4. So here we go. We did it, right? Log base a of b a to the 4th, c to the 4th, minus 4, yes, but we could think of 4 as just log base a of a to the power of 4. And now what we've achieved is what we set out to do. This is 4, but written as a log base a, meaning I can use my log laws to combine it with this log base a. And for this one, I'll have to use the fact that log base b of m over n equals log base b of m minus log base b of n from our formula sheet, okay? So I'm subtracting 2 logs, means I can divide this one by this one inside one log, right? So m minus n can become m over n. So this is really just log base a of b a to the 4th, c to the 4th, over a to the 4th. And then a to the power of 4 over a to the power of 4 is just 1. So those just cancel out, actually. So log base a of b, c to the power of 4, which looks like option C. So going to our Scantron, our bubble sheet, number 9 is C. All right, so another numerical response here. The graph of y equals log base b of x plus c, shown below, passes through the points 0, 0, and 3 over 2, 1 over 2. So 1.5, 0.5. And always a good idea to read the question so you can start thinking about what we're looking for. Even sometimes before you read this, it's a good idea to read the question so you can pick out the important information. But the value of the base b to the nearest hundredth is blank. So we're trying to figure out what is b. Okay. Now they gave us the graph. Honestly, nice of them to do that, but I don't think it really matters here. I don't think we need the graph that much. I suppose what the graph does let us do is confirm things like, you know, the sign of c. So it'll maybe help us check our work because we can tell this is a logarithmic graph that's been translated to the left. So that's one thing, but I think this question is completely solvable without the picture of the graph here. You'll notice in my solution, I'm probably not actually going to use the graph much, other than a quick check maybe to see that my work makes sense. That if we get a horizontal translation to the left, that it checks out with the graph. Okay, but not actually mandatory here to see the graph in order to be able to solve this. So let's take a look. Problem is, in solving for b, we don't know two things, right? If there's one equation and two things we don't know, we can't actually solve, because if I don't know what c is, how am I supposed to eventually isolate b? Because I don't know what this is. However, we were given 2 points. And whenever we're given two things to substitute into the equation, often what that means is we can use, 1 point might let us find one of them. And now that we've got one of them, that means we only don't know one thing in our equation, so we can probably solve for the other, right? I should say, too, technically, like y and x are just standing in for any number, but since they gave us 2 points, we can substitute those in as x and y and make it into equations where b and c really are the only things that we don't know in those equations. So, before I'm able to find b, I'm going to need to figure out c, okay? Now, they gave me 2 points. Which one should I use to find c? I mean, often 0, 0, that's going to be a nice point to try, even if it doesn't end up working out. 0, 0 is really easy to work with because then 2 parts of your equation just become 0. So I'm going to start there. Let's see if we can find c using the fact that our graph passes through 0, 0. Okay, because if our graph passes through 0, 0, then that means y being 0 and x being 0 needs to satisfy our graph's equation. All a graph shows us is every point that satisfies the graph's equation, every combination of x and y that makes this equation true. So they're telling us, by telling us that it passes through this point, that x being 0 and y being 0 makes this equation true. So I can use that fact to say that, okay, when y is 0, then this equation, this log base b of x plus c, should be log base b of 0 plus c, right? Just subbing in 0 for y and 0 for x. And so you'll notice that this just tells me 0 equals log base b of 0 plus c is just c. And hey, this is looking pretty promising, because remember, for any log, this to the power of this equals this. Right? The base to the power of this equals the argument of the log. So rewriting this in its exponential form, b to the power of 0 equals c. And we don't know what b is, but it doesn't matter now, because anything, whatever b is, anything to the power of 0 equals 1. So now I see that my c value here is 1. And again, like I said, this is where the graph could, I guess, come in a little handy, because now we can say, okay, if c were 1, would this thing be translated to the left? And yes, it would, right? Because a little tricky, but we'd have x plus 1. So if we wanted to think about the h value there, our h is -1. So yes, a translation to the left. Again, not mandatory, but a nice little work check, I guess. So now that we know that c is 1, well, we can use that, right? C is 1, so that means our equation is really, so step 2, find b, right? We can use the other point now. We can say that we know that y equals log base b of x plus c, yes, but we just figured out that c is 1, so x plus 1. And so if we use the other point here, I'm just going to Well, no, I'll keep it in fractions. I was going to say I'm going to work in decimals since they wanted our answer to the nearest hundredth anyway, but honestly, these fractions are pretty nice to work with anyway. So now I know that 1/2 equals log base b of x being 3/2 plus 1. And hey, look at this. The only thing I don't know is b. If you only don't know one thing in an equation, you should be able to solve for that one thing, right? So let's just simplify a bit here before we start worrying about getting b by itself. I have 1/2 equals log base b of 3/2 plus 1. You can think of that as, right, 3/2 plus 2/2 or 5/2, right? Just getting a common denominator for our 1, if you like. So log base b of 5/2, or if you're working in decimals, 1.5 plus 1 is 2.5. So that checks out. And then that means, again, using just our logarithmic relationship, just basically the definition of a logarithm, b to the power of 1/2 equals 5/2. b to the power of 1/2 equals 5/2. And remember, something to the power of 1/2, that really means the square root of b equals 5/2. Again, not even necessary to rewrite it this way, because you could also just say, what do I have to do to get b by itself? How do I get rid of an exponent of 1/2? I could put it to the power of 2, because then 1/2 times 2 is just 1. Or same idea here using the square root. What's the opposite of square rooting? It is squaring. So if I square both sides, I get that b must be 5/2 squared. So 5/2 times itself. Well, 5 squared is 25, over 2 squared is 4. So b equals 25/4, but they wanted it as a decimal to the nearest hundredth. So if we go ahead and actually divide 25 by 4, we get 6.25. So that would be our answer for this one. So for a numerical response, right, we are, in this format anyway, we do include that decimal when we fill it in on our Scantron, or our bubble sheet, okay? So numerical response 2, we got 6.25. Notice they give us the little bubbles for decimals. So I need to say 6.25. So 6, and then I'm going to fill in the little decimal bubble, 0.25. Alrighty, so looking at number 10 here, another log type 1. Given that y equals a to the x over a to the power of 2x minus 6, and that log base a of y equals x, and a is greater than 1, what is the value of x? So in other words, solve for x. Okay, so we're kind of given almost like a system of equations here where there's two equations, yes, and two things we don't know, right? So even though we don't know a and we don't know x, we have two equations that involve a and x. You might recall from previous math courses, right? Whenever we have two equations and only two unknowns that appear in both equations, we can actually still solve for each unknown, right? So there's hope here, even though there's two things we don't know. So let's just take a look. My mind actually right away goes here, and I say, does this tell me anything interesting that maybe I could use to simplify a bit here, or maybe make a substitution here, like we normally would for a system of equations? Because remember, this is just saying a to the power of x equals y. A logarithm's just another way of writing an exponential relationship. So that means, right, we could take this and use it to say that a to the power of x equals y. Or in other words, y is a to the power of x. Now that's pretty handy to know, because if y is just a to the power of x, well look, a to the power of x shows up in this equation here. By the way, this is not the only way to approach this one, but it's kind of where my mind went when I saw it. So if a to the x is y, let me now rewrite this, make that substitution, where I'll say y equals, yes, a to the x over a to the 2x minus 6, but that just means y equals, well, y over a to the 2x minus 6. Maybe it doesn't look like we're too much closer to solving, but I mean, we definitely got a little bit more information here. So maybe let me try solving, at least get it so where I just have the x's on one side. You can kind of see this is starting to look like just a good old regular exponential now, right? I don't have a to the x over another a to the x. I've gotten rid of one of my x's essentially. So it looks a little bit easier to solve. I'm just going to multiply that a to the 2x minus 6 by both sides. And then you can probably guess my next step here. Let's just divide both sides by y so that I have a to the stuff equals, other stuff. And even more helpfully, when I divide both sides by y, I just get a to the 2x minus 6 equals y over y is just 1. And now, looking at it, we've kind of got a exponential equation that we've got options here. I could take the log of both sides. That's one option. I could also try to rewrite this in terms of common bases, right? You might be saying, well, how could you do that? You don't have an a over here. I actually do, or I could anyway, write 1 as a power of a, right? If this were a different number, I couldn't really do it because I don't know what a is. But since this is 1, we could actually just write it as a to the power of 0. Again, not the only option. We could have said, log of a to the 2x minus 6 equals log of 1. Then, use our exponent law for a logarithm to bring down that 2x minus 6. Log a equals log 1. And then you can see that way we're also pretty close to solving it using that method. So not the only option, but I think here the slightly easier way to go at it is to recognize that 1, we could just write that as a to the 0. So now I have a to the power of 2x minus 6 equals a to the power of 0, right? Well, that's only possible. How could a to this power be exactly equivalent to a to this power if the powers themselves weren't equal, right? How can I raise a to some power and have it be equal to a to some different power? It's not possible. They must be the same power. So that just lets me say that 2x minus 6 must equal 0. Right? Checks out, even going back here. A to the power of something equals 1. Well, the only thing I can raise a power to and get an answer of 1 is 0. So 2x minus 6 must be 0. And therefore 2x equals 6. And therefore dividing both sides by 2, I get that x equals 3. So option A. So number 10 is A. All right, so another numerical response here. One looks like it has to do with compound interest. So let's just read here first, and then we'll talk about the formulas we have on our sheet and the one we don't have on our sheet. But Joe invested $4,500 at a fixed annual interest rate, compounded annually. At the end of 12 years, the investment has doubled in value. Okay, so yes, we're dealing with a compound interest rate one. Now, just want to remind ourselves of the formulas here and what they're saying, and more importantly, why they make sense, right? So this is what is on your formula sheet. This one is not. To be honest, do you need to memorize this one? If you understand this one, you can see that it's just a special, not even special, it's just a more specifically labeled version of this, okay? Let's just break it down. This is the formula that is on your sheet, and it's labeled as the exponential growth or decay equation, right? And it makes sense when we understand what each thing is saying. So y, that's just our new amount. It's what we're going to end up with, okay? A is the original amount. It's what we started with. And then b is what we're multiplying that original amount by repeatedly, right? That's why there's this exponent here, because we're going to repeatedly multiply by b. So if something doubles every year, for example, well, that just means every year we're multiplying what we started that year with by 2, right? Every year we're multiplying repeatedly by 2, for example. Or if it gets half as large, then b is 1/2. We're multiplying by 1/2 repeatedly. Okay, and then the exponent here, they break it up into t over p, okay? T is just the total amount of time that's gone by. P is the time it takes before we have to multiply by that b again. So you can see that combining these two, really all it's saying is how many times do we actually need to do that multiplication by b? That's why it's our exponent. We're going to multiply it by b that many times, right? So again, going back to my example from before, if, say, 2 years have gone by, and it doubles every 1 year, then 2 years over 1 year twice, right? It should have doubled twice. So we'll multiply by b to the power of 2, right? And that's why hopefully that exponent there kind of makes sense. Now, This is what we call the compound interest formula. It's not a new formula. It's just this one, but more specifically labeled to have to do with money terms. So A it stands for amount. It's the new amount. Hey, that's what Y stood for, new amount. Little a here is what we started with. Well, when we're talking money and investments, we call that the principal. So it literally means the original amount of money that you started with. No different than what A meant here. The principal just means an initial amount of money, has a special name. Okay. Now B, this part, I can see how you might say, well, that looks pretty different, but it's not, because we're just saying I is the interest rate as a percentage, right, expressed as a decimal. So like, for example, if it were 7%, percent literally means per 100. So 7% per 1 is saying 0.07, right? That's 7% is expressed on a decimal. 100% as a decimal is just 1. It's 1 out of 1, right? Versus 100 out of 100, okay? 50% is half, so 0.5, like we would expect, okay? Divide by 100. So all this is saying, if I have a percentage rate that or an interest rate, that increases my principal by 7% every year, let's say, just to work with some numbers, that means I'm just multiplying by 1.07, right? If it stayed at 100% of its original value, I'd be multiplying by 1. That's 100% of what I started with. If I started with $100, then I would have 100% of that, or $100, if it didn't change, if it didn't grow or shrink, right? But if it went up by, let's say, 7% again, right, I would multiply by 1.07. It got bigger by 7%. So if I had $100 and it grew by 7%, that's saying it grew by 7% of 100, or grew by $7 in that case. Okay, if it shrank, same thing, but we'd subtract it. If it shrank by 7%, I would multiply by 0.93. That's 100% minus 0.07. It's now 93% of what it used to be. Shrank by 7% of what I started with. Again, $100 would become $93, meaning that I lost $7, which was 7% of what I started with. Okay, so that's just our quick, reminder that B and this are really saying the same thing. If it's a percentage growth, we multiply by, 1.0, whatever percentage represents our interest rate. An important note that we'll get into here in a second, it is the interest per compounding period. So that comes up in these questions. Sometimes maybe it's 10% annual interest, which means over the whole year it's 10%, but it might be compounded monthly, meaning that each month you're paying 1/12 or earning, depending on whether it's a loan or debt, right? You're earning 1/12 of that 10% interest for the whole year. So it's the interest rate per compounding period. Again, a compounding period is just when they're going to actually calculate the interest and apply it. So sometimes you have an annual interest rate, but it's spread out over multiple months. If it were a monthly interest rate, you might say, again, if it was 10%, 10% divided by 12. That's how much interest is actually being calculated and applied each month. So that the total is 10% over the years, but it's actually calculated and applied in split up amounts over the 12 months. Okay, that's actually not going to come into play in this question because it's just compounded annually and it's an annual interest rate. So it's just, we're going to divide by 1, but still good to note. And then N is just the number of compounding periods that have actually gone by. So if we compound monthly, let's say, then in 1 year, we're going to multiply by our interest rate 12 times. Of course, our interest rate here would get divided by 12, but then we're going to actually apply it 12 times. In other words, we multiply by our B 12 times in that example. So N is just the number of compounding periods that have actually gone by. If you have, 10% annual interest compounded monthly, then in 2 years, 24 months have gone by, so we need to multiply by this 24 times. But don't forget it's compounded monthly, so we would take that 10% annual interest and divide by 12. Okay, so I just want to do a quick recap of what these formulas are and what they're saying. But again, you don't necessarily need to memorize this one. I mean, you can if you want. I find it easier to understand how it's really the same thing as this. It's just made more specific to the money we're working with. Let's now take that and see if we can use it to solve this question. So Joe invested $4,500. So that is our principal. That's what we started with, right?
at a fixed annual interest rate compounded annually. Okay, that's important to know because it tells us what we're dividing our interest rate by to get the interest rate per compounding period. It also is going to help us figure out how many compounding periods have gone by. So at the end of 12 years, well, there you go. Every year it's compounded and 12 years have gone by. So we're going to need to, multiply by our b value, or our 1 plus I value, 12 times. Our n, our exponent, is 12. And it tells us that the investment has doubled in value. So that's the new amount of money, right? That's what he ended up with. So if it doubled in value, our new amount was $4,500, times that by 2, we now have $9,000 at the end of 12 years. So let's just write this out, okay? I guess I'll use the compound interest version, but again, it's really the same thing, just made more specific. So if I take that, the amount is equal to the principal times 1 plus the interest rate to the power of n. Well, we invested $4,500, okay? Our interest rate, that's what we're trying to find, sorry. We're trying to find the interest rate. Joe's investment pays interest at blank % per year, also important, okay? So it really is, we're looking for the annual interest rate. So no funny business here with having to actually divide by anything. Compounds once per year, and we want the yearly interest rate. It's not like it compounds monthly and we want the yearly interest rate. All right, so, and I forgot to put in our A. Our A is 9,000, right? We know we have $9,000 at the end of these 12 years. And I also forgot to put in the N, which is 12. There we go. Okay, 12 years have gone by. Every year we apply the interest. So let's go ahead and see if we can solve for I. I'm just going to, first things first, right? Reverse order of operations. So we're not allowed inside those brackets or to deal with that exponent until we've dealt with the fact that it's all being multiplied by 4,500. So let me divide both sides by 4,500, divide by 4,500. Okay, this makes sense actually. I'm just going to drop the color coding now. 2 equals 4,500. Nope, sorry, I divided by 4,500. That's gone. 2 equals 1 plus the interest rate to the power of 12, right? We actually, even if they hadn't told us the initial principal, they had just told us that it doubled in value, we actually still could have solved this question. Nice of them to tell us that, I guess, so we could work out the new value, but all we actually need to know is that the new value is twice as big as the old one, right? We could let 1 represent the initial value, and then the new value just represents 2. It's just twice as big, because we'd always end up doing this step. So no matter what the initial value was, if it's doubled in value, it kind of means the same amount of time has gone by with the same interest rate. So that means we're continuing here now to solve for I, the interest rate. Now 1 plus I in brackets is being raised to the power of 12. Honestly, probably the simplest way to deal with that is to put both sides to the power of 1 over 12, right? Put both sides to the power of 1 over 12. Or you could take the 12th root on your calculator. But I think in the calculator it's probably easier just to type in 2 to the power of 1 over 12, which gives us 1.059463, and that is 1 plus the interest rate. So the interest rate is that minus 1. You need to subtract 1 from both sides, so the interest rate is just going to be 0.059463. Don't forget, though, that's still as a decimal. We want to, that's per 1. We want to convert it to per 100, to per percent, right? So in order to do that, let's multiply by 100%. And get that this is 5.9463%, or to nearest hundredth, the question says, so 5.9, and because that 4 is followed by a 6, we're going to round that 4 up to a 5. Be careful with your rounding, right? And that's why we don't want to round until the very end, or at least over round until the very end, so that we're sure we're keeping the accuracy as we go. And so, yeah, if you put 5.94, the diploma will mark it as wrong. So be careful with the rounding. These numerical responses are kind of done, either they're right or they're wrong. So we don't want rounding to take a mark off for us. I hear my cat meowing in the background. Not sure if you guys can hear that, but number 3, 5. We are going to include that decimal again, 5.95. So 5.95. Again, be careful checking the format of the question and how they want you to record it, but they're just asking us for the interest as a percentage, so we would just say 5.95 and bubble those in. Alrighty, number 11 here. If we read the information, sometimes a good idea to read the question and then read the information just because it clarifies what you're looking for. Let's try that here. So which of the following rows shows the correct values for A and B? Noticing here A and B are just part of these two like factors that some polynomial gives us, so you can kind of tell. Looks like we're going to have to factor something. Looks like we're going to have to factor this, but let's just read. In order to factor the polynomial function p of x equals 3x cubed minus 2x squared minus 19x minus 6, a student determined that the function has a 0 of x equals 3. Ooh, that is very nice of them to tell us. Normally, we would have to figure that out on our own. We'd have to test some numbers to find a 0, but they're just giving us one. He then wrote the polynomial as a product of a linear factor, so this is a linear factor because the biggest power on x is 1, and a quadratic factor. You probably guess that's the quadratic factor because the biggest power on x is 2, as shown below, where a, b, and c are all integers. So they're just telling us these are all integers. We shouldn't be getting any fractions or decimals when we solve for a, b, or c. Okay, so we were right. It really is just a factoring a polynomial question, right? We need to factor p of x equals 3x cubed minus 2x squared minus 19x minus 6, and they've actually already done some of the work for us because they told us that it has a 0 of x equals 3. So remember, if an a is a 0, let's say, so if a is a 0, then that means x minus a is a factor. Why? Because if I have p of x and I want to write it as some product of factors, right? If I have x minus a is one factor, that just means x minus a times something else would give me p of x, right? That's what it means to be a factor. 2 is a factor of 6 because I can do 2 times 3 equals 6. 4 is not a factor of 6 because 4 times some integer does not give me 6. Right? So what it's saying is that x minus a, if a, here I'll just say some other factor, right? If a is a 0 of the function, then x minus a is a factor, which actually makes a ton of sense because if we think about writing p of x as a product of its factors, well then, if I make this 0, right, then the function becomes 0 because I would have 0 times doesn't matter. It's going to equal 0, right? So if a is a 0, it means x minus a is a factor, right? If a is a 0. Now careful, I'm not saying a is 0. I'm saying it's one of the zeros of the function. Just to give an example, like, well, let's use the example they gave us. X equals 3 is a 0 of the function. What that means is that x minus 3 must be a factor. Because again, you can see, right, times some other factor. A 0 of a function is just a value of x that's going to make the function equal 0. So notice if x were 3, I'd have 3 minus 3 is 0. And then it doesn't matter what this is, 0 times anything would make my function equal 0. So p of x equals 0 when x is 3. And that's why knowing that it has a 0 of x equals 3 tells us that it has a factor of x minus 3. It must. Because otherwise, how could making 3 be x give us the function's value of 0, right? Give us a function value of 0. Means it looks something like this. Now we can see when x is 3, I have 0 times doesn't matter, gives me the function being 0. So that's actually how we usually start these questions. We test possible zeros, right? We look for factors of the constant term, and then we put them into the function to see if they give us 0 out, because that tells us they would have to be a factor, okay? That can also make use of the remainder theorem / factor theorem, right? That just says if x minus a is a factor, then the remainder should be 0. When you divide something by a factor, you get a remainder of 0, right? 2 is a factor of 6. 6 divided by 2 is 3, remainder 0, right? 4 is not a factor of 6, so 6 divided by 4 is 1, remainder 2, right? We get a remainder of 0 when something is a factor, which makes sense because if it's a factor, it means the thing is evenly divisible by it, right? So if x minus a is a factor, then we should get a remainder of 0. And we can find a remainder by plugging a in to the original function, right? So this is just the remainder theorem and the factor theorem rolled into one, because it tells us that we can find the remainder for any division by an x minus a by doing p of a, and that will tell me the remainder. And then if we combine that with the factor theorem, that the remainder should be 0 if this is a factor, well then we just want our remainder to be 0. So using the remainder theorem, p of a is the remainder, and the factor theorem, the remainder should be 0, we would test. Now all of that we don't need to do here. Normally we have to figure this out on our own. We'd have to start testing this to see if we can find a factor, right? Find a 0 and therefore a factor. But here, they've actually just given us that x minus 3 is a factor because they told us that x equals 3 is a 0. So now this question basically just becomes, let's find that other factor, right? Find this part, some other factor. We can actually already figure out that, like, look, right? X plus a times some other factor. So we can figure out, they're being a little tricky here, but we know x minus 3 is a factor. So that's this part. So we can think about, what does that mean a is, the way they've written it here? How do we make that look like x minus 3? Well, a would have to be negative 3. So we have x minus 3. Okay. Anyway, if I told you that 2 was a factor of 6, and I asked you to find another factor, right? Pretend you didn't know much about the number 6, you would say, well, if 2 is one factor, that just means 2 times something must equal 6, right? So you could divide both sides by 2 to figure out that the other factor is 6 over 2 or 3, right? We're going to apply the same logic here with the polynomial. We know that x minus 3 times something equals p of x. So let's divide p of x by the factor we do know. If I divide both sides by x minus 3, I'll figure out the other factor. And we have a nice simple process for dividing a polynomial by a binomial. That is our synthetic division. So remember, we put the a value here to represent that we're dividing by it. X minus a here, we would have x minus 3. So positive 3 is our 0. Right? Positive 3 is our 0. That's what goes there. And then we're going to put in here just the coefficients of the polynomial we're dividing by. So all we're doing is we're dividing this polynomial by x minus 3, okay, to figure out what this other factor must be. So the coefficients are 3, negative 2, negative 19, negative 6. Synthetic division is a quick way of dividing p of x by an x minus a. So that's what we're doing here. We're just doing division. I know it looks a little weird. It's based on an algorithm that's proven, but, you know, in the interest of the time on this test question, we'll just go ahead and use it. So we bring down the 3, bring down the first number. That's always our first step. Then we multiply these. So 3 times 3 gives me 9, and 9 goes here. Okay, and then I just add down the column. So negative 2 plus 9 is 7. And then I just repeat. So 3 times 7 is 21. Now goes up here. Oops, wrong color. 21. I add down the column. So negative 19 plus 21 is positive 2. And 3 times 2 is 6. And this is a good sign. Negative 6 plus 6 is 0. Remember, when we divide something by a factor, the remainder should be 0, right? Again, 2 is a factor of 12. So 12 divided by 2 is just 6. No remainder, right? 5 is not a factor of 12. So 12 divided by 5 is 2, remainder 2. Because 5 goes into 12 twice, but then you have a remainder of 2. Right? Again, so this is a good sign. We knew we were dividing by a factor, we should be hoping to get a remainder of 0 here. If you know you're dividing by a factor and you don't get a remainder of 0, that's not a good sign, right? But again, only if you know that this is a factor. If this wasn't a factor, it's totally normal to get a non-zero remainder. Okay, so now what do these numbers mean? They mean the same thing they meant here. So starting from the remainder, we've then got our constant. So this is a polynomial where the constant term is 2. Then it just goes up in powers of x. So we've got a 7x and then an 3x squared, right? If there was another one here, it would be the x cubed, okay? But it looks like our polynomial, our other factor polynomial is 3x squared plus 7x plus 2. Now, normally we would continue on and see if we could factor that at all, but this question actually just asked us what is, if we get it to the stage where we have a quadratic factor and a linear factor, well, we've done that, right? We know then that the other factor, this stuff here, is 3x squared plus 7x plus 2. So all this means is that p of x can be rewritten in factored form as, or at least partially factored. I'm not sure if we could factor that further or not. But we've got x minus 3 times 3x squared plus 7x plus 2. That's p of x written as the product of a linear factor and a quadratic factor. Linear in red, quadratic in green, right? Could always double check your work too if you wanted by actually multiplying it out, right? Do x times 3x squared, x times 7x, x times 2, and then repeat with negative 3 for each term, and make sure that you really do get p of x. Because if these are factors of p of x, that when we multiply them together, it should give us p of x. Spoiler, it will give you p of x back because we did do this correctly. So let's just make sure we answer the question correctly. We want to know what the value of b is. So what goes in b's place now that we've got our answer? Well, looks like it's a 7. 7 is in the spot. So 7, and that means our answer is B. Only B has both A and B values correct. So for number 11, we would bubble in B. Okay, let's take a look at number 12. A particular polynomial function has the following characteristics. So it has a factor of x plus 2 with multiplicity 3. So that means, again, multiplicity means it's really, we've got x plus 2 cubed, or x plus 2, x plus 2, x plus 2. Okay, that's what that multiplicity part means. So that's part of the equation for the polynomial. It has a y-intercept of negative 24, right? Because it's saying p of 0. So when x is 0, y is negative 24. Well, that's just where the y-intercept is. And it has a minimum value of negative 66. Okay, let's read this first. So for the polynomial function described above, the minimum possible degree is blank, and our options are 4 and 5, and the leading coefficient is blank. Okay, so this is actually one of those ones where they kind of gave us some information I don't think we need. Maybe it doesn't hurt to know, but I don't think they needed to tell us this. We'll get into why here. Okay, but let's just think about this. So the minimum possible degree. Remember, for a polynomial function, what degree decides, I mean, obviously it decides the behavior of the graph overall, but one of the key things that it decides is whether it's odd or even will determine what the end behavior is, whether the arms go in the same direction or the opposite direction as x goes to infinity or negative infinity. So remember, for even degree functions, I just drew this out ahead of time to talk about it. For even degree functions, both arms go in the same direction, meaning that as x goes to negative infinity or positive infinity, both of the arms either go up or they both go down. Okay, even doesn't tell us if they go up or down, but it tells us they will both go up or they will both go down. Okay. Odd degree, one arm goes up, one arm goes down. Again, doesn't tell us which necessarily. To do that, we have to look at the leading coefficient, which we'll talk about. But it does tell us that they do the opposite thing, which actually makes a ton of sense because for even degree, it doesn't matter if x is going to negative infinity or positive infinity. Because we're raising it to an even power, it will go off with the same sign, right? So for example, when I have a negative 2, if I square it, I get positive 4, right? If I have a 2 and I square it, I get a positive 4. And same goes if I have, negative 2 squared, that gives me negative 4, or negative 2 squared. Negative 2 squared is positive 4. Make it negative, you get negative 4. And this is true for if we have, negative 2 to the power of 4 or 2 to the power of 4, because it's an even number of multiplications. So whether it's negative or positive, it doesn't end up mattering for what the sign of the result is. They have the same sign as x goes to negative infinity or positive infinity, right? Negative 2 times negative 2 times negative 2 times negative 2. Well, negative 2 times negative 2 is positive 4, times negative 2 is negative 8, times negative 2 again, though, is positive 16. So that's why the arms do the same thing. As x goes to negative infinity or positive infinity, if we're raising that to an even power, it ends up doing the same thing. And then it's the opposite reasoning, opposite result for odd degree. Well, same reasoning, I guess, but opposite result for odd degree. If I have negative 2 cubed, I get negative 8. Negative 2 times negative 2 is positive 4, times negative 2 again, though, is negative 8, right? But positive 2 cubed, I get a positive 8. So as x goes off to positive infinity or negative infinity for an odd degree, I really do get opposite signed answers for negative x's versus positive x's. So again, I don't know which way it's going, where it goes up to positive infinity or down to negative infinity, but I know it does the opposite for when x is negative infinity and when x is going to positive infinity. Okay, so long story short, right? Even degree, the arms do the same thing. Odd degree, the arms do the opposite thing. Why am I bringing this up? Well, we know that this has a minimum value. It has a minimum. So look at the odd degree ones. Do those have a minimum or a maximum for that matter? Right? No, they don't. Why? On the y-axis, we're going either down forever if we look this way or up forever. There's no min. This is headed down to negative infinity. No min here either. It's headed down to negative infinity. The only way to get a minimum and or a maximum is to have even degree, right? Because then the arms really they reach a lowest point, but they're both going up forever. So there's some minimum value they hit that they never go below. Or if it opens downwards like this, there's some maximum value that they hit and never go below. So that tells me this has to have an even degree. It must have an even degree. Okay, so that doesn't necessarily it helps us think, okay, we're probably thinking A or B already. We know it has to have an even degree. It did mention the minimum possible degree. So the lowest the degree could possibly be, okay? Let's think about this though. We know that it has a factor of x plus 2 with a multiplicity of 3. So you might be wondering, why didn't they give us 3 as an option here, right? If we didn't think about this, our gut might have told us that the minimum degree was 3. But this tells us that it can't actually be 3. It would have an odd degree. It wouldn't have a minimum value. So we know that this gives us a degree of 3 all on its own, but that means this can't be the only factor, right? Yes, there's a factor of x plus 2 with a multiplicity of 3, but that's not the only factor, obviously. Otherwise, we couldn't have a minimum value because we wouldn't have an even degree if the degree were 3, right? So there's at least one other factor there that gives us an even degree. Maybe there's 2 other factors that gives us a degree of 6, or even 4 other factors that give us a degree of 8, okay? But the minimum must be 4 because we know it's at least 3, but we know it's even. So at least 3, but even. The only number that fits that, or the lowest number that fits that, is 4, right? It's at least 3, and it's even, 4. Now, for the leading coefficient, this is what I mentioned earlier, okay? For a leading coefficient, remember, a positive leading coefficient will make the right arm go downward. Makes sense, because if we have a positive... Sorry, I said that backwards. A positive leading coefficient will make the right arm go upwards, I meant to say, okay? Which makes sense because as x goes to positive infinity, that's just thinking about the right arm here, as x goes to positive infinity, well, if there's a positive leading coefficient there, then the biggest term, the leading term, is just getting to be a bigger and bigger positive number, right? If I have, 3 times x squared, as x gets to be a bigger and bigger and bigger positive number, then multiplying it by positive 3 just allows it to continue getting bigger and bigger and more positive, right? So as x goes to positive infinity, this will go to positive infinity, and therefore our function goes to positive infinity. Versus if I had negative 3x squared, so if I have a negative leading coefficient, we say that the right arm goes downwards, okay? Again, makes sense as x goes to positive infinity to think about the right arm. X squared will just be a positive number, and then a positive number times a negative is negative. So as x goes to positive infinity, this gets bigger and bigger and bigger, but we're multiplying it by a negative, so it's becoming a bigger and bigger negative number. So thinking about that then lets us take a look and decide what fits. We know it's an even degree, but we know it has a minimum value. So we need both arms to go up, yes, to get a minimum at all, okay, or a maximum at all. Well, no, I guess both arms go up to get a minimum, okay? And we need our right arm to be going upwards to make both arms be going upwards, because that's how we get a min. Both arms need to go up. So both arms need to do the same thing. That told us even, and they need to go up tells us that we get a minimum here, right? We need a positive leading coefficient to make the right arm go up, and we need the degree to be even so that the left arm also goes up and we get a minimum there. So we need a positive leading coefficient, option A. So 14 is A. No, that's not 14, that's 12. 12 is A. All right. Taking a look at this one here, we're given a graph of a polynomial function, told that it has integral x and y intercepts. That just means they're integers. So like this really is 8, it's not 8.1 or something. Okay, the equation of the function can be written in the form p of x equals ax to the fourth plus bx cubed plus cx squared plus dx plus e, where a, b, c, d, and e are elements of the integers. So all of those are just integers. There's no decimals, no fractions to worry about. All right, and we are trying to find what are just a and e. So we don't have to find the whole function, just a and e. Okay, we might end up finding the whole function though as a result of this. Let's just take a look though. Well, e is actually going to be pretty quick and easy because that's our constant term, which you might remember is the y-intercept, but you don't have to memorize that. It actually makes a ton of sense. What's x at the y-intercept? X is always 0 at the y-intercept. That's why it's a y-intercept. The y-axis is at x equals 0. So look, if I put in 0 for x, this is 0. I have 0 plus, well, 0 plus 0 plus 0 plus e. So p of 0, in other words, the y-intercept of this p of x is just going to be e. So the y-intercept is the constant term e. So right off the bat, e is just 8. That's our y-intercept. We can see when x is 0, y is 8. When x is 0, p of x is e. So e is 8. Okay, now a might take a little bit more work. Let's just work out what we can tell about this function. Well, we know it's a degree of 4, right? It's a degree of 4. And the other key piece of information we can see here is that it has 2 x-intercepts. Now at both x-intercepts, it, bounces. It doesn't cross. So these x-intercepts must have even multiplicity, right? Do you remember that? They must have an even multiplicity, meaning that they show up in the equation twice, so to speak. Okay, the associated factors show up twice. So I'll explain why that makes sense a little bit here. Let's just start writing out what p of x could be in factored form though, okay? Because I know right away that it's got a 0 of -1, which tells me that it contains a factor of x plus 1, right? If x were -1, this factor becomes 0, and therefore p of x becomes 0, right? Which we can see it does. When x is -1, the value of p is 0. Same thing here, except this associated factor is x minus 2. If I put in a 2 for x, I obviously get 0 for my function, so that can only be possible if this is our, factors. 0 times x plus 1 would be 0, sure enough, and 0 times x minus 2 would be 0, sure enough, right? If x were -1, this is 0. Okay, now, That's not quite it, though, because we can see they have a multiplicity of 2. It is tangent to the x-axis at those x-intercepts. It does not cross. The sign of y does not actually change. That's only possible if these have an even multiplicity. But how do I know if the multiplicity is 2 or 4 or 6 or 8? Because those are all even. Well, if they both have to be even and the total degree is 4, that only leaves us with one option for each of these, right? They both have to be 2. Otherwise, how could the degree be 4 and both of them be even, right? If this were 2 and this were 4, my degree would be 6. If this were 2 and this were 8, my degree would be 10, right? So it has to be 2 and 2 to give us a total degree of 4 and still make these both even, right? This can't be 1. We know it's not an odd multiplicity or it would cross. Now again, just a quick refresher of why does it make sense that we have an even exponent on this 0 if it touches but doesn't cross? Well, because it has to do with what we were talking about in this question for even powers and what those do to positive and negative numbers, right? So on either side of this 0, we're squaring. So the sign of y won't actually change. If we square a negative, square a positive, we can see, for example, when x is less than -1, this becomes a negative factor, right? -2 plus 1 is -1. But we're squaring it, so we should still actually get the same sign for y, right? Versus when x is on the other side, let's say x is 0, if x is 0 and therefore greater than -1, this is a positive factor. 0 plus 1 is +1. And squaring a positive also gives us a positive. So on either side of our 0 here, because we have an even multiplicity, the sign of overall what this becomes doesn't change. That's only possible with an even exponent. If it were an odd exponent, right, cubing -1 and cubing +1 does give us a different sign. So that's why we know this has to have even multiplicity. And since the degree is 4, they must both have 2. All right, now I've actually left something out of this equation, and it's the most important thing because it's what we're trying to find. And that is, all of this would still be true, right? Everything I've said so far would still be true if there was a 2 here, or a 3 here, or a 5 here, right? So notice that doesn't change anything we said. Would the function still be 0 at -1 and at 2 if there were a 5 here? Yeah, it would, right? Or if there were a 3 here, or a 2 here, or a 1 here. So there could be some number there that we don't know what it is. So we say it's a. We leave in a for now, and then we'll figure out what a could be. Now, to figure out what a could be, we can just use any point that's on our graph, because again, an equation shows us, or a graph shows us rather, every point that satisfies our equation. If a point is on this graph, it means it makes this equation true. Now, it's up to us. We could pick any point. The only point that won't work is an x-intercept, because at an x-intercept, all we'll end up doing is proving that 0 equals 0, which is true, but it won't help us find a. What I mean by that is, like, if we put in -1 for x and say, okay, when x is -1, y is 0, this side will be 0, but so will this side. -1 plus 1 is 0. So we zero out our a, and it doesn't help us find it, right? So it's true that 0 equals 0, but it's not going to help us find a. We can pick any point we want. Often the y-intercept is a nice, easy point to use, though, because it's often pointed out nicely on the graph like it was here. And the other reason it's really nice to use is that at the y-intercept, x is 0. So we can just put zeros in here, and that makes the math pretty quick and easy. Just be aware, if the y-intercept isn't a nice, easy number to see, you don't have to use the y-intercept. If there was, for example, if this one was nice and easy to see, we could use that one, right? The y-intercept is often nice to use, but sometimes if it's like one you're going to have to estimate, it's not really worth it, and you just find one where you don't have to estimate. But we don't have that problem here, so I'm going to use the y-intercept to find the value of a. So at the y-intercept, we know that the function is equal to 8, right? We can see that here. So 8 is equal to a times x is 0 at the y-intercept. So putting in 0 for x, that just means 8 equals a times 1 squared times -2 squared. So 8 equals a times 1 times 4 Or 8 equals 4a, divide both sides by 4, and we get that a must be 2. So a is 2. And there we go. Kind of checks out, right? It's almost like it's been, well, it's not almost like, it's like we took x plus 1 squared, x minus 2 squared, and vertically stretched it by a factor of 2, right? We can quickly check. 0 plus 1, so 1 squared. 0 minus 2, so negative 2 squared. So 1 squared times, well, 1 times 4. We would expect our y-intercept to be at 4 for just this stuff, but it's at 8. So it's been vertically stretched by a factor of 2. Is just another way to look at it. So our numerical response for number 4 would be, careful to follow the order, right? A first, then E, A and E respectively. So we do need to say 2, 8, not 8, 2, because our A was 2 and our E was 8. Whoops, it's for number 4 though. And again, start in the first box. If you don't need those, that's okay, right? But start in the first box always. So 2, 8. All right, so here we are given a graph of y equals f of x, and then we are asked, well, we're told that we're going to draw y equals the square root of f of x. So we're going to take the square root of this function. Remember, the value of the function, those are the outputs, right? The function, like when I say f of x equals x squared, for example, the value of the function is the value of x squared. It's the y values, right? What is x squared equal to? It's the y. So when we take the square root of f of x, we're taking the square root of the whole equation, or we're taking the square root of the outputs it gives, okay? So the graph of the function y equals root f of x will have a domain of blank, and there are blank invariant points associated with this transformation. Okay, well, let's start out with the domain, two-parter, right? We got a two-part domain here, or a two-part question, sorry. Domain and then invariant points. Well, what can we not take the square root of? We cannot take the square root of a negative number, right? It doesn't make sense because, again, -1, the square root, I'll start there. The square root is saying what number could we multiply by itself to give us the radicand being the thing in there. That's why the square root of 4 is 2, because 2 times 2 is 2. Or that's not true. 2 times 2 is 4, obviously, right? That's why the square root of 4 is 2. What number can we multiply by itself and get 4? 2, right? There's actually another answer, though. The square root of 4 could also be -2, because -2 times -2 is +4. Now, no matter what, again, what number can we multiply by itself and get this as an answer? So if we think about this, a positive times a positive times itself, let's say, is going to be a positive. A negative times a negative, so a negative times itself, is also going to be a positive, right? The only way to get a negative is to do a positive times a negative, right? But then we're not multiplying something by itself. So the only thing we can take a square root of is a positive number, because nothing times itself will ever be negative. So that's why we have the restriction that if we're taking the square root of something, we can't take the square root of a negative number. It doesn't make any sense because no number times itself could ever be negative, right? Negative times negative, positive, positive times positive, positive. So all of that to say, if we're going to take the square root of the y values here, we can only take the square root of the positive y values. That means these parts we cannot take the square root of. Y is negative here, right? Y is negative here. Y less than 0 here. Or really, I mean, I could say f of x, the original function, is less than 0 here. So root f of x is undefined here because we'd be trying to take the square root of negative numbers if we tried to take the square root of these y values. So what does that mean for our domain of y equals root f of x? Well, it's not between negative a and b, right? We can only take the square root of positive numbers. So we can only take the square root of these y values, and these y values only happen when x is greater than or equal to b or less than or equal to negative a. Otherwise, y is negative. Everywhere between negative a and b is negative. So we're looking for the domain where x is less than negative a or greater than b. Looks like that is either a or b. so we can cross out C and D. Right? These are the exact opposite of what we wanted. This is where root f of x would be undefined. This is the opposite of its domain. This is what we would need to leave out of its domain. Okay, now the other piece of this is the invariant points. Remember, invariant point means it doesn't change when we do some transformation. The transformation that we're doing here is taking the square root. So we got to think, what type of number wouldn't change if I take its square root? There's actually only two numbers that do that. Only two numbers are their own square root. So if we think about it, what numbers can we multiply them by themselves and still get the same answer? Or still get them, I should say, right? Well, it's 0, right? The square root of 0 is 0, because only 0 times 0 will give me 0, right? Any other number times itself could never equal 0, right? And 1. 1 is its own square root, because only 1 times 1 equals 1, right? No other number times itself will ever equal 1. So that just means, again, we're taking the square root of the y values. So we need to see how many places here does y equal 0 or 1. 0 we can see right off the bat. 2 places. There are 2 places where y equals 0, right? So invariant wherever f of x equals 0 or 1. So I can see 2 places where it equals 0. So right off the bat, we've got two invariant points. Y is 0 here, and the square root of 0 will still be 0. We're not taking the square root of the x values. We're taking the square root of the function, the y values. Okay? And then, where is it 1? I mean, they haven't labeled 1 on our y-axis here or anything, but you can tell that no matter what, it's going up forever. They've got the arrows, so no matter where 1 actually lies on this graph, let's say it's there, it's going to have to cross it twice as well. So 2 invariant points from where y was originally 0, 2 invariant points from where y was originally 1, or f of x was originally 1. So when we take the square root, there are 2 plus 2, or 4 points that will not change. 4 places where y equals 0 or 1 on the original function. So number 13 should be A. All right, numerical response 5 here. The vertical asymptote of the graph of this rational function is defined by the equation x equals k, and we want to know what is the value of k to the nearest hundredth. Okay, so essentially, we got to find the vertical asymptote of this graph. Okay, so remember, a vertical asymptote is a x value, because it's vertical, so it's talking about an x value. So if this is my, if I have a vertical asymptote here, it's the value of x that my graph will approach but never reach. So I don't know, just making something up. Maybe it looks something like that. It gets closer and closer to that x value, but it never actually reaches it. So it's not allowed to take on that x value. And for these rational ones, that's usually because it would have us dividing by 0. In fact, that's pretty much always what it is for most asymptotes, vertical asymptotes anyway, but definitely for rational functions. That's where we get those vertical asymptotes. A value of x that it can be as close as we want it to be, but it can't ever actually take it on, because then we'd be dividing by 0. As always, when working with a rational function, it's going to be way easier to think about, way easier to look at, way easier to pick stuff out if we factor everything completely. So before we start talking too much about, which ones are asymptote, let's factor this completely. Okay, so I'm going to factor the numerator and I'm going to factor the denominator. Just break it up into two steps in your mind if you like, right? Factor the numerator. So let's do the numerator first. Now the numerator is just a quadratic with an a value of 1. A I'm referring to there as the leading coefficient. So we can actually just use good old product sum here, right? I mean, we could use decomposition, but that's a little bit more work. Let's just use product sum. So I'm looking for two numbers that multiply to c, the constant. So something times something needs to equal -10, and add to the b value, the x coefficient. So something plus something has to equal -3. So you can sit here and, think about it. If you get really stuck, don't forget, you can always just factor out the 10, right? 10 could be 5 times 2 or 10 times 1. We actually got lucky right off the bat there. 5 times 2, hey, that'll work, right? We could make that work, because if I do -5 and +2, then -5 times 2 is -10, and -5 plus 2 is -3. So that tells me for product sum, we're actually, it's factored. Our numerator is, we've now got y equals, the two numbers are negative 5 and positive 2, right? So that means the two factors are x minus 5 and x plus 2. Okay, if we really wanted, we could always double check our work by foiling this back out, multiplying it all out, right, and make sure we really do get this. Interest of time, I won't do that, but I can promise that is what you get. Okie doke, numerator's been factored. Let's factor the denominator now. This is going to be a little bit tougher because our a value is not 1, so we are going to have to use that decomposition method, okay, or AC method, some of your teachers might have called it, right? So now we're looking for two numbers that multiply to, be careful, not multiply to negative 18. They need to multiply to AC, right? 4 times negative 18, which I believe is negative 54. No, negative 72. Sorry, that wasn't correct math at all. Negative 72. Okay, so to do the denominator now, I'll just, move down here, or maybe move over here. For my denominator, I need two numbers that multiply to negative 72, and adding is still the same. We need to add to negative 1, right? Negative 1 is the coefficient there, so negative 1. All right, well, 72, 9 times 8, those are separated by 1, so we could probably make a negative 1 by adding them if I made one negative. Well, one of them negative, I should say. So how about I make negative 9 and positive 8? That would work, right? Negative 9 times 8 is negative 72. Negative 9 plus 8 is negative 1. So now for decomposition, right, we're not done. We have to do the decomposition part. So I'm going to rewrite. What we do here is we rewrite this as 4x squared. We decompose the x term into these two as the coefficients. So what I mean by that is I'm going to rewrite negative x as negative 9x plus 8x. And you can see why that's okay, because negative 9x plus 8x is still just negative x. I've decomposed it into these two terms though, okay? Why would we do that? Because it lets us continue factoring. We're now going to group these two, and factor those two groups separately. Just a quick reminder, in case it's been a while, we don't ever want to have a negative, well, I shouldn't say that. If we have a negative here in the middle, we've got to be careful, because in our next step, what I'm going to do, like I said, I'm going to group these two, and I'm going to group these two. So if there were a minus there, I'm safe here, but if I had maybe wrote the negative x there, I'd need to be careful, because then what I would be saying, if I had a minus here, I'd now be subtracting both of these terms. So I'd actually change the sign on this just by putting brackets around it. I would have negative, like subtracting negative 18, which is adding 18. And we never wanted to do that. We were always subtracting 18. So just a word of caution, don't forget that if there must be a minus there, then we just rewrite it to get around this problem. Like let's just say this were minus 8x, I would just rewrite it as plus negative 8x. Because then when I do group it, I don't have any problems. I haven't changed the sign of anything, right? Still a negative 8x, still a negative 18. Now again, that's not what we had. That negative 8x is just a hypothetical. Okay, but I just wanted to give a quick note on that in case it's been a while since you factored by decomposition, which I guess it shouldn't be because we've been doing it throughout Math 30, but you never know. All right, so now I factor these two groups individually. So the greatest common factor of these first two is, I think, just x. That's the biggest thing that's divisible by both 4x squared and negative 9x. So if I factor out an x here, 4x squared divided by x is just 4x, and negative 9x divided by x is just negative 9. Over here, this I can factor a little bit more out of. These are both divisible by 2. I guess that's not that much more. Both divisible by 2, so I'll be left with 4x minus 9, dividing both of those by 2. And now the nice thing about decomposition is there's a natural step where we can kind of check that we're doing something right, because these two should always be the same if we've done it correctly, right? And that's actually crucial for moving forwards, because now look, for the blue stuff, right, I have x times 4x minus 9 plus 2 times 4x minus 9. So 4x minus 9 is a common factor to these two terms. I can pull it out as a common factor. And if I divide x times 4x minus 9 by 4x minus 9, I'm just left with the x. If I divide 2 times 4x minus 9 by 4x minus 9, again, just pulling 4x minus 9 out as a common factor, I'm just left with 2 from that group. And there we go. We factored it by decomposition. Okay, so that means, remember, all of this was just to factor the denominator. So my denominator is 4x minus 9 times x plus 2. Now we can actually get into the math 30 part of this question, which was just, where do we have a vertical asymptote? So we've got a couple places in our denominator where we could be dividing by 0, right? I see 2 places. If x were negative 2, we'd be dividing by 0. If x were 9 over 4, we'd be dividing by 0, right? I mean, that's just me solving for when is 4x minus 9 equals 0, when 4x equals 9, so when x equals 9 over 4, okay? With that in mind, though, how do we know which one's the vertical asymptote? Is it x equals negative 2, or is it x equals 9 over 4? Well, remember, the vertical asymptote is like, it's there. It is a major feature of the graph. The graph will approach a vertical asymptote but not reach it, okay? Now, it is still true that x cannot equal negative 2. But notice, if we were to simplify this equation, x plus 2 over x plus 2 is just 1. So we could actually simplify this equation to just be x minus 5 over 4x minus 9. Now, x still cannot be negative 2, because we know this is really our equation, and x being negative 2 would still have us dividing by 0, even if it's possible to simplify and write it without, okay? All this is showing us here is that the graph will look a lot like, in fact, it'll look pretty much identical to, because this factor doesn't do much in the end, it just simplifies out to 1, the graph of y equals this will actually look pretty much identical to the graph of x minus 5 over 4x minus 9, except in one very important place. And that place is when x equals negative 2. X can be negative 2 for this graph, right? But for this graph, x cannot be negative 2. So what we would have is a point of discontinuity. If we were to graph this, we would have a point of discontinuity at x equals negative 2. Meaning that for the most part, yeah, it would look exactly like this graph, except at x equals negative 2, there would be a little hole, a literal point of discontinuity where it's not continuous. So, can x be negative 2? No, it is a non-permissible value. But is it a vertical asymptote? No, it's not like a major feature of the graph that it's going to approach and get closer and closer to, because it does end up just simplifying out. There's a little dot at x equals negative 2, but not an entire vertical asymptote. This one, on the other hand, does not get simplified out. It is, it's going to be a major feature of our graph. It really is governing the behavior of our graph. So our vertical asymptote is at x equals 9 over 4, which to the nearest hundredth, like the question asked for, well, 9 over 4 is just 2.25. So that's to the nearest hundredth. So for numerical response 5, we've got an answer of 2.25. So we would include that decimal, right? For the format they're asking for here, we do need the decimal, so 2.25. All right, number 14 here. The graph of g of x shown below can be represented in the form g of x equals a over x minus b plus c. And then a different function, f of x, can be defined by the equation f of x equals x squared plus 3x minus 4. All right, so careful to note, be important to note that g of x, what we're seeing graphed here, is different than this. This is f of x. Different function. This is totally different information than what the graph is showing us. The domain of the function h of x, and h of x is defined as g of f of x. This is a composition, right? I often like to rewrite these. That open circle does mean g of f per Personally, I prefer this. It just makes it a little clearer to me that what we're doing is we're taking f of x and putting it into g of x. Okay. So this function will have the restriction, what can x not equal? So what is x not allowed to equal for putting it into h of x? Okay, well, to think about this, right, really what we're looking for, we're taking g of something, okay? And if we look at the graph for g of, stuff, g of x, okay, we can see that there's a vertical asymptote at x equals 6. Vertical asymptote, a value of x that the function cannot take on. It can approach it, but it can never be it. So we can see here that our g of x can approach 6, but it looks like it can never be 6, right? It's a rational function, so we can kind of tell that, it must contain a factor of x minus 6 in its denominator, and that's why x can be very close to 6. It can be 6.0001, because then we're not dividing by 0, but it can't be 6, because then we would be dividing by 0. So let's think about that then. We know g of x, we're not allowed to make the input into g be 6. We're not allowed to put 6 into g of x as x. But we're not putting x's into g of x, we're putting f of x into g of x. But that doesn't change the fact that we can't input 6 into g, right? We can see that. We're not allowed to input 6. So really then what this question becomes is, where does f of x equal 6? Because if f of x equals 6, then I'm going to be putting in 6 to g when I do h of x, right? H of x is not g of x or f of x, it's g of f of x. So the restrictions on h of x, I need to find what values of x are going to make this safe, right? And any value of x that makes f of x 6 is not safe. It might be okay to make f of x equal 6. In fact, it definitely is okay to make f of x equal 6 on its own, but it's not okay to make f of x 6 if I'm going to put f of x into g, because I can't put 6 into g. So really this question just becomes, right, need to find, so cannot input 6 into g, right? We are inputting f to g. So we need to find x's that make f of x equal 6. Because again, we're really not putting x's into g here. We're putting f of x's. We're putting x's into f, and then we're putting those f's into g. So the restrictions on x are the ones that are going to make f of x equal 6. So when does f of x equal 6? Well, f of x equals x squared plus 3x minus 4. So 6 equals x squared plus 3x minus 4 will let us solve. If we can solve for what x would be here, we can solve for the values of x that make f of x equal 6. And now we're back in Math 20, right? I just need to solve this quadratic equation. So as we would normally do, let's get everything to one side so that we can focus on factoring and figuring out how to make the factors equal 0. So I'll subtract 6 from both sides. 0 equals x squared plus 3x. Negative 4 minus 6 is negative 10. Just going to, negative 4 minus 6 is negative 10. Okay. And now, if we can factor this, we'll have two factors multiplied together, and we know it equals 0. So it'll be pretty easy to solve for what values of x would make each factor equal 0. So I need two numbers that multiply to negative 10 and add to 3. Could list out the factors of 10 if we got stuck, but I'm thinking 5 and 2, right? 5 and 2 could make 3 if one of them were negative. And in this case, I think 5 and negative 2, right? 5 times negative 2 is negative 10. 5 plus negative 2 is positive 3. So our two factors are just x plus 5 and x minus 2. We're almost there, but this is just saying now, okay, so this equation is, true. What values of x would make it true, right? Well, something times something equals 0 is only possible if one of the things is 0, right? If either of these is 0. So x plus 5 equals 0 if x equals negative 5. There's one solution, right? If x were negative 5, yeah, this would work. 0 would equal 0. Same here, x minus 2 equals 0 if x equals 2. So really, I'm saying equals, but that means x cannot equal those. X cannot equal negative 5, x cannot equal 2, because again, that would make, we've just shown that that would make f of x equal 6. And f of x cannot equal 6 if we're going to put it into g, because we can see that g has a non-permissible value of x being 6, because there's a vertical asymptote there. So our answer here, negative 5 and 2, looks like option D. 14 is D. All right, so number 15 here, we've got a carousel, right? Like a merry-go-round, which is just, it spins in a circle, okay? So we've got a circular carousel with a diameter, careful, diameter of 22 meters. An adult is standing on the outer edge of the spinning carousel. Okay, what do we want to know? We want to know the central angle that's formed when the adult travels 10 meters. To the nearest degree. So if we think about that, if I'm just going to do a view from above, what does this situation look like from above? Well, the carousel would look like that from above, right? It's just a circle. If our adult is standing at the edge of it, we want to know what angle has it moved through by the time our adult, now as they move, they're going to follow the outer edge of the circle, right? They're going to move like this. So we want to know if they've traveled 10 meters, if that's the actual distance they've moved through as they make their way around the edge of the circle like this, right? We want to know what is the central angle formed. In other words, what is this angle here? What angle have they been moved through relative to the center of the circle if they've actually traveled a distance of 10 meters around the circle's edge? Now, in order to figure that out, we do have, right, we have our, formula, if you want to call it that, but really it's not that much of a formula as it kind of is the definition of a radian, okay? So remember, 1 radian, what that is it's the angle that subtends an arc length of 1 radius. So if this is 1 radius, let's just give it a number so we can think about it. Let's say this circle has a radius of 15 centimeters. Okay, again, just kind of making that up. Then this angle is 1 radian if this arc is also 15 centimeters, right? That's a radius of 15. That's a radius of 15. I haven't drawn it very to scale. That looks more like closer to 90 than to 1 radian. But still, 90 degrees, sorry, than 1 radian, or pi over 2 radians as opposed to 1 radian. But this is the idea of what a radian is, right? This is 1 radian if it's the angle that we kind of need to move through to trace out a distance that's 1 radius along the circle's circumference here, okay? So in general, it just says if this is a radius, this is a radius, and if this is a radius, then that means this angle here is 1 radian, right? That's the definition of the radian. Anyway, we don't need to fully understand that to use the formula, but it helps us understand the formula a little bit more. So let's actually take a look here. And from that definition, you can see, right, from that definition I just had there where I was looking at, what is a radian, you can see that this equation only makes sense if our angle is in radians. So to use this equation, remember, we cannot use degrees. We have to use radians for this equation to even make sense at all, right? We can see it makes sense because look, 1 radian, if I've gone an arc length of 1 radius, divide that by the radius, I get 1 radian, right? 15 centimeters over a radius of 15 centimeters. I've gone through 1 radian using this example here, okay? This stops making sense if we used 360 degrees, right? That's why, again, there are 2 pi radians in a full circle, because there are 2 pi, a circumference of a circle, the full circle is just 2 pi times the radius. So 2 pi radii fit into a full circle, meaning that we need to do 2 pi radians to get all the way around the circle if we're thinking about the angle. Okay, so again, just really emphasizing this formula only makes sense if our angle is in radians. Now, the other piece of the puzzle here is that it has a diameter of 22 meters. This is not diameter in our formula, it is radius. So remember, diameter is the total distance across the whole circle. So what's the radius? It's half. It's half of the diameter, right? It's just halfway across. So our radius will just be 22 over 11. No, 20, I was jumping ahead there. You can probably see where I got that number. 22 over 2, sorry, or 11 meters. So that's our radius. Okay, so now we're ready to find the angle in radians. Our angle in radians will be equal to the arc length. That's how far the adult has traveled, 10 meters, over the radius, 11 meters, which gives us 10 over 11 tells us that our angle is about 0.909091 radians. Okay, that will be in radians every time. So again, we're not going to round that. Okay, don't round in your steps as you go, because over rounding can end up changing your final answer, right? Especially on like a numerical response. I would never ever want to round this to like 0.9, because what if that changes my final answer by enough where I'm off by, you know, a 1/100th of a degree or something, and then my numerical response will be wrong because I've over rounded. So just a reminder, it doesn't matter as much for this one. Multiple choice will probably be close enough, but still, right? Don't round until you're doing your final step, actually getting your final answer. So now what's left is just to convert this into degrees, because all the options are in degrees and we had to do to the nearest degree. So if the angle we know is 0.909091 radians, to convert that to degrees, well, there's 180 degrees in every pi radians, right? 180 degrees is the same thing as pi. So really, I'm just multiplying it by 1, because 180 degrees is the same thing as pi radians. They're just measured differently. So I'm not changing what this number means, because I'm really just multiplying it by 1. I'm just changing how it's represented. So I need to take 0.90901, multiply it by 180, and then divide by pi, and that's going to give me 52.087 degrees, or to the nearest degree, 52 degrees. So that's going to be C. Apologies if you can hear the sirens that are happening outside my apartment right now, but 15 is C. All right, let's try this one out. So the point T, which has an x value of root 3 over 2, a y value of 1 over 2, is already, I'm kind of thinking special triangles, right? Is the point at the intersection of the unit circle and the terminal arm of the angle theta, drawn in standard position as shown below. All right, well, it's on the unit circle, so that's really good to know. That means our r is 1. Okay, we can still make use of ratios and stuff even if it's not on the unit circle, but nice to know that it is, potentially, if we need that. Let's just read what they're actually asking us to do here. If the angle of rotation is changed to become theta minus 3 pi over 2, then the coordinates of the point where the terminal arm intersects with the unit circle will be, which one of these? Okay, so if we're thinking about this, right, all it's saying is if you took theta and subtracted 3 pi over 2, which, you know, that's 3/4 of a full rotation, 270 degrees if you're a degrees person, okay, where would the new arm now, where would it intersect with the unit circle? So we can kind of picture this a little bit, right? Minus 3 pi over 2, that means, you know, rotate from here 3 pi over 2 in the negative direction, clockwise. So in other words, take this and, you know, 270, 3/4 of a turn. So it's going to look something like this. That's actually a strategy we could kind of employ here to at least eliminate a couple options. Again, we can go through this with, you know, with just solving for the angle and doing it. But, you know, a thing to keep an eye out for here, we're expecting our x value to be negative, our y value to be positive. We're in quadrant 2 here. So we could maybe use that to narrow it down a bit right off the bat. We're probably not expecting A or C, because those have positive x's, negative y's, positive x, negative y, Okay, so something to keep in mind. But let's just go ahead and see if we can, jump into this and start figuring it out. I didn't draw 3 pi over 2 very well, but get the idea, hopefully. Okay, so what is theta, right? I mean, before we start thinking about theta minus 3 pi over 2, we should probably figure out what theta is, right? How are we supposed to subtract 3 pi over 2 if we don't know what it is in the first place? So let's think about finding that, original theta. What is that angle? Well, again, it's on the unit circle. It's on the unit circle. So remember, on the unit circle, r is 1. So we can take advantage of the fact, I mean, if you want to memorize this, you can, right? Helps to know it. I won't deny that. But it makes a lot of sense that this is just cos theta and this is just sine theta, because anywhere on the unit circle, r is 1. That's what makes it the unit circle. It has a radius of 1. Okay? So if we think about that, what is cos of theta? Well, it's, opposite over hypotenuse. But opposite here, opposite to the angle, is just the y coordinate, and hypotenuse is just the radius. Y over r, right? Opposite over hypotenuse. On the unit circle, what did we say? Whoops. I was talking about, I think I said opposite hypotenuse, but I had written cos to begin with. Sorry, that was probably confusing. Sine theta equals opposite over hypotenuse, y over r. Sorry about that, folks. But r on the unit circle is just 1. So y over 1 is just y. So that's why on the unit circle, the y coordinate is just going to be the sine theta, right? Where this intersects with the unit circle, r is 1. So y over r is just y. Sine theta is just y. Same logic goes for cos theta. I'll do it right this time. Cos theta is adjacent, or, this side, x over r. But on the unit circle, r is just 1, so x over 1 is x. So cos theta just equals x, right? So just a reminder of why we can be so sure that this is really just telling us cos theta, and this is really just telling us sine theta. Okay, so with that in mind, we now know, right? We can say that it's on the unit circle, so root 3 over 2, 1 over 2, that's the point they gave us, is really just cos theta sine theta, right? And these are definitely, these numbers are getting me thinking special triangles, right? Root 3s, 2s, 1s, those are all the things we look for if we want to think about a special triangle to save us some time and effort on the calculator, okay? So if cos theta equals root 3 over 2, let's think about what that means we're dealing with in terms of a reference angle and a reference triangle and all that good stuff, right? So adjacent over hypotenuse, or x over r, is apparently root 3 over 2. If I want to figure out what this angle is, we technically already can, right? We know that this is our 30, 60, 90 triangle, right? We can extra confirm sine theta, y over r, or opposite over hypotenuse, is 1 over 2. So this is definitely telling me that this triangle here, this is I remember it as next to the root 3, 3 for root 3, 3 for 30 degrees. We're working in radians here though, so pi over 6 is 30 degrees, right? It's 1/6 of 180, and 180 is pi. So pi over 6 radians is our reference angle here. And again, reminder folks, even if you couldn't fully remember this, I do suggest remembering the 2 special triangles. It's just handy and quick to know them off the bat. But let's say, worst case scenario, you're writing your diploma, you forget one of the special triangles. If you can even they told us this, right? So you could even just use SOHCAHTOA to figure out what that angle should be, right? Root 3 over 2, well, inverse cos of root 3 over 2 will tell us what this angle is, right? Inverse cos of root 3 over 2, try it on your calculator. If you're in degrees, you'll get 30 degrees, right? If you're in radians, you'll get some big long decimal, but I would do it in degrees because then you can just convert to radians and see that, oh, it's just pi over 6, right? 30 degrees is just pi over 6. Anyway, now we know our reference angle is 30 degrees. Now, which quadrant are we in? we're in quadrant 1. So if our reference angle is 30 degrees, if this is 30 degrees, our angle is just 30 degrees, right? In quadrant 1, it's easy to go from reference angle to angle because the reference angle referenced to the x-axis is just our angle of rotation. So theta just equals 30 degrees, right? In quadrant 1, the reference angle is the angle. All right, but we didn't want to do this for theta. We wanted to do it for theta minus 3 pi over 2. So now that we know theta is 30 degrees, oh, I shouldn't be using degrees, should I? I should be using radians. Technically, it's fine to do it all in degrees and then convert to radians at the end, but, you know, let's stick with what they told us here. Never hurts to use radians. Radians are actually very convenient because they're just fractions of a 2 pi, we can think of them as. Okay, so step 2 here now, let's find the new theta after subtracting, like it said, 3 pi over 2, right? Because that's what it said we were going to do. So starting from pi over 6, if we subtract 3 pi over 2, what are we going to get? Well, I mean, we could get a common denominator here if you like. So pi over 6 minus, if I multiply by 3 over 3, that's 9 pi over 6 equals negative 8 pi over 6. So that's like our new angle, right? We're actually trying to figure out what is the point of intersection for this angle's terminal arm with the unit circle, negative 8 pi over 6. So let's just, do what we always do now, figure out what negative 8 pi over 6 actually looks like so that we can get a reference triangle so that we can then find the ratios using that reference triangles. So if we think about it, right, I mean, this is 0. This is, if we're going in the positive direction, it's 3 pi over 2, but we're kind of going in the negative direction. So we could also think of this down here as negative pi over 2, right? That's a rotation of negative 90, negative 90 degrees, negative pi over 2 radians. And this would just be negative pi, right? This would be negative 3 pi over 2. Going all the way around would be negative 2 pi. Just kind of rethinking of those quadrantal angles in terms of the negative version, since we have a negative angle of rotation here, okay? You could also just, add 2 pi to this to make it positive, and then think about the positive if you prefer that, okay? But I'll just stick with the negatives here. I'm going to negative 8 pi over 6. If we want, we could reduce that fraction even to being negative, divide by 2, so negative 4 pi over 3, right? Negative 4/3 of pi, okay? So what does that mean? Well, we're going past pi, right? Pi would be, if we want to think about it in terms of this fraction, negative pi is negative 3 pi over 3, right? Negative 3/3 of pi. Well, we're going past that. We're rotating past negative pi by another third of pi, right? There would be 3/3. There would be 3/3, but we didn't rotate negative 3/3. We rotated negative 4/3. So another third of pi past negative pi. Okay, and again, just to emphasize, we could have also said, I don't want to deal with the negative angle. Let me just add 2 pi to get a positive coterminal angle, right? So this would be negative 4 pi over 3 plus 6 pi over 3 is 2 pi over 3, right? And that's a positive angle that we can use to get the same reference triangle and do all the same trig stuff, right? And we'd get the same result. We're 1/3 going the positive direction, right? 3/3 would be to pi. We're stopping 1/3 of pi short of 3/3 because we're only going 2/3 of pi. So either way, we get the same result. This is pi over 3. This is pi over 3. That's our reference angle. Okay, so again, just 2 ways to do the same thing. If you're comfortable with the negative angle, nothing wrong with rocking with the negative angle. If not, add 2 pi and turn it into a coterminal positive angle. Anyway, I'm just going to get rid of this because it's adding up extra work there. All right, so now here we go. We know that this is the reference triangle we want to kind of be thinking about, right? We want to be thinking about the reference triangle that has a pi over 3, 60 degrees. And again, since we're trying to find the point of intersection with the unit circle, we're kind of just trying to find cos theta and sine theta for that, right? Cos theta, sine theta for this angle here. We can use the reference triangle here to think about it. So a couple things you could do. You could recognize that we're in Q2, so this should be a negative measurement, and this will be a positive measurement, right? A negative x, a positive y, okay? But you could also just, treat it like a regular triangle and then use cast to tell you what should be negative, what should be positive. Both achieve the same result. So this is pi over 3 or 60 degrees. That makes this pi over 6 or 30 degrees. I always remember that the root 3 goes next to the 30. 3 for root 3, 3 for 30. Okay, so root 3, 1, 2. That's our special triangle here. So let's get our ratios so that we can get the cos theta, sine theta, because that will be the x and y coordinate of the intersection of this angle's terminal arm with the unit circle. So cos theta, adjacent over hypotenuse, 1 over 2. Okay, or I'll say cos of our reference angle anyway. We'll have to think about cast to place it in the 4 quadrants. Cos theta is positive 1 over 2. Cos of our sine of our reference angle, sorry, I just did cos. Sine of our reference angle is opposite over hypotenuse, right? Y over r, so root 3 over 2. But we got to be careful, right? We're not actually just dealing with this simple reference triangle. We're dealing with this thing in, 4 quadrants. Or at least, we have to think about which of the 4 quadrants it falls into. So our angle we know is over here. We're in quadrant 2. So using cast here, right? I won't go into a re-explanation of why cos is positive in the 4th quadrant, why they're all positive in the 1st, why only sine is positive in the 2nd, and only tan is positive in the 3rd. But again, you can kind of see the logic, right? Positive x's, positive y's. Negative x is positive y's. Since sine depends on y over r, you can see why sine would be positive here, but cos depends on x over r. You can see why cos would be negative here, right? Because x's are negative. Tan would be negative here because y is positive, but x is negative, so y over x is negative. Anyway, that's where cast comes from. I won't go into the boring details of all of it. Not boring, but I won't go into the details of all of it. So we are in the 2nd quadrant, so sine is positive, cos will be negative, so that tells me that my ratios are really cos of, right, if I want to do cos of negative 4 pi over 3, my new angle, it's actually going to be, well, cos is negative here, so negative 1/2. Sine of negative 4 pi over 3, we're in quadrant 2, so sine should be positive, root 3 over 2. And so remember, any angle intersects with the unit circle at cos theta, y theta, because again, r, the hypotenuse, is just 1 when we're in the unit circle. So this will be negative 1 over 2, root 3 over 2. Or option B. Hey, remember what we said at the beginning? We said we're kind of expecting it to be B or D, because those we knew we were going to be in quadrant 2, right? So we knew we would have a negative x, a positive y. Sure enough, we did. So number 16, B. Alrighty, so here we've got one where the point A, negative 2a, so x value a, y value negative 2a, where a is positive, is the point of intersection between the terminal arm of the angle theta, drawn in standard position, and the unit circle. All right, so another unit circle one, right? Meaning we know that this is cos A and this is sine A, for reasons we kind of went into in the previous question. So the value of A can be written in the form m over root n, where m and n are single-digit whole numbers. So they're not decimals or fractions or whatever. M is just a number, n is just a number. It wants us to figure out what are the values of m and n, respectively. Okie doke. Well, nice that they told us a is greater than 0, because that means a is positive, so the x-coordinate is positive. A is positive, so the y-coordinate is negative, right? It's negative 2 times a positive number, giving us a negative number for the y-coordinate. So that actually kind of tells us right off the bat which quadrant we're in, which is kind of nice to know, I guess, right? Which quadrant has positive x's and negative y's? Quadrant 3. The x's are positive there. The y's are negative. So our angle theta must look something like this, right? Probably not drawn to scale, but the the x coordinate is just a, and the y coordinate is just negative 2a. Okay, so I mean, there's a couple ways we could go at this, but honestly, I think probably the easiest is just to use the Pythagorean theorem, right? Because we know that r, this is on the unit circle. So what's r on the unit circle? It's just 1, right? Again, for a recap of all that unit circle stuff, you might be able to go back to the previous question. I talked about it more there. Okay, but again, that's all the unit circle is, the radius of 1 traced around in a circle. So if we think about this, what we're dealing with is a triangle where, you know, this side is A, this side is, we could even use the negative here if we want, negative 2A, and this side is 1, right? So let's just use the Pythagorean theorem. A squared plus B squared equals C squared, right? C just has to be the hypotenuse, so we'll make A squared plus negative 2A squared, negative 2a squared equal c squared, our hypotenuse squared, so 1 squared. So this just means, I'm just going to drop the color coding now, a squared plus negative 2a squared, that's just negative 2a times negative 2a, that's positive 4a squared, and 1 squared is, of course, just 1. So now I can just combine like terms. A squared plus 4 more a squareds gives me 5a squareds, and that equals 1. Okay, then moving over here, 5a squared equals 1. Divide both sides by 5. To start isolating a, we get that a squared equals 1 over 5, and now square root both sides. Square root both sides. And we get that a is the square root of 1 over 5, but we can just take the square root of 1. That just leaves us with 1, right? 1 is a perfect square. Square root of 1 is just 1. And in our denominator, we still just have square root 5. Now, technically, you're right. We took that square root, so we'd have to consider plus or minus. However, don't forget we're solving for a, and they told us a is positive, so it's just the positive one. We don't need to worry about the negative one. They already told us a was just the positive. So 1 over root 5 is a, meaning that m over root n, right? They told us that it's of the form m over root n. So what goes in m's spot? 1. What goes in n's spot? 5, right? It's 1 over root 5. So m is 1, n is 5. And for numerical response number 6, we would bubble in 1, 5. Again, always start in that first box. If you don't need the boxes that come later, that's fine, right? Just leave them blank, but always start in that first box. We wouldn't want to do this. The machine would mark that as wrong. Alrighty, so 17 here. If secant of theta equals 13 over 12, where, ooh, look at this, 3 pi over 2 is less than or equal to theta, which is less than or equal to 2 pi, we're only in one quadrant here. So that's going to make our lives a little bit easier. We are only looking for the angle in the fourth quadrant. We can kind of already tell because, again, this is 0 or 2 pi if we go all the way around. This is pi over 2, 90 degrees, pi, 180, 3 pi over 2, 270. Okay, so if we're just between, right, the angle being between 3 pi over 2 and 2 pi, we're just in quadrant 4 here. All right, now we want to figure out then, what is the value of cosecant theta? So we know we're in Q4, okay, and we know that secant theta equals 13 over 12. So if secant theta equals 13 over 12, remember secant is just 1 over cos. They're reciprocals of each other. So that means cos theta is just 12 over 13. Not really like mandatory to make that conversion, but I often find cosine and tan easier to think about than secant, cosecant, and tangent. So I might just do that, just to get my bearings here a bit. So if you think about it, we're in the fourth quadrant, Okay, what is cos theta equal to? Adjacent over hypotenuse, or in the case of these, right, x over r. So this just tells me my x coordinate is 12. And the radius here, r, is 13. Right? That is what I got here for my x coordinate, 12 over 13. Now I want to figure out cosecant theta. So I want to figure out cosecant is 1 over sine, right? 1 over sine theta. Well, sine theta is just y over r, right? Opposite over hypotenuse. So if I can figure out sine theta, then it's pretty easy to figure out cosecant theta because it's just r over y, right? I mean, again, technically I don't even need to find sine theta. In fact, I probably won't. I'll just find cosecant theta, but I'm missing a piece of the puzzle to be able to do that. I need to know y. But again, this is actually just a Pythagorean theorem, right? Look, I've made a little right angle triangle here by drawing it out. So a squared plus b squared equals c squared, right? Remember, that c squared needs to be the hypotenuse, right? It doesn't matter what we make a and b, right? We're just adding them anyway. But since that c squared is just isolated on the right side of the equation, or I guess however you write it, but the c squared is isolated, so it is important that this is the hypotenuse. But that just means 12 squared, we need to find y. So 12 squared plus y squared equals c squared. And our c is 13. Our hypotenuse is 13. So that means I've got 144 plus y squared equals 13 squared is 169. And then y squared equals, just subtract 144 from both sides. So y squared equals, ooh, look at this. Always nice when it's a perfect square. Y squared equals 25. So square root both sides. And we get that y equals 5. And you might again be saying plus or minus 5. That's true. We took that square root, so we've got to remember that, negative 5 squared is 25. So is positive 5 squared. But again, we know which quadrant we're in. We're in quadrant 4. So which one of those should I take? Well, a picture helps out too, right? Y is negative in quadrant 4. So this is, our y now we know is just negative 5. So we're almost there. Cosecant theta is just the reciprocal of sine, right? So instead of being y over r, it's r over y. We've known since the beginning that r is 13, and now we know that y is negative 5. So cosecant theta should be 13 over negative 5, or, negative 13 over 5, however you want to write it. You can even put it there, negative 13 over 5. Looks like that's how they did it. But no matter how you write it, D is what's equivalent to the answer we got. So number 17, D. Okie doke. So this one here, number 18, angles alpha and beta are drawn in standard position with the point -7, -4 on the terminal arm of the angle alpha, and the point 2, -1 on the terminal arm of angle beta. All right, so already I'm kind of thinking we could find this angle if we needed to, right? We've got a point on its terminal arm. Same goes for this one, but let's just read ahead. The exact value of tan of alpha plus beta is, okay. So again, there are options here. We could actually find the angle alpha and find the angle beta and then add them up and then figure out what tan of that resulting angle is. However, honestly, that's probably a bit more work than taking advantage of the fact that we've got a sum identity here, right? Tan of alpha plus beta. So from our formula sheet, we can make use of this. If I can just find, right, if tan of alpha plus beta is what I'm looking for, this tells me that that will always be equal to tan of the alpha plus tan of beta over 1 minus tan alpha tan beta, right? So if I can just find tan alpha and tan beta, I'm good to go, right? I don't even actually need to find alpha and beta. I just need to find their tans, okay? Now, this can be pretty super quick if we remember that tan of an angle in standard position is equal to the y-coordinate over the x-coordinate, right? We are given the x-coordinate and the y-coordinate of points on the terminal arm here, right? So I'll draw the sketch out just to, visualize that a bit, but technically we don't even really need the sketch if we're confident enough with our our ratios and understand where they're coming from, but just to, show it, find tan alpha and tan beta. Okay, again, if the point -7, -4 is on the terminal arm of the angle alpha, well, look, folks, that just means the x is -7, the y is -4. That point right here is on the terminal arm of our angle. So our angle just looks like this, but how would we find the tan of that angle? We would just do, y coordinate. So -4 has an opposite side of -4 over adjacent. Tan is opposite over adjacent, or y over x, so -7, right? So we can see that if this is the angle alpha, then tan alpha just equals y over x, opposite over adjacent. So -4 over -7, which is just going to be +4 over +7, right? 4 over 7. Okay. Again, they want exact values, so we're definitely going to leave that as a fraction. We don't want to round and get decimals. Those now become approximate values. So do the same thing for beta. Same idea, though. Beta has the point 2, x is 2, y is -1. That point has the terminal arm of beta passing through it. So that means beta looks something like that. Okay. But again, same idea. How would we find the tan of that, right? We do opposite over adjacent, y over x. So we can see that that's just going to be, for beta, y over x is just -1 over 2. -1 over 2. There we go. And so now, right, step 2, find tan of alpha plus beta. Well, we have a trig identity that shows us what tan of alpha plus beta will always be equal to. Tan of alpha plus beta equals tan alpha plus tan beta over 1 minus tan alpha tan beta. And I know what tan alpha is. It's 4 over 7. So tan alpha is 4 over 7. Plus tan beta. I know what tan beta is. It's -1/2 over 1 minus tan alpha. Tan alpha is 4 over 7 times tan beta. Tan beta is -1/2. And now we've just got to simplify this fraction down, right? So 4 over 7 minus 1/2 over 1 minus, I might just do the multiplication here. So 4 times -1 is -4 over 7 times 2 is 14. So -4/14. Okay, so I'm subtracting a -4/14, again, because the positive times the negative gives me a negative there. Let's see if we can get maybe a common denominator up in our numerator, just so we can have one fraction there. Common denominator is going to be 14, right? That's where I can make 7 and 2 meet. So multiply this by 2 over 2 to get it over 14. That's going to be 8 over 14 minus, this one needs to be multiplied by 7 over 7 to get it to 14 as a denominator. So 7 over 14, that's equivalent to 1/2. That's equivalent to 4/7 over my denominator. My denominator here, right? I've got to do 1 plus 4 over 14, but I'll rewrite 1 as 14 over 14 plus 4 over 14. And we're getting there. 8 over 14 minus 7 over 14 gives me 1 over 14. 14 over 14 plus 4 over 14 gives me 18 over 14. And then, dividing by a fraction is the same as multiplying by its reciprocal. So this is the same as 1/14 times 14 over 18. And you can even just see the 14, right? 14 divided by 14. Once I multiply these out, the 14 is just going to be, canceled out. 14 over 14 is just 1, leaving me with just 1 over 18. So that is option A. Again, was this the only way you could have solved it? No, but it's probably one of the faster ways, as opposed to, you could actually figure out the angle alpha. You could figure out the angle beta, right? You just have to do an inverse tan to figure out alpha and an inverse tan, and then do the 4-quadrant stuff to figure out beta. And then you could just add alpha and beta and then repeat for that, whatever that is. But that's probably longer than just using in fact, it's definitely longer than just using our identity there for the sum with a tan. So 18, what did we say? It was A. 18 would be A. Okie doke. So this one here with an amusement park, a Ferris wheel, they love Ferris wheels when it comes to, trig questions because they repeat themselves regularly and it gives a very nice sinusoidal function, right? The height of them, they go up and down as they make their circle, okay? So this is definitely one, especially when we're given lots of information like this, it's nice to just first read what we're being asked to find so that we can kind of focus our thinking as we read the information. So we want to figure out what two parameters must be different in the two functions. I'm guessing it's one function for the big Ferris wheel, one function for the small Ferris wheel. That would be my guess. So is it A and B, A and D, B and C, C and D? So essentially, do the vertical stretch and the horizontal stretch, or the phase shift, which is really just a horizontal translation, but we give it a special name for a trig function, or the vertical displacement, which is really just a vertical translation, but we give it a special name for a trig function. Which one of those would have to be different? Let's just go ahead and see what's going on here. So an amusement park has two Ferris wheels that both load passengers at the bottom, 3 meters above the ground. Okay, so even just when they get on the Ferris wheel, they're already 3 meters above the ground. Cool. Both wheels require 40 seconds to complete one revolution. Aha, so to do a full cycle, it takes them 40 seconds. That sounds kind of like the period, or like it's related to the period anyway to me, right? And what is the period related to? B, the horizontal stretch. You might remember that B is just going to be 2 pi over our period. Why? It's actually, I think probably the more intuitive way to look at it is that the period is going to be 2 pi over B, but I'm even just going to write that as 1 over B, absolute value of B anyway, times 2 pi. And that makes this equation, where it comes from, make a little bit more sense, because a regular sinusoidal function, or a regular sine or cos function, repeats itself every 2 pi, right? Every 2 pi radians, because that just represents all the way around the circle in standard position, right? If we do a full 2 pi, sine is about to start just repeating itself, or cos is about to start just repeating itself from there. And so since B is I should be careful here. B tells us the horizontal stretch, but remember, for horizontal stretches, it's really 1 over B is what every x value gets multiplied by. So since the period is the distance on our x-axis for sine, it looks like this. So this is 2 pi radians. It's the horizontal value before it starts repeating itself. So if I take that and I horizontally stretch it by a factor of 1 over b, what's my new period? Well, 1 over b times 2 pi, right? If my b is 2, if it's 1/2 times 2 pi, I'm going to horizontally stretch this by a factor of 1/2. I'm literally going to multiply every x value by 1/2. So if I were to do that, my new period would look like this, right? I shouldn't change the amplitude, but just trying to make it so you can see it. My new period would look like that. It would now do a full cycle in just pi. 1 over 2 times 2 pi, right? Just pi. Anyway, that's how and why b is related to the period. So if they both take 40 seconds to complete one revolution, they have the same period. Now, if they have the same period, they've got to have the same b, right? How could period be different but b be the same? It can't. We're just dividing 2 pi by the period. If that's different, we're going to get a different answer for b. So right off the bat, right, we can kind of eliminate a couple options here. We can eliminate a because that has b, right? And we can eliminate c because that has b. So we're down to b and d. Honestly, we can kind of just think about it from here, but I'll go through it in a bit more detail. We could actually kind of get our answer already, but let's just keep going and thinking here. The larger Ferris wheel has a diameter of 25 meters. Well, they've drawn that in the diagram here, right? So if we think about what that means, they start at 3 meters above the ground already, and then by the time they're, at the highest point up here, they're going to be 28 meters total above the ground, right? Because again, they were already at 3, so add another 25, now they're at 28. So basically, as they ride this big one, they're going between a height of 3 at the minimum and a height of 28 at the maximum. and then they're just going back and forth, right? Up to a high of 28, down to a low of 3, and repeat. While the smaller Ferris wheel has a diameter of 10 meters. Okay, so that's going to give us a different ride, obviously, right? This one is only going up to a max height of 13. Max at 13. And a min at 3. Versus over here, like we talked about, min height at 3 meters, max height all the way up at 25 meters. Okay. So the height of a passenger on each wheel can be expressed in the form height as a function of time, that's all that means, h of t is equal to a cos of b times t minus c plus d, so it's a cosine function, where h of t is the height above the ground in meters, t seconds after the ride begins. Okay, so we want to figure out which of those have to be different. We've already eliminated b. B cannot be different because they have the same period. It takes them both 40 seconds to do one revolution. So that leaves A, C, and D. Now again, kind of looking at this, remember A tells us, A is the vertical stretch, yes, but for a sine or cos function, it tells us the amplitude. What is the amplitude? It's the highest it ever gets above the midline. What is the midline? It's the middle. It's the middle. So for this, it was going to look like this. Kind of spoils which one of them has to be different, right? But just to get back into the amplitude here again, right? For a basic unstretched sine function, we know that it goes up to 1, down to -1. I don't know why I'm drawing sine when it's a cosine, but it's the same idea for the amplitude, right? It goes as high as 1 and as low as -1. So the midline is here at 0, right? That's my midline. So the amplitude is just the highest or the lowest it ever gets compared to the midline. So this has a sine function or a cosine function has an amplitude of 1. Obviously, though, if we vertically stretch that, if we multiply every y value by a, which is what a vertical stretch does, we can change the amplitude, right? If I make a equal 2 and draw what that sine function would look like. Well, now, the y values that used to be at 1 are getting multiplied by 2. So my new max will be up here at 2, right? 0 won't change, but this min of -1 multiplied by 2, now my min is at -2. Like this. Okay, so what's the amplitude of that thing? The amplitude of that is 2, right? And that goes for any sine function. If we stretch it by a factor of a, the new amplitude is just going to be a. And that's because we're starting out from an amplitude of 1 on an unstretched function, an unstretched sine or cos function. So multiplying that 1 or that -1 by a gives us a new amplitude of a, because 1 times a is a. So right off the bat, we can see a is going to have to be different between these two, right? What is a for this? Well, it has a diameter of 25. So this amplitude here, the highest it ever gets above the midline, is going to be 12.5 meters, right? Or you could measure it here as well, 12.5 meters, right? Same goes for this one in terms of how we find it, but it's a different number. This is only a 10-meter diameter, so this only has an amplitude of 5 meters. It goes 5 meters above the midline, and it goes 5 meters below the midline. So that's our amplitude. So definitely seems like A has to be different. So technically we can just pick B and move on, but let's talk about why it needs to be D, and also why it doesn't have to be C. Okay, so D is the midline. We often refer to it as well as the vertical translation. That's how we would talk about it in previous units. So just like always, we're adding this to our y values, right? We're saying y is equal to this stuff plus a d, right? So what's that going to do? It's going to move the y values up if d is positive, or down if d is negative, right? So starting from a midline of 0 for a basic sine or cos function that has not been, translated, we start from 0. Well, if I slide it up d units, the midline's now at d, right? If I slid this whole thing up by 2, the midline, which was at 0, would now be at 2, and our function would look, something like this. It would go up to 3 and down to 1. instead of up to 1 and down to -1, because the middle is at 2 now. So the midline for this ride, right, you get as high as this, as low as this, but the midline is right here. It's actually at about, whatever it would be at 3 plus 12.5. So 15.5 meters would be our midline, D, right? Same thing over here, 3 plus 5, so 8 meters, right? And again, this makes sense. If our midline is at 8 meters, we go 5 above it. Sure enough, max at 13. 5 below it, min at 3, right? 3 plus 12.5, 15.5. 15.5 plus 12.5, 25. Okay, so that's why D is correct. Now C actually could be different between the two because C is just the phase shift. But notice it said they must be different because C could also very well be the same. Remember, C is like H in our normal transformation terminology, right? It's really just the horizontal translation. We call that a phase shift for a trig function. But all it does is, if I'll draw a cos graph. If we have a cos graph like this, all C does is slide the whole thing that way or that way, right? So maybe if C were, if C were pi, now we would be starting down here and going like this because I shifted it pi to the right. So I took the min that used to be over here and I shifted it pi units to the right, half a period. Or sorry, this is half a period for the base graph, not for the one we're talking about here. Okay, that would have a different period. But anyway, looking here, right, don't forget what's on our x-axis. It's time. It's time. Time is on our x-axis. Height of the Ferris wheel is on our y-axis. So is it possible that C could be different? Absolutely. That would just mean when time started, right, one of them was at a different height than the other. They would still take the same amount to complete a cycle, right? It's just because one's starting at a different place than the other doesn't mean that by the time they do a full cycle, they've taken a different amount of time to complete it. It's just that, start of the cycle was starting from a different height. So is it possible that C is different? Totally, right? If they started measuring the heights at different times, we would have a shifted graph, okay? Because the height at 0 would be a different spot because 0 represents the initial time. So if we start the time differently, the height might be differently, okay? However, it does not need to be different. It's totally possible that they started at the same time. We don't need C to be different. There is no way to describe these, though, without a different amplitude, A, and a different midline from D. So 19 definitely has to be B. Option B. Whoops. B. Okay, so number 20 here. The average temperature of a particular town in Alberta can be represented by the function T equals 15.8 times the sine of pi over 6 times T minus 3 plus 5. Already I'm kind of thinking this is probably one we're going to put in our calculator, but let's just keep reading. Where T is the average temperature in degrees Celsius and little t is the time in months after January 1st. All right, so this makes sense, right? A temperature graph will be sinusoidal, meaning it will repeat regularly because, we start from, let's say, summer high temperatures, gets mid in fall, and then down to cold in the winter, and then back up to mid in the spring, and then high in summer, winter, summer, over and over, repeating like that, okay? So this is going to represent the temperature on our y-axis, and on the x-axis, the time that's passed in months. So the minimum number of months to the nearest tenth of a month that it takes for the average temperature of the town to rise from 5 degrees Celsius to 15 degrees Celsius is... Okay, so if we think about that, right, the minimum number of months, well, our y-axis we know is temperature. So we want to figure out how much time goes by when we go from, I'm just, adding something in here. I don't know how accurate of a picture this is going to be, but from 5 up to, 15. We want to figure out, I guess it said rise, so I should actually, oh no, never mind, that works, sorry. 5 to 15, right? So how long does it take to go from 5 up to 15? right? We want the minimum amount of time. So we wouldn't want to go from like 5 to 15 because that's, that's saying go from 5 all the way down to minimum and then all the way back up to 15. So we'll go from here to here. Now time is on our x-axis. So what we're actually trying to figure out is what's the difference in the x value here and the x value here, right? For example, if this is, just making numbers up, but if this is like 11 months and this is 9 months on the x-axis, then it took us 2 months to go from 5 to 15 on the y-axis, on the temperature axis, okay? So definitely, like I said, this is one that we would just punch into our calculator and graph it and let the graphing calculator analyze the graph on the calculator and let it tell us those x values. Okay, so this is going to be a purely calculator one, or at least, I mean, not purely calculator, because obviously we have to kind of think about what we're doing. But in terms of the actual math, it would be a little bit miserable to try and do it algebraically. Okay, you know what? It wouldn't be that bad. I guess you'd put in 15, put in 5, and figure it out. But definitely one that I think makes more sense to graph. So I'm going to switch over to my graphing calculator here. I'm just going to put in this function. I can't put both up on the screen at the same time, but this is just what I'm entering. Okay, so let's start out by graphing that. But before we even graph that, here's all the checks we need to do. Okay, we can tell that our equation is working in radians. There's no degrees sign in there. And even if, even without that, pi over 6, that's probably talking radians. So we got to get this in radians. Should by default be in radians, but never hurts to double check. Sure enough, it is. Okay, that's good. Our window settings, we'll want to have to think about those. We want to be able to see high enough and low enough to on our sine graph to actually be able to tell what's going on. I'm just going to first enter the function, then we can think about our window settings. So let's just head to our y equals here. So that's that button there. I want to go to y equals, and I'm going to start entering this function. Okay, so the function was 15.8 times the sine. I'm going to use brackets here, quite a few brackets, because I want to do pi, so second pi over 6. And then I'm going to close that bracket because I don't want to do pi divided by 6 times stuff. I want to do pi over 6 times stuff. Notice there I still have this bracket, right? I've opened up the sign, so everything is still happening in the sign. That's what I want. Pi over 6 times, okay, now I'm going to open up another bracket because I need to multiply this by not just x, but x minus 3. So use the brackets here to make sure that I'm telling it to do what I want it to do, x minus 3. So close that x minus 3 bracket, and now close that sine bracket overall. So far I have that y equals 15.8 sine of pi over 6 times x minus 3. Okay, and now outside of those sine brackets, I want to add 5. Now if I graph this, oh, it's actually not as bad as I thought. You can see some of it. Okay, but you can tell we need to kind of zoom out on the y-axis. We need to be able to see higher and lower. Now, for many trig functions, I'll just show you this. You can go to, zoom, and you can go to 7, zoom trig. This doesn't work that well when we have a weird function that's been very stretched, like we can see this one has, right? It's been stretched by a factor of 15.8, and it has a b of 6 over pi. So it's not, a b of pi over, a b of 6 over pi. That's, no, a b of pi over 6. I'm getting my b's flipped around, okay? So it's very stretched, so that's why that zoom trig didn't work very well. Zoom trig works well when it's like a pretty basic trig function, like looks a lot like sine x or cos x. This one's been stretched so much that it doesn't look that much like it anymore. So just pointing out the zoom trig function is there, but it's not always going to work. Okay, so let's think about, again, this is how it has decided to zoom our thing by pressing that zoom trig function. Okay, normally this would be defaulted to -10 to 10 with a scaling of 1, and same on the y-axis, -10 to 10 with a scaling of 1. That's what we had at the beginning, right? And we can tell we need to see higher. Honestly, we could just make the y range higher and lower, but we can also take advantage of here, right? We can look. We know that our amplitude is 15.8, right? Our amplitude is 15.8. our midline is at 5 because that's our D value. It's been shifted up from 0 to 5, right? And the amplitude will have been vertically stretched from 1 to 15.8. So that can kind of tell us we're starting from a midline of 5, we're going 15.8 above it. So my max should be happening at 5 plus 15.8 or 25.8, right? And my min should be happening at 5 minus 15.8 or negative 10.8. Okay, so that kind of informs what my windows should be. Again, we have other strategies too. We know that we're looking for the time it takes for the temperature to go from 5 degrees to 15 degrees Celsius. So that could inform my Y min and my Y max. I know I at least need to be able to see from 5 to 15, okay? But I'll probably just, sometimes we don't have that at our disposal, right? So I'll use this because this will always work, right? Think about where your midline will be at 5, and then think about your amplitude. That tells you how far above it you go or below it you go, right? So when we don't know all that stuff, like we're looking for between 5 and 15, we can always rely on that. So I'll go up to 20.8. I'm just going to make it a nice even 21. Y max, I want to be able to see up to 21. And my min, what did I say? I said negative 10.8. Let's just go down to a nice even, I don't know, negative 12. Okay. Again, you mess around with that. Really what we need to do is be able to see higher and lower. And now I can kind of see the whole graph. I feel pretty good about this. Okay, so I need to figure out the time that passes when the graph goes from 5 to 15, the minimum amount of time. Now, unfortunately, our graph does not have a feature where we plug in our calculator does not have a feature where we can plug in a Y value and it tells me the X value. If that were the case, I would just say, tell me what X is whenever Y is 5, and then tell me what X is when Y is 15. The reason your calculator doesn't do that is that this is a function. So we can see there's actually many different X's where Y could be 5 or Y could be 15. There's in fact infinitely many, okay? So again, we could go second trace and value, and we can put in an X, right? I could put in X is 5, and it'll show me that Y is 18.68, but there's not a reverse way to do that, okay? I can't put in a Y and it tells me the X. However, there is the ability to enter new functions. So I can graph Y equals 5, and that will draw the line where Y equals 5, right? We'll talk about why that's helpful in a second. And then the other temperature I was interested in is when Y is 15. So let me graph this now. It's going to graph Y equals 5 and Y equals 15. We'll notice those two equations, right, they intersect with my sine graph. They intersect with my sine graph, okay? So the value of my sine graph there, since it's intersecting with the line Y equals 5, the value of Y on my graph there, my sine graph, has to be 5. Otherwise, how is it intersecting with the line Y equals 5? Same goes for this one, but with Y equals 15, right? How could my sine graph be intersecting with this Y equals 15 line if Y is not 15 on the sine graph at that point? So what we can do is figure out the X's where those intersections happen. And that tells me the X when Y is 15 on the sine graph, and the X when Y is 5 on the sine graph. And remember, X represents the time in months. So if I know the X where this intersection happens, I know the time in months where it got to 15 degrees. And if I know the X where this intersection happens, I know the time in months where the temperature was 5 degrees. So if I can find the difference between them, I can find the time that passed. So how do I find the intersections? Most things when we're analyzing graphs on our calculator come from second function and then trace. And it lists all these things it can do for us. We want to find intersections. We want to find where our sine graph intersects Y equals 5 and Y equals 15. So we'll do them one at a time. So I'll do option 5 for intersect. Now it's going to say first curve. Notice it's sitting on my sine graph. All that means is it's asking us, is this one of the curves that I'm looking for the intersection of? And it is, right? I want to find where that curve intersects with the red line or the green line there. Okay, so I'll just hit enter. I don't need to do anything. Second curve, it's saying, is this the other one? Am I looking for where that one intersects this one? And I am, right? So, I eventually need both, but first let's find this one. So I don't need to do anything. I'll just hit enter. Then it says guess. All that means is, put me close to the intersection point. Use these cursors here, right? See my little cursor moving as I move right or left. Make sure the cursor is, the closest intersection is the one that the cursor is next to, right? The intersection that you're trying to find is the one the cursor is closest to. That's pretty good. It definitely doesn't need to be perfect. It doesn't even need to be that good. I'll just hit enter, and there we go. My sine graph has an x value of 3. Do you see that there in the bottom of left? When y is 5 on my sine graph, x is 3, right? That's where that intersection is occurring. So that's where my sine graph has a y value of 5, and it's happening when x is 3. So 3 months, that's my initial time, right? It reaches 5 degrees after 3 months. Now I need to do the same, but for 15 degrees. So same thing, I'm going to go second trace. I would write down my 3. I'm going to need that. But 5, intersect. Now same idea, first curve, yep, I want the blue curve. Now, second curve, notice it's still stuck on that red line. We already got that intersection. So that's actually not the other curve we want to find. So using the up or the down arrows, you can jump curves. So now I'm on the blue one, don't want that, I'm going to press up again. Now that's the other curve I want to find the intersection of with my sine curve, right? So there we go. That's the other one. I can just hit enter, and it's just saying put the cursor so that the intersection you want to find is the closest one to the cursor. Doesn't need to be perfect, just close enough. And so that intersection happens. Y is 15 on my sine graph when x, the time, is 4.3 months. So it was 5 at 3 months, and it was 15 at 4.3 months. So going back to the diploma here, right? Now we know, okay, so it reached 15, right? It reached 15 after 4.3 months, and it was at 5 after 3 months. So how much time passed in between those? How much did our x-axis move that represents time? Well, 4.3 minus 3 is 1.3 months. It took 1.3 months to rise from 5 degrees Celsius to 15 degrees Celsius. So 20 is A. 20 is A. Okie doke. So numerical response number 7 here. Each of the following trigonometric expressions can be simplified to a numerical value, meaning that we can simplify these to actually just a number, not even like sines, coses, thetas, just numbers, where cos theta does not equal 0 and sine theta does not equal 0. Again, that's just because we can't divide by 0, right? So like, for example, here, can't divide by 0, so sine theta can't be 0. But even just for tan, right, we would have cos cannot be 0 because tan is sine over cos, right? Or secant is 1 over cos. Cotan is cos over sine, so sine couldn't be 0 there, but we're also dividing by it, but so cos couldn't be 0. So all that's saying is just, there's no NPV stuff that we're going to do, obviously. It's just covering their bases. Okay, anyway, with that in mind, these look very much so like trigonometric identities that we'll be able to use to simplify these, right? I mean, it kind of tells us that. They can be simplified to a numerical value. So, all right, so I just paused there for a second because I realized I needed to go get my formulas, my formula sheet, like you should always have out when you're working with simplifying trig functions, right, or trig expressions. Make sure you just have this next to you so you can glance at it, look for inspiration and all that kind of stuff, okay? Now, looking at what we've got here, we're going to try to simplify each of these down until they're just numbers because it's saying we can do that. And then this actually wants us to arrange them. Once we've done that, use these numbers to put them from lowest to highest, right? So like if this is 0, this is 1 and 2, then we would just write 1, 2, 3 because 0 is less than 1, which is less than 2. Those aren't what it works out to be, but that's the idea here. So now, I'll say right off the bat, there is more than one way to approach any question like this. What jumps out at you might be different than what jumps out at me. So don't think that just because I do something, you say, well, I would have done this. Am I wrong? Not necessarily, right? There's more than one relationship you can see here, right, and use to simplify. So I'm just going to start. I'm going to start with 1, right, expression number 1, and I'm just going to simplify it and see what jumps out at me. So 1 is tan squared theta minus secant squared theta. minus 1. Okay, so let's just see if we can get any inspiration by, looking at our formula sheet, thinking about it. Well, as soon as I see squareds, I'm thinking maybe one of the Pythagorean identities could come in handy here, right? That's these ones here. They're really all the same thing, just kind of some algebra to make them look a little bit different forms, but they're all come from the same starting place. They all come from the Pythagorean theorem for something on the unit circle has x this, y this, radius 1. That's where it comes from. A squared plus b squared equals c squared, and then rearranging and dividing by some stuff and rewriting in equivalent forms gives us those other two. But anyway, so tan squared theta minus secant squared theta minus 1. Well, look at this, right? Look at this one here. This one says that 1 plus tan squared theta equals secant squared theta, which tells me, right, that also tells me that tan squared theta minus secant squared theta, which is what I have here, I can rearrange this to look like this and see what it's equal to, right? So really that would just be, subtract 1 from both sides. Tan squared theta equals secant squared theta minus 1, and then subtract secant squared theta from both sides to make it actually look like that. Tan squared theta minus secant squared theta just equals negative 1. So that's what jumped out at me there. This is just negative 1. So sure enough, expression 1 here is just going to simplify to tan squared theta minus secant squared theta is just equivalent to 1. So we have negative 1 minus 1, which is negative 2. So expression 1 just equals negative 2. They said it would simplify to a numerical value. It did. All right, let's try expression number 2, because we got to order them from lowest to highest. All right, now we've got tan theta, cos theta, over sine theta. Okay. Very often with these, like we say, a good strategy is to try rewriting all your tans in terms of sine and cos, right? Looking like I don't see any Pythagorean stuff we could do. Definitely no double angles we could get rid of. No like common factors really that we could pull out to make things simpler. So definitely that's really all I'm seeing for inspiration here. I might rewrite tan theta as, again, tan theta is just sine theta over cos theta. Again, that just comes from the unit circle, right? Tan theta equals y over x, sorry. And on the unit circle, y is sine theta, x is cos theta. So sine theta over cos theta times cos theta over sine theta. All I've done there is rewrite tan theta as sine over cos. Well, hang on then. I can do some simplification right off the bat because cos theta, right? Cos theta here multiplied by sine theta and then divided by cos theta, that's just 1. So I'm just left with sine theta over 1 or sine theta over sine theta, and sine theta over sine theta. That just equals 1. So expression 2 simplified to the numerical value 1. So far we know that expression 1 is less than expression 2 because negative 2 is less than 1. So now we just got to figure out where expression 3 fits into this. We've got secant theta minus cosecant theta over cotangent theta. Okay, now again, I'm just going to rewrite everything in terms of sine and cos. That's really never a terrible idea. Sometimes there's stuff we can do to simplify without doing that, but often this gives us some ideas if we don't have any. So 1 over cos theta minus, that again, that's just secant theta. Definition of secant, it's 1 over cos. Okay, cosecant theta is 1 over sine theta. And then that's being divided by cotangent of theta. Well, again, since cotan is 1 over tan, cotan is the flipped of tan. Tan is sine over cos. Cotan is cos over sine. So minus 1 over sine theta over cos theta over sine theta. Sorry, that's a little janky looking. All right. Well, I can kind of see here I could do some simplification, right? I've got sine theta in a denominator divided by sine theta in a denominator. We can actually cancel those out just to make it a little more obvious. Let's rewrite that division by a fraction as a multiplication by a reciprocal. So dividing by cos theta over sine theta is the same as multiplying by sine theta over cos theta. And then sine theta over sine theta. Hey, sine theta over sine theta, that's just 1. So those kind of cancel out. 1 times sine theta over cos theta sine theta is just 1 over cos theta. So 1 over cos theta, oh my goodness, look at this. 1 over cos theta minus 1 over cos theta. Well, that equals 0. 1 over cos theta minus 1 over cos theta, we're subtracting something from itself. We're going to be left with 0. So expression 1 is -2 once simplified. Expression 2 is +1 once simplified, and expression 3 is 0 once simplified. So the least value is expression 1, right? That -2 is the lowest of all. Then 0, so that's expression 3. Okay, expression 3 simplified to 0. And expression 2 was the highest at +1. So 1, 3, 2 would be our answer to this one. We're just listing them in order to make sure we do the right order. What is this? Numeric 7. Numeric 7, start in the first box. 1, 3, 2. We don't need the fourth box. That's okay. We'll just leave it blank. 1, 3, 2. Alrighty, so let's take a look at this one here. The non-permissible values of x for the identity cosecant x times tan x equals secant x are... All right, so remember, why do we get non-permissible values anyway? Because for these, we're dividing by 0, right? We're not allowed to divide by 0, hence non-permissible. It's not permitted, okay? Now, you might be looking at this and saying, but there's no division happening. It's just multiplication, right? Careful. All of these actually involve division, okay? So basically with trig functions, we can get NPVs from kind of two places, right? Just like straight up division, obviously, right? Like if I have, 3 over sine x, then obviously sine x can't equal 0. But don't forget to also look in the nature of the trig function itself, right? So like within the function, I don't know how to properly word that, but like from the function itself, right? Just for example, like looking at this one, cosecant x, you might say, well, we're not dividing by anything there, but we actually kind of are. Cosecant x is 1 over sine x, right? It is, again, since sine x is y over r, opposite over hypotenuse, right? Cosecant x is r over y. And it is completely possible for y to be 0. That happens at 0 degrees and 180, or 0 and pi radians, right? So cosecant x does have non-permissible values because it's 1 over sine. And sine can definitely be 0. Sine is 0 wherever y is 0. That happens at this angle and at this angle. So with that in mind, even though it might not look like we're just doing straight up division here, we kind of are. There's division cooked into all of these. Remember, they're all ratios, right? They all involve dividing something by something else. So if we take a look, let's just see. Cosecant x, I'm just going to rewrite it. To find NPVs, to be honest, it's pretty much just rewrite it in terms of sine and cos and see where you could be dividing by 0. So cosecant x, cosecant is 1 over sine x, like we just said. I'm multiplying that by tan x. Again, tan x is just sine x over cos x, because it's y over r. Or sorry, y over x. So tan x, I'm just going to rewrite as sine over cos, sine x over cos x. And that equals secant x. Well, secant is just the reciprocal of cosine, right? It's just 1 over cosine x. And this kind of just lets me see where I'm actually doing the division, right? Now I can kind of see all the places where I could be dividing by 0, because I am dividing by sine x by doing cosecant x, right? This is r over y, and y can be 0, okay? Same thing here. Tan x, I'm dividing by cos x. Cos x can definitely be 0, so I'm going to get NPVs there, things x is not allowed to be, and same there. So altogether, my NPVs are going to come from here, right? Sine x cannot equal 0. And from here, cos x cannot equal 0. And, if this were something different, it would give us another NPV, but this is just a repeat of this one, right? So even if this weren't here, we would still have cos x cannot equal 0. Even if this weren't here, we would still have cos x cannot equal 0. But those are the two things we have here. If either sine x or cos x are 0, we will be dividing by 0 in this function. So that's not allowed to be. So all that's left to do is figure out, all right, what values of x make sine 0? what values of x make cos x equal 0? Okay, well, let's, we can think about this. Where is sine x 0? Again, sine x, sine of an angle, I'll just say, just so we don't get confused on the x's. X really is representing an angle here, but sine theta, let's just say, is opposite over hypotenuse, or y over r. So where would that equal 0? Well, wherever y is 0, right? So at what angles is the y value 0? Well, there's one, right? 0 or 2 pi or 3 pi, or 4 pi or 6 pi or 8 pi, okay? If we think of a point on the unit circle, that would be like 1, 0, right? Y value 0, so 0 over 1 is 0. Sine would be 0. But it happens again over here. If I draw this one in, right? Sine of theta, or sine of x, is also 0 over here, where we're at, on the unit circle, negative 1, 0. The y coordinate is 0, so opposite over hypotenuse, y over r is 0, okay? So that tells me, from this one, I get that, right? If sine x cannot equal 0, now I know that means x cannot equal, I'm just going to do from 0 to 2 pi at first, and then we'll think about the general, but x cannot equal 0 or 2 pi, from 0 to 2 pi. You're probably saying, there's more than that because we want the general solution. You're right, but just for now, I'll leave it like that. Now, where can we get cos x equaling 0? Because we're not allowed to do that, so we can't have x equaling anything where the cosine of it would equal 0. Well, again, cos of any angle is equal to x over r, adjacent over hypotenuse. So where can that equal 0? Where at any angles where the x coordinate is 0, right? So where does that happen? Happens at 90 or pi over 2 and 270 or 3 pi over 2, right? Because again, if we think about a point on the unit circle there, the x would be 0, the y would be 1, or down here, the x would be 0, the y would be negative 1. So cos theta equals x over r. Well, the x coordinate 0 here, right? So 0. Okay, cos would be 0. So from this one, we get that x cannot equal, again, just from 0 to 2 pi for now, I'll say it cannot be pi over 2. It cannot be 3 pi over 2. Okay, so now let's think about the fact that this happens infinitely many times, right? For example, yes, sine of x is 0 at 0. It's 0 at 2 pi. It's 0 again at 4 pi. It's 0 again at 6 pi and 8 pi, right? So we need to cover all of our bases, even going the other way. It's 0 at negative 2 pi. It's 0 at negative 4 pi. It's 0 at negative 6 pi, right? So all of those we need to include. So how do we do it? Well, we could do it one at a time, right? If we want, we could say x cannot equal 0 plus multiples of 2 pi. That's all angles that are coterminal to 0, right? We could say x cannot equal 2 pi plus multiples of 2 pi. But notice there, right, these are actually just separated. We can kind of combine the sine NPVs. They're only separated by pi, right? We know that our restrictions there are, oh, I missed one here, didn't I? Sorry, I missed one. I mentioned it when I was talking about, but then when I wrote it down, I left out pi. Whoopsies. Sine x is also 0 at pi. So 0, pi, and 2 pi. Whoopsies. I think I said it, but I didn't actually write it down when I was making the list. Okay? So we can notice there that it's just really, if I go from 0 to pi, that gets me from one NPV to another. And then if I go from pi to 2 pi, that gets me to another NPV. And then 2 pi to 3 pi, that's another NPV. So notice I can just combine these. It's actually just multiples of pi, right? It's actually just pi times n, where n is an integer, right? Those are what x cannot equal. It can't be 0, it can't be pi, it can't be 2 pi, it can't be negative pi, it can't be negative 2 pi, it can't be negative 3 pi. So that just covers all my bases. I'm just saying x is not allowed to be any multiple of pi, right? If n is an integer, this just represents any multiple of pi. That will always give me an NPV because it will always make sine x equals 0. Now again, you might be noticing, oh, that still doesn't, well, I guess it does match this one, but that's ignoring this. That's ignoring this here. So let's see if we can work this into our expression. Can we include these as well? Same thing, actually, right? If we look at those, they're also just separated by pi, right? 90 and 270, or pi over 2 and 3 pi over 2. It's the same thing. The NPVs that we get for cosec's are anytime, you know, it's in the same place as pi over 2 or the same place as 3 pi over 2. So that's adding pi. That's adding pi. Add another pi, you get back to another NPV. Add another pi, you get back to another NPV. So we can actually combine this information into just saying x cannot equal, well, pi over 2, right? 90, start from 90, and if you just add multiples of pi, you'll always be at a non-permissible value. Or again, subtract multiples of pi. Work the other way too, right? If I went in the clockwise direction, I'd still go from NPV to NPV. So that's why we say n is an integer, because it can be a positive or a negative number here to give us coterminal angles. All right, now that still doesn't quite fit what we were looking for, right? You might say, well, B and D kind of contain each one, but I got to pick one or the other, right? So that's kind of a clue that maybe we can simplify this even more. Just looking at what our NPVs are, right? Let's look. 0, pi over 2, pi, 3 pi over 2, 2 pi, right? We've got 0, 1/2 of a pi, right? A full pi, 1.5 pies, 2 pies, right? Do you see what we're going up by? This is actually just multiples of pi over 2, right? If you want to think about it in degrees, might be a little easier to see. 0, 90, 180, 270, 360, right? It's just multiples of 90. So we can actually combine both of these now to say that x just can't equal any multiple of pi over 2. Pi over 2n, where n is an integer. Right? Any multiple of 90 or pi over 2 is going to give us an NPV, which, I mean, if we think back to where we started here, we actually should not be too shocked by, because look at where we said the NPVs happen, right? We said they happen at the quadrantal angles. They happen at 0, 90, 270, 360, and anything coterminal to 0, 90, 180, 270, 360, right? Well, that's just saying, you know, starting from 0, add 90, that's another NPV. Add 90, that's another NPV. Add 90, another NPV. Or, you know, subtract going in the other direction. So there we go. It's actually just going to be, that is, they've written it slightly different than me. They've multiplied the n up there, but it means the same thing, right? Pi over 2 times n versus n times pi over 2 means the same thing. So option C. Option C is our answer here. This is number 21. 21 is C. Moving right along here to number 22, we have, for a team photo, 9 volleyball players are to stand in a line. Okay, sounds like we're in the perms and comms section of the diploma now. The photographer will place the shortest player at one of the 2 ends of the line. Okay, I'm going to emphasize that. The shortest player goes at one of the 2 ends of the line. And they're going to put the tallest player in the middle. The number of possible placements for the players in the photo is. Okay, so this is just, you know, how many ways do we arrange 9 objects, except we have some, you know, conditions. There's certain things we have to do. So this is kind of, we got 2 cases going on here, so to speak, right? We can kind of think of this as it emphasized at one of the 2 ends. So kind of like almost 2 cases, right? Case 1, the short player is on the left end, right? Case 2, short player is on the right end. Because both of those are different arrangements, right? Short player on the left versus short player on the right is a different arrangement. Or, sorry, short player on the left is different than short player on the right. So those are unique arrangements. We have to consider them as unique. So if we think about this, right, I mean, you might be able to see we just need to do it once and then double it, but just to really show the thinking here, right? In case 1, we've got 9 players, so 1, 2, 3, 4, 5, 6, 7, 8, 9, okay? How many options do I have for players to put here? If I want to do case 1, I'm going to put the short player here, right? The short player could go there. That meets the conditions. The short player needs to be at one of the 2 ends of the line. Okay, now the tallest player needs to be in the middle. So that also limits who can go here. Where's the middle? 1, 2, 3, 4, 5, right? 4 on either side. So that's the middle. There's only one person that can go there, right? We're just using the fundamental counting principle here. We're saying if, how many people can go there times how many people can go there times how many people can go there. So now I've got how many players left. I put the short player and the tall player in. I had 9 players total. I've already placed 2 of them. So I've got 7 left, right? 2 of the 9 are already placed. So that just means 7 players left who could go there, 6 who could go there, 5 who could go there, 4 who could go there, 3 who could go there, 2 left who could go there, and only 1 left to put there, right? So what does that give us? It's you might be able to see it's just 7 factorial basically, right? 7 times 6 times 5 times 4 times 3 times 2 times 1, 7 factorial times 1, so still just 7 factorial, gives us 5,040, okay? Now you might be able to see that we just need to double that in order to find the total, but just to really emphasize why, right? Case 2, because we also could have put the short player, 1, 2, 3, 4, 5, 6, 7, 8, 9, we also could have put the short player at this end. That still meets our conditions. It just said at one of the 2 ends. So this gives us a whole nother, set of arrangements. The arrangements we get when the short player is on the right side, right? So if we do that, now either way, the tall player needs to be in the middle. So 1, 2, 3, 4, middle is right here, okay? And again, how many players do we have left? 7. So, doesn't really matter where we start, but I could put 7 here, 6 here, 5 here, 4 here, 3 here, 7, 6, 5, 4, 3, 2 here, and 1 there, right? 1 left to place there. So multiplying that out, unsurprisingly, we also get 5,040 because it's all the same numbers. But again, just really emphasizing why there's actually twice as many as 5,040. Because there's all these arrangements where the player is on the left end, and then all those arrangements basically again, but with the player on the right end, the short player on the right end. So the total number is 5,040 from putting the short player on the left, plus another 5,040 if they were to be on the right, which is 10,080, or option B. 22 is B. Okay, so here we have a circle drawn with 6 points on its circumference as shown in the diagram below. A student creates polygons with 3 or more sides. Well, that makes sense because you can't make a polygon with 2 sides, right? That's not a polygon. A polygon has to be closed. So all polygons have 3 or more sides by connecting the points with straight lines. The number of polygons that can be created that have at most 4 sides is, okay, at most. So we'll talk about that in a second, but let's first just figure out what we're working with here. What is this actually asking us to do? They're creating polygons by connecting the points with straight lines. So we think about that, right? All that means is they're going like, okay, connect those, connect those, connect those. I made a triangle, right? Connect this to this to this. Oh, I made a different triangle, right? Connect this to this to this. I made a different triangle, right? What about connecting 4 points? So let's connect this to this to this, back to this. Hey, I made a quadrilateral. Not a very straight looking one, but a quadrilateral nonetheless, right? 4 sides. Okay. What if I did this? 1, 2, 3, 4. Hey, I made a different quadrilateral. Notice what we're doing here. We're just choosing 4, well, not necessarily 4. For the quadrilateral, it was 4. We're choosing R points to make an R-sided polygon, right? If I choose 5 points, I will make a 5-sided polygon. I'll make a pentagon, right? If I choose 1, 2, 3, 4, 5 points to connect, 5 dots to connect, I've made a 1, 2, 3, 4, 5-sided polygon. Okay, so it's just about, all it's really saying when we draw a polygon, it's just saying choose R dots to connect, and you will make an R-sided polygon. Okay, so how many do we have to choose from? How many dots do we have to choose from? Well, 6, right? 1, 2, 3, 4, 5, 6. So we have, again, drawing an R-sided polygon just means choose R points to connect, right? So R is just how many we're choosing. So what's the N? How many are we choosing from? We have 6 dots to choose from for connecting, meaning our N is 6. Now, does the order matter here? Well, let's see. If I go boop, 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 do I get a different triangle than if I go boop, boop, boop? No, right? That's the same triangle. So we're dealing with a combination here. It doesn't matter the order we draw them. Okay, we still get the same result as long as we choose the same 3 points. Okay, so we know we're kind of dealing with an N choose R, a combination situation. Now, let's now dissect this. At most 4. So the number of polygons that can be created that have at most 4 sides is, well, again, we can't make a polygon with any less than 3, right? And it even told us that with 3 or more sides. So at most 4 just means we could do 3 or we could do 4, right? We can't do 5, we can't do 6. So what we need to figure out then is how many ways are there to choose 3 from 6, right? How many ways could we connect 3 dots if there's 6 dots to choose from? And then figure out how many ways we could connect 4 dots, right? How many ways are there to choose 4 from 6 options? So in other words, right, we could do choosing 3 points. That's case 1. Case 1 that satisfies our conditions, right? That would have at most 4 sides. It would have 3. So case 1, choosing 3 points. That's just drawing a 3-sided polygon. Okay. Case 2 would be choosing 4 points. Drawing a 4-sided polygon. And we can figure out how many ways there are to choose 3 from 6, right? We know that it's just 6, choose 3. So we could go to the calculator, right? In fact, maybe I'll remind ourselves of how to put it into the calculator. Uh-oh. Got to refresh the page here. Oh boy. Bear with me. Okay, sorry about that. All right, so just to refresh your memory, right, for older calculators, newer ones you can get away with, but I'll just do it like, because most people probably don't have this fanciest, newest form, because it does a lot of stuff we don't honestly need. But first I'll put in my N, so my N was 6, there was 6 options to choose from, then math, that button there, then all the way over to probability, or PRB, okay, on an older calculator, then 3, option 3, N choose R, and my R is just 3. 6 choose 3. So it's 20. While I'm here, I might as well do 4, so 6, and then math, all the way over to probability, option 3, N choose R, and now I'll choose 4. So there's 15 ways to choose 4 things from 6 options. There's 20 ways to choose 3 things from 6 options. So this equals 20 And while we were there, we just did this one. 6 choose 4 is 15. So what's the total number of different polygons we could draw with at most 4? Well, the number of ways to do 3 plus the number of ways to do 4, which is 15, giving us 35. So option D. So number 23 is D. Okay, last multiple choice one here, number 24. The coefficient of the 9th term in the expansion of 3x minus 1 to the power of 10, written in descending powers of x, that's typically how we do it, is, all right. So, I mean, we could, do a whole Pascal's triangle thing, but we've kind of, we've studied Pascal's triangle to the point where we've been able to come up with a formula that lets us do this in a more straightforward way. But you could do the Pascal's triangle. It's kind of fun to do. Okay, on a diploma, I might not recommend it. Save yourself the time. But the 9th term, so we're looking for T9, right? The 9th term. Now, remember, that means our K value here, our K is 8. Okay, because again, if we think about the Pascal's triangle, we always start counting from 0. So it's like, n choose 0, n choose 1, n choose 2, where this is the k. So k is always 1 less than the term number, right? First term, second term, third term. First term, k is 0. Second term, k is 1. Third term, k is 2. So for the 9th term, k is not 9, it is 8. Be very careful there. Common student mistake for sure. In the expansion of 3x minus 1 to the power of 10. So let's write out our binomial expansion formula. It is t, so that the k plus 1th term is equal to n choose k, again for reasons that I won't go to here in this video, right? But again, since there's, we're arranging different multiplications of these two terms, that ends up working out to make sense that there's n choose k as our coefficient there. Okay, n choose k times x, just a general placeholder x. Remember, that doesn't actually always mean x, to the power of n minus k times y to the power of k. Right? Now, so with this in mind, okay, keep in mind, don't forget, x just stands in for your first term. So our first term here is not x. Our x, our first term is 3x, not x. And our y is not y at all. It's negative 1, right? Our y is negative 1. So we're going to have to keep that in mind when we go to actually start putting stuff in here in order to calculate the coefficient, because that will affect the coefficient, right? For example, squaring 3x gives me 9x squared. So that 9 is going to become part of the coefficient, right? I'm not saying we're squaring it. We're probably doing more than squaring it, but we'll see. Actually, looking ahead, it looks like we will square it. It's kind of just a coincidence I picked that. Okay, so tk plus 1. We're looking for t9. K is 8. So the 9th term will be n. Oh, I forgot to mention n. What is n? Our exponent, right? N is 10. Okay, so we're going to have 11 terms here with n being 10. We're looking for the coefficient on the 9th term. So n is 10, so I've got 10 choose 8. Okay, that's just a number. We can put that in our calculator and get it. Times our x, don't forget, x is just the first term. In this case, x is 3x. So 3x to the power of n minus k, so 10 minus 8. That's going to be 2. That's why I said we actually are going to end up just squaring the x here. So 10 minus 8 times the y, which again is not just y, it's the second term. In this case, that's negative 1 to the power of k, which is 8. Okay, might drop the color coding here, but T9 then equals, well, 10 choose 8. Again, you can go onto your calculator, enter that. If you're don't remember how to do that, check the video over the previous question, one question ago. I did a calculator tutorial on how to enter that again. But if you do that, 10 choose 8 is just 45. So we've got 45 times 3x to the power of 10 minus 8. Well, 10 minus 8 is just 2. times negative 1 to the power of 8. Well, negative 1 to an even power is just going to be positive 1, right? I mean, if you really want, you can do negative 1 times negative 1 times negative 1 8 times, or I guess you could even put it in your calculator, but let's just think about it, right? Negative 1 multiplied by itself an even number of times is going to give us a positive 1 out. All right, so we're getting there. That means the ninth term is 45 times, well, 3x squared is just going to be 9x squared, right? That's 3x times itself. 3 times 3 is 9. X times x is x squared. So we can simplify that to 9x squared. And then times 1, I mean, it's not going to change anything. We can just leave out the times 1, right? So then T9, the ninth term, is just 45 times 9 times x squared, and 45 times 9 is 405 x squared. So what is the coefficient on the ninth term? It is 405, option D. So for number 24, our last multiple choice on this diploma, it is D. Alrighty, and for the last numerical response on this diploma, numerical response 8, looks like we've just got a basically, which of these two are true, which two statements are true. So 6 statements about the expansion of the binomial x squared minus 1 over 2x to the power of n. Which of these statements will be true, right? You can kind of see here if you look, right? Often a good strategy with these is they're kind of like groupings that we're deciding. So notice statement 1, 2, and 3, those are all, only one of those can be true, right? Only one of those can be true. And same goes for statement 4, 5, and 6. The largest exponent is this, or is it this, or is it this, right? There's no way 6 and 5 could be true. They're saying things that contradict each other. So really what this boils down to is which one of these is true and which one of these is true, right? If we look at it that way. So let's just see. Statement 1, the expansion contains n minus 1 terms? No, right? A binomial expansion always contains n plus 1 terms, right? I mean, just checking out with a very simple one, if I have x plus 1 squared, that's x plus 1 times x plus 1. So that's x times x is x squared, x times 1 is x, 1 times x is x, and 1 times 1 is 1. So this has, once simplified, 3 terms, right? N was 2, and we got 3 terms when we expanded it out. Okay, so we could do another one to prove it if we wanted, but that always ends up being the case. We always have one more term than we do the exponent on our binomial. Okay, so definitely, I mean, right off the bat, there we go. Statement 1, 2, and 3. No, statement 1, statement 2, it doesn't have n terms. It has n plus 1 terms. So statement 3 is true. Okay, now we just got to decide between statement 4, 5, and 6. So it's either the largest exponent on the x variable is 2n, the largest exponent on the x variable is n, or the largest exponent on the x variable is n plus 2. Okay, well, I mean, we can kind of see here by looking, right? Look, which of these is going to give us the bigger exponent on x, our first term or our second term? First term, the exponent on x is 2. Second term, it's x to the minus 1, right? So this actually gives us bigger exponents on the x term, right? We want the first term to have the highest exponent because that's going to give us the biggest exponent on x overall. Now, don't forget, when we expand it all out and write it in descending powers of x, right? Basically, our numbers are going to look like, n choose 0 times x to the n minus k, but since k is 0, it'll be x to the n, y to the 0, right? Plus n choose 1, x to the n minus 1, y to the 1, right? Plus dot, 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 dot. And it goes all the way to n choose k, where that's the last one in the row, right? X to the 0, y to the n. Okay, so keeping that in mind here. Sorry, folks, video got cut off there for a second, and I just also realized that should actually be n choose n at the end of the thing there, right? That's the last term there. So again, right? I mean, don't need to fully draw this out or anything, but the key takeaway is that the first term's exponent, it counts down from n to 0, while the second, part here, the y part, counts up from 0 to n, the exponent on it. So if we want to find the first term here to make sure that our x squared has the biggest power possible on it, right? Because this part is going to have an exponent, x is to the -1 there. So we don't actually want that to be the one that's maximized. We don't want the last term, right? We probably want the first term. Every time we multiply by this again, we actually end up with a smaller power of x. So you could actually reason without actually finding the first term here. You could probably reason that statement 4 is going to be true, because we're going to take x squared, and then in the first term, it's just to the power of n. You might be saying, oh, but this has a power of -1, so won't that affect it? That's true, but in the first term, this has a power of 0, so it just becomes 1, right? We have 1 over 2x to the power of 0. But just to really emphasize it, let's actually go ahead and, find that first term where we'll have the greatest power on x. So for t1, our k is 0, right? K is always 1 less than the term number. So tk plus 1 equals n choose k times our x to the power of n minus k times y to the power of k, right? Now our n here is just n, but our k for the first term is going to be 0. So t1 equals n choose 0 times x to the, not x, got to remember, x isn't just x, it's the first term. So our x here is really x squared. So times x squared to the power of n minus 0. Now n is just n, we don't know what it is, but k is 0. And then our y, again, it's not just y. In this case, it's -1 over 2x. I'm going to rewrite that, though. It's always easier with these to rewrite them as negative exponents. So y equals x to the negative x to the -1 over 2. It's actually not going to end up mattering much because the exponent on it is just 0 anyway. I guess we could even write this as negative, 2x to the -1. Okay, so let's just do that. Negative 2x to the -1 to the power of k, but k is 0. That's why I'm saying it doesn't end up mattering much because anything to the power of 0 is just 1. So term 1 is just, now again, we're just looking for the exponent on x. So we can actually completely ignore anything going on with the coefficients. We don't care what the coefficient of this term is. We just care about what the exponent on x is. We can actually figure out that this will just be 1, right? N choose 0 is 1, okay? But here, n choose 0 is 1. I've got, just focusing in on this part, that's where we get the exponents. Coefficients don't affect the exponents. I've got x squared to the power of n times, well, anything to the power of 0 is 1. So look, x to the 2n. The greatest exponent on x will happen in the first term again, because our first term here, in the first term of the expansion, our first term has the greatest power. And our first term in this binomial has a power of x squared versus a power of x to the -1. So maximizing that, which is what we do by finding the first term, is what we want. And triple proving it now, x to the 2n is what we will get. Not x to the n, not x to the n plus 2. So the two true statements are statements. Whoops. Why did I say statement 1 there? Sorry, folks. Statement 3 and statement 4. Sorry, that was probably confusing. I checked off the right one, but then I wrote in the wrong number. So numerical response 8 is 3, 4. 3, 4. We need the first 2 blanks. We don't need the last 2. That's okay. We just leave the last 2 blank. All right, so moving along into the written response questions now. There are 3 on the diploma. So let's start off with number 1 here, 1A. Typically, they're split up into 2 parts. So all 3 questions have an A and a B. Okay, so let's start out 1A. The graphs of 2 functions, f of x and g of x, are shown below. Three new functions, j of x, k of x, and h of x, are defined by j of x is f of g of x, k of x is f of x over g of x, and h of x is g of x minus f of x. Okay, so different, operations being performed or compositions being performed with the functions. Let's just see what we actually got to do. Determine which function, j of x or k of x, has the larger value when x equals 0. Okay, so that's just saying which one's bigger, j or k, when we put x equals 0 into that function. So let's remind ourselves, what is j of x? J of x is f of g of x. So j of x means we put g into f, right? I'm just going to write that out here. J of x is f of g of x. Be careful, that's not a multiplication. The dot is empty, so that's a composition. For compositions, I find this a little bit easier to think about. I like to rewrite it this way because that really shows me that what am I doing? I'm putting the outputs of g of x as the inputs of f of x. Okay? And then k of x, what was k of x? K of x was just f of x over g of x. So the outputs of f of x are going to get divided by the outputs of g of x, and that defines k of x. K of x equals f of x over g of x. All right, so simple enough here because we were given the graphs of f and g. It's actually really, really nice when they give us the graphs because now we just need to look at what's on there, right? We just need to look at what's on there and pick out the outputs of f of x and do the right thing with them, or vice versa, pick out the outputs of g of x and do the right thing with them, okay? Now, an important note on terminology, they asked us to determine here, right? Determine means, well, solve the question, right? Show your work, show your thinking, but ultimately they just want to see you answer the question. Determine, figure out something that we don't know now. So we need to figure out which one's larger, okay? To show our work here, we're going to need to show us finding the value of j of x when x is 0 and finding the value of k of x when x is 0, right? There's no universe in which you flip a coin and say j of x is bigger and you get any marks, right? It's a 50-50. They're not going to give you a mark for just saying j of x and hoping you're right. You're going to have to show how you calculated the value of j of x and how you calculated the value of k of x, and therefore which one's bigger when x is 0. Okay, so j of 0 and k of 0, I should say. All right, let's do j of 0. So if j of x is f of g of x, well then j of 0 is f of g of 0, right? All that's saying is figure out what the value of the function g is when x is 0, and then whatever that is, put that as the input into f of x. Luckily, with the graphs, it actually makes it pretty straightforward because we can see from the graph that what is g of 0, what is y when x is 0 for this function g? Well, when x is 0, y is -3, right? We can see that right there. G of 0 equals -3. When we input an x of 0, we output a y of -3 for g. So that means j of 0 is f of g of 0, but g of 0 is just -3. So j of 0 is just f of -3, right? When we have these compositions of functions, we put stuff into the first function, and then that gets spat out into the second function. Whatever it spits out when we input 0 gets put into f of x, okay? So now I got to figure out what f of -3 is. So let me go to the graph here. When x is -3 for the function f, it looks like y is 1, right? The output of f when we input -3 is +1. And that's what we did. We input -3 to f because we input g of 0 to f, and g of 0 was just -3. So f of -3, which is j of 0, is 1. J of 0 is 1. Now we got to redo that, but for k of x. So k of x equals f of x over g of x. So what is k of 0? Well, K of 0, right? I mean, I just have to figure out K of 0 is just f of 0 over g of 0, right? It's not a composition where I'm figuring out what f of 0 is and then putting it into g of x. I'm really just taking f of x, dividing it by g of x. So at 0, that means put 0 into f, whatever it gives out, divide it by whatever g gives out when you put 0 into it. So again, like I said, it's nice when they give us the graphs, because now we really just got to go look and say, okay, what is the value of f when x is 0? Well, when x is 0, f seems to be negative 2. F of 0 equals negative 2. So negative 2 over g of 0. Let's head over to g. Hey, we already figured that out. It's negative 3. G of 0 is negative 3. So over negative 3. So k of 0 is negative 2 over negative 3, which is just positive 2/3. Now we're almost done. Don't stop there, though. Always make sure, go back and read the question one more time, see if you've actually answered it, right? Sometimes you get lost along the way. You forget what you were actually trying to answer. We were trying to say which one has the larger value when x equals 0. So just a quick little sentence, right? J of 0 equals 1. K of 0 equals 2/3. So J of x, since 1 is greater than 2/3, right, has the larger value when x equals 0. All right, just a quick little sentence to say what we did. And there we go. That should get 2 out of 2. We showed all our work, showed what we did, right, explained our thinking, and gave an answer. Okay, so for part B of written response question 1 here, it's just continuing on from what the information they gave us here was. So now it wants us to sketch the graph of h of x on the coordinate plane provided below, identify the coordinates of the y-intercept, and state the domain of the function. Okay, so what is h of x? What was h of x? H of x was g of x minus f of x. Kind of annoying that they didn't give us the graphs again. We have to kind of flip back and forth, but that's all right. So h of x was just equal to g of x minus f of x, right? G of x minus f of x. Did I say that right? Yes, g of x minus f of x. So that means, you know, what it always means. What is h of x? Take the value of g and subtract the value of f. If you do that at every x, you're starting to think about what h of x is at every place, because h of x is just defined as g minus f, okay? So a good approach for this might be to make a little table of values, right? Like just say g of x, f of x, and then h of x. Right? Because now what we can do is we can just kind of go to the graphs, get some x's, get some, you know, values of g, values of f, and then figure out what h will be, right? Once we subtract g or f from g, okay? So going back to this, right? I mean, like let's say x is negative 4, right? When x is negative 4, looks like f is negative 2 and g is positive 5. So when x is negative 4, g is negative 2, f is positive 5. So h of x is just g minus f, right? H of x is negative 2 minus 5. H of negative 4 is g of negative 4 minus f of negative 4, which is negative 2 minus 5 is negative 7. And there we go. We've actually already got a point on h of x, right? So we could even start sketching our graph. When x is negative 4, h of x will be negative 7. When x is negative 4, h of x will be negative 7. There's a point on our graph, okay? And we could just keep doing this for, you know, oopsies. I did that backwards, didn't I? Yep, I did. So sorry, f was negative 2. G was positive 5. You were probably saying, what's he doing? F was negative 2. G was positive 5. So G was positive 5. F was negative 2. Just notice that there. Okay, whoopsies. So G minus F is not negative 2 minus 5. It's 5 minus negative 2. So 5 minus negative 2, giving us positive 7. Okay, good thing I caught that early. So when x is negative 4, h of x is positive 7. All right, let's continue on here, though. Let's get another point. How about negative 3? Right? When x is negative 3, got to make sure I don't mix them up this time. When x is negative 3, f is 1, g is 0. F is 1, g is 0. Let's not forget that. F is 1, g is 0. There we go. So when x was negative 3, g had a value of 0, f had a value of 1. So h is going to be g minus f, or 0 minus 1. H will just be negative 1, right? 0 minus 1 is negative 1. So when x is negative 3, h of x is negative 1. Right around there. Okay. Let's keep going. Negative 2. When x is negative 2, f is positive 2, right? X is negative 2. F is positive 2. G is negative 3. So g is negative 3. F is positive 2. So again, g minus f, right? Negative 3 minus 2 is negative 5. That'll be the value of h of x there. And again, that was when x was negative 2. So we just keep going like this, filling in points, right? When x is negative 2, h is negative 5. Let's do when x is negative 1. See what happens. When x is negative 1, f is 2, right? G is negative 4. So g is negative 4. And f is positive 1. So then g minus f is negative 4 minus 1, or negative 5. So when x is negative 1, we've got another minus 5 there. Let's do one more, and then we'll see something interesting happen after that. How about when x is 0? When x is 0. When x is 0, g of x will be negative 3. H of x will be negative 2. No, sorry, f of x will be negative 2. So f of x will be negative 2. What did I say g of x would be? Negative 3? I'm going to double check so I don't do the wrong thing. Yeah, negative 3. So then, okay, g of h of x, which is just g minus f, is negative 3 minus negative 2, or negative 3 plus 2, or negative 1. All right, so that means when x is 0, h of x is negative 1. Now, look what happens if I go beyond that, right? This is important with these compositions. Remember, or sorry, not composition, operations in this case, this subtraction, right? G of x is not defined for x is greater than 0, right? It stops. Notice there's no arrow there. It's not saying that this continues on forever like that. No, that is an end point. That's a hard stop, right? Same thing over here when x is less than negative 4. That's a hard stop, okay? So you might be saying, okay, so beyond those x's, right? Beyond this, does it just look like f? Does h of x just look like f because g stops being defined here? No, it doesn't, because don't forget, h of x depends on g and f, right? If h of x is g minus f of x, I don't know if you can hear my dogs fighting in the background, wrestling over a toy. G of x minus f of x, right? There's no such thing as saying, oh, g of x is undefined but h of x is still defined. No, right? How can h of x be defined if this is undefined, right? It depends on something undefined when we go beyond x equaling 0. So h of x would be undefined beyond x being 0, right? G of x doesn't exist there, and h of x depends on g of x. Similarly over here, when x is less than -4, h of x is not defined because f of x is not defined. And h of x depends on f of x. It needs f of x to be defined for it to be defined, right? So we stop there. This is crucial, okay? If you look, and by the way, I'll just mention here, if you scroll down in the release diploma here, you'll see they've included lots of samples of student responses and ones that students got wrong, why they lost marks, things like that. You'll notice that quite a few students lost marks because they did this. They drew arrows, right? Maybe one arrow, maybe two arrows, but either way, that will lose you a mark, right? Or at least half a mark here, because that is not true. H of x does not continue beyond x being -4. It does not continue beyond x being 0, right? It really does stop here and stop here. So you need to make it clear if you're sketching a graph like this that it has an endpoint, right? That would do the job, right? That would do the trick. I'm showing that it ends there. It doesn't continue on, okay? That really is all of h of x, because since f and g are only defined, together between -4 and 0, h of x is only defined between -4 and 0. So I've sketched the graph. Let's just finish up here with the coordinates of the y-intercept for h of x and the domain of h of x. We kind of found the y-intercept as we went. Y-intercept happens when x is 0, right? Even if you weren't sure about graphing, never just leave a question blank, right? You might be able to answer parts of it, so you could still get a mark if you know that the y-intercept happens when x is 0. So even if you had no idea how to graph it, you could say, okay, well, when x is 0, what's g minus f? Because that'll be h, right? So -3 minus -2 is +1. Graphing it definitely helped us out. There's our y-intercept, okay? But now we need to state it. The coordinates of the y-intercept. Read carefully. Coordinates, that matters. You can't just say it's -1. Those aren't coordinates, right? What you could say is 0, -1, okay? Again, we kind of knew that from here too, right? When x is 0, y is -1. The domain, again, even if you weren't sure how to graph it, you could have gotten the mark for domain, right? Because you can see that, well, f is not defined when x is less than -4, and g is not defined when x is greater than 0. So if f and g, right, both contribute to h, then our h needs both f and g to be defined. That's only going to happen between -4 and 0, because that's the only place where both f and g are always defined, okay? So our domain is just going to be the set of all x's such that -4 is less than or equal to x, which is less than or equal to 0, where x is an element of the real numbers. You could also say it in interval notation. They would take that as well. Make sure you use the right brackets. We want square brackets here because they are included. It's defined at -4 and it's defined at 0. It's just not defined beyond them. So again, the graph makes that kind of nice and easy to see as well, right? We can see x goes from -4 to 0. But notice what I mean, right? Never leave it blank completely. I'm sure you can get a mark or two here or there, even if you're not 100% sure how to finish it. Never leave it blank. You can get some of the marks, right? Even if it's just showing a couple steps or a couple works, or even just writing a sentence about here's what I would do, I don't know how to do it. It's worth a shot. That might get you a half a mark here or there. All right, so there we go. All right, moving on to written response number 2A here. Okay, algebraically solve. Obviously that means you can't just put this into your calculator and let your calculator graph it and then tell you. You will get probably 0 out of 3 if you just write the answer here, okay? Algebraically means using like math symbols and algebraic manipulation and all that stuff. So we got to show all our work, show our steps, and get our answer here. So we want to algebraically solve the equation secant squared theta plus secant theta equals 2, where 2 pi is less than or equal to theta, which is less than or equal to 3 pi. So kind of an interesting domain there, but let's not panic, right? That just means, if we really think about it, here's 0, here's 2 pi. So we're starting our domain there from 2 pi to 3 pi. So really, we're just in quadrant 1 and 2. It's just saying we're going to be thinking about having done a full rotation before whatever angles we get. So honestly, I'll probably just solve it from 0 to pi, and then at the end I'll add that extra 2 pi rotation. That's probably how I'll go at it, okay? Because it'll be the same thing. They're coterminal. It's just we did a full rotation before we started. Okay, so let's start out when solving a trigonometric equation, right? First thing we want to do, if it's quadratic like this one is, right, we want to get everything to one side. I mean, normally we just want to isolate the trig ratio if there's only one. But since there's two here, we're never just going to get secant theta equals stuff, right? But what we can get is all of the secant stuff on one side of the equation and then factor it like we would any quadratic and solve that way, okay? So let's start out with that. Step 1, secant squared theta, probably hear my dog squeaky toy, secant squared theta plus secant theta equals 2. Let's bring everything to one side. So secant squared theta plus secant theta minus 2 equals 0. And again, the reason we want to do that is that if we have stuff equals 0 and we factor, it's really easy to see what values of theta could make it true, or what values of secant theta could make it true, right? Because once we have two factors, well, the only way to make those two things being multiplied together equal 0 is if they themselves equal 0, right? 0 times anything is 0. So don't get bogged down by the fact that it's trig stuff happening, right? This is really no different than x squared plus x minus 2 equals 0. It's just that instead of an x, we have a secant theta. But secant theta is just a number. It's just a ratio, the same way x just stood in for any number. So we can factor this the same way we would have factored that. We would ask ourselves, right, what two numbers multiply to the constant term? So what two numbers multiply to -2 and add to +1? And I can do that here, by the way. I can use this simple product sum method because my coefficient here is 1, right? If this were a 2, I would have to do decomposition, ask myself what multiplies to -4, right, AC, and then do all the decomposition stuff, break the middle term up into 2, group them, and then factor individually. But here, I can just do simple product sum. So two numbers that multiply to -2 and add to 1, how about 2 and -1, right? When in doubt, you can list out the factors of 2, but that's pretty quick. It's just 2 and 1. So if the 1 is negative and the 2 is positive, then 2 times -1 is -2. 2 plus -1 is +1. So yeah, those work out. Meaning that my two factors are secant theta plus 2, right? Same way if I had x squared plus x minus 2, one of my factors would be x plus 2, right? The other one would be x minus 1. It's just instead of x, I've got secant theta times secant theta minus 1. And that is apparently equal to 0. So how can that be possible? Well, there's only two ways to make that true, right? Stuff times other stuff equals 0. Well, only 0 times something can equal 0. So this can only be true if secant theta plus 2 equals 0, or if secant theta minus 1 equals 0. And that can only be true. Secant theta plus 2 can only equal 0 if secant theta equals -2. And this can only be true if secant theta equals 1. So there we go. From here on out, we're kind of back in Math 20 trig, sort of. I mean, in Math 20, we wouldn't have had secants, but it's pretty quick to turn that into a 1 over cos. And then we really are back in Math 20. We're just trying to solve two Math 20 problems at the same time, basically, right? What values of theta make secant theta equal -2? What values of theta make secant theta equal 1? Okay. So with that in mind, I might just, right off the bat, just because it's often easier to think about coses and sines and tans, I might say cos theta equals 1 over this, so negative 1 over 2. And cos theta equals, well, 1 over 1 is just 1. So that's really what I'm trying to solve here. Cos theta equals negative 1/2. Cos theta equals 1. All right. So now that we've got that, let's get our reference angles. And then we can start thinking about quadrants and all that stuff. Step 2, okay, what reference angle would give us these ratios? Okay, so I'll just say we're finding our reference angles. Find our reference angles. Okay, so 1 over 2, that should probably get you thinking special, right? 1s, 2s, root 3s, root 2s, that's where we think of special triangles. I see a 1 and a 2. So for cos theta equals negative 1/2, right? Again, we're just thinking about the reference angle here, so we won't worry about that negative part for now. Okay, we're just getting a reference angle. So if I have adjacent over hypotenuse being 1 over 2, what is this angle? What is this angle? It's one of our special angles, right? This is 60 degrees or pi over 3, right? Again, I remember that the root 3 goes with the 30-degree angle, so that makes this the 60-degree angle. So that's pi over 3, okay? Boom, got it. Reference angle for this one is pi over 3. Now for cos theta equals 1, we're not even really getting a reference angle. We're actually going to be able to just get the angle itself. So for cos theta equals 1, there's only one spot where cos theta can equal 1. Well, there's infinitely many, but they all look the same. Where can cos theta equal 1? Well, cos theta can equal 1, since cos equals x over r, right? We need x to be the same as r. So using the unit circle, because that's the simplest one, when x is 1 and r is 1, right? On a unit circle, the radius is 1. So where does that happen? Where is x the same as r? It happens at 0. Now I know you're saying, but hey, our domain is between 2 pi and 3 pi. I know, but I'm just going to think about it here at first, and then we'll worry about adding that on, okay? So if you like, the reference angle is 0, right? But that's just the angle here, okay? That's just kind of the angle here. So where does cos theta equal 1? When theta r is 0, okay? When our reference angle is 0. So leading into that now, let's get our quadrants. So I'll move up here to step 3. Okay, getting the quadrants. So again, for cos theta equals negative 1/2, for cos theta equals negative 1/2, we can just use cast here, right? We can just use cast, C-A-S-T. So cos theta is negative. It's less than 0. So where does that happen? Well, cos is positive in quadrant 4. They're all positive in quadrant 1. Again, in previous questions, I've talked about the reasoning behind that. To save some time here on this long question, I might not get into all of that. It has to do with where y and x is positive and how y and x are involved with cos, okay? But I don't know why I'm circling them. They're actually what we don't want. We want either quadrant 2 or quadrant 3. But don't forget this. We need between 2 pi and 3 pi. So now I'm actually thinking about this, right? Because I'm finding the quadrants. I'm getting close to finding the angles themselves. Okay, so this means I just want, right, between 2 pi and 3 pi. Again, what we said here, that's really just in quadrant 1 and 2. So yes, cos theta would be negative in quadrant 3, but that's not part of our domain, right? So none of these except for quadrant 2. Okay, so this one is in quadrant 2. Now, cos theta equaling 1, right? Cos theta equaling 1, that's not really in a quadrant because like we said, it's here. So not a ton to think about there, but we will think about it now when we actually state our angles. So actually finding the values of theta themselves. Here we go. Okay. So we know that we are in quadrant for cos theta equals -1/2. Cos theta equals -1/2. Like we said, we know we have to be in quadrant 2. And we know we have to be in quadrant 2 with a reference angle of pi over 3. Okay, so we're going to be in quadrant 2 with a reference angle of pi over 3. Now, normally, if we were just 0 to 2 pi, right, so 0, 2 pi, pi over 2, pi, 3 pi over 2, okay, normally we would just say this is our angle. But that's not within our domain for this question. The domain was from 2 pi to 3 pi, okay? So we need to go past that. We need to go all the way around to 2 pi, and then, like we said, another half rotation. That gives us our whole domain. So from 2 pi, this is actually where our domain starts now, right? From 2 pi to 3 pi, this would be 3 pi, right? Pi, or in this case, 3 pi. 2 pi's plus another pi. Okay. So how far is that? Well, I mean, a couple ways you could look at it, right? You could say this is just, we stopped pi over 3 short of a full 3 pi. So that's one way to look at it. 3 pi minus pi over 3, right? This theta would be 3 pi minus pi over 3, which is just 9 pi over 3 minus pi over 3, which is 8 pi over 3. Right? I mean, you could also do it this way where you think about, okay, how would I normally find this angle if it was just 0 to 2 pi? And then whatever that is, so that would be pi minus pi over 3. Get that, and then add the extra 2 pi that we know we're doing here. Okay, that would work. And now from secant theta having to equal 1, or I guess from cos theta having to equal 1 is how we've been looking at it, but really it's been secant from the beginning. So from cos theta having to equal 1, okay, well, like we said, that happens when our terminal arm looks like this, because that's where the x value is 0. So from 2 pi to 3 pi, where does that happen? We can't say 0. That's not between 2 pi and 3 pi. But it does happen at 2 pi, right? It would happen again at 4 pi if we did a full nother circle. So for that, it's just theta equals 2 pi. That's between 2 pi and 3 pi. So we're good. So theta could equal 2 pi. Theta could equal 8 pi over 3. Theta could equal 8 pi over 3, or theta equals 2 pi. Those are both solutions to this equation. Right, and again, if you really wanted, you could go back and check your work. Put in 2 pi and 2 pi. Put in 8 pi over 3 and 8 pi over 3 and check if they actually work. We actually should. I should mention here, we should definitely check for non-permissible values. Okay, so secant is 1 over cos. That's all I have here. That's the only place I could get non-permissible values. We're actually safe, though. Neither of our angles are going to make cos equal 0, right? In fact, we kind of knew that. Cos theta could equal -1/2. Cos theta could equal 1. Okay, but always worth a shot, because you can sometimes, especially in ones where you're simplifying, you can find extraneous solutions. Okay, in this case, we're safe. We're dividing by cos, yes, but our solutions are not anything that would make cos equal 0. So we're safe from extraneous solutions due to non-permissible values. And there we go. That's how we could solve that one. All right, so we did it algebraically. We showed our work. We represented our, our solution algebraically. We even did a couple diagrams so they could follow what we were doing. I feel pretty good about that solution, right? All right. Alrighty, so part B here of written response number 2, another trig-looking one. Points A, B, and C are on the terminal arms of angles drawn in standard position. Okay, so it's just saying this is the terminal arm of an angle, that's a terminal arm, that's a terminal arm. These angles are the solutions for theta to a single trigonometric equation. All right, so all that's saying is that, whatever theta this is for A, for example, it happens to be the solution to some trig equation, right? Same goes for B. Not whatever angle, we can see that that's just pi, right? That happens to be the solution to an equation, and same for C. But actually, all this is asking us to do is to state the general solution for this equation. So remember, general solution, why are we worried about a general solution? Well, because if angle A is a solution, you can probably see that that's, 3 pi over 4, because it's pi over 4 short of a full pi. If that's a solution, so is this, right? So is that plus 2 pi, because it's going to end up in the same spot. It's going to have the same ratios, and therefore, whatever equation this smaller theta solves, so does this one, because it has the same values. It has all the same ratios. It's essentially the same angle, but with a full other rotation involved, right? And that goes on and on. That even goes for negative angles. That would have the same ratio. So that would be negative 5 pi over 4, right? That would have the same value as whatever ratio we're taking of this one. And so we need to cover all our bases when we're stating the general solution. All possible values of theta that could be solutions. So we're just stating here, so we can basically just, state our answer, show a little bit of work, show a little bit of thinking. But really, this just boils down to how do we cover all of our bases? How do we include all angles that are coterminal to A, or the angle whose terminal arm passes through A? How do we include all angles that are coterminal to the angle whose terminal arm passes through B? And all angles that are coterminal to the angle whose terminal arm passes through C. Okay? So, let's just figure out, for A. For the angle that passes through, I'll call it theta A, just meaning that that's the angle whose terminal arm passes through A. Well, look. Here's the point A, it passes through there. It's telling us that it's got a reference angle here of pi over 4, right? They even gave us the reference angle, that was nice. So what is this angle? Well, again, this is 0, this is pi over 2, this is pi, this is 3 pi over 2, or we could think of 0 again as 2 pi if we go all the way around. So theta is just going to be, well, pi, but take away, right? There's pi. Pi, take away pi over 4. So pi minus pi over 4 will leave us with that orange part there, right? So pi minus pi over 4, you can think of it as, 4 pi over 4 minus pi over 4, if you like. Gives us an angle of 3 pi over 4. Kind of already mentioned that, didn't we? So that angle there, that's 3 pi over 4. Now we need to cover all angles that are coterminal to it. So in general, every time we do a full another rotation, whether it's in the positive direction or the negative direction, right? If from here I do a full another rotation, I get back to the same spot. If I do 2 full rotations, I get back to the same spot from there, right? Even if I go in the negative direction, so if I go clockwise here, if I do a full rotation, I'm back to the same spot. If I do 106 rotations, I'm back to the same spot. So I need to say that in general, theta could be 3 pi over 4 plus any number of full rotations. So plus 2 pi times n, where n just represents any integer, right? If n is 1, that's 1 full rotation. If n is 106, that's 106 full rotations. If n is negative 1, that's a negative full rotation in the opposite direction. But all of those are guaranteed to be coterminal to that angle, and therefore to also be solutions to whatever equation this is a solution to. Okay, so there we go. That's the general thing we can get from that. For theta b, do the same thing, but for theta b. Okay, well, theta b, we can kind of see is just pi, right? That angle, if its terminal arm goes through the point B, and the point B is just on the x-axis over here, we can kind of see that what angle is this? This is just pi. Theta equals pi. Okay, so how do I cover all my bases? Well, add full rotations, right? Careful, we don't want to add pi. That's not actually going to be a solution according to them, right? Coterminal to this, coterminal to this. So I just need to add pi. So in general, starting from pi, add full rotations to get coterminal angles. So pi plus 2 pi n, where n is an element of the integers, right? And again, all that's saying is starting from here, you could do another full rotation and you'd get back to another solution, a coterminal angle. You could do another negative rotation, so you could go clockwise, negative 2 pi, sorry, and that would give you a coterminal angle and therefore another solution. So there we go. Now for last one, theta c. Okay, we've got the terminal arm passing through the point C. They tell us that the reference angle here is pi over 4. So first, let's just figure out what that theta is. And then all we have to do to make it general is add 2 pi n, right? Add full rotations, integer number of rotations. So what is that angle? Well, we can see again, all the way around would be 2 pi, right? So we're not doing a full 2 pi, we're stopping pi over 4 short of that, right? Here's a full 2 pi. We need to take away pi over 4 to leave us with just the orange stuff. So that means this theta here, the one I've drawn, is going to be 2 pi minus pi over 4. If we want to get a common denominator to make things a little more clear here, 2 pi is just 8 pi over 4 minus pi over 4. So we can see that that angle there, that one angle that would be a solution is 7 pi over 4, right? How do I get all solutions, the general solution? Well, 7 pi over 4 plus multiples of 2 pi, right? Plus an integer number of full rotations, and that'll always give me a coterminal angle, and therefore always give me a solution. Okay, now not mandatory. You can actually look in the marking notes for this question, which again, those are included in this document. If you just keep scrolling, it talks about some of the things that can lose marks. It shows you student solutions and why they might not have gotten full marks and all that kind of stuff. Not mandatory, but we could here actually simplify this a bit, right? We could, because these two are just separated by pi. These two, A and C, are just separated by pi. So technically, we could combine them into one rule for the general solution. We could just say, starting from A, for example, just keep adding pi's. Just keep adding pi's and you'll always get to another solution, right? Add pi, add pi. So if we wanted, we could kind of combine those two into one rule, right? Again, not mandatory, but just writing them all out here, right? We can see that starting from 3 pi over 4, if we just add pi, right? Theta equals 3 pi over 4 plus multiples of pi. Those will always be solutions. Now, there's no way to include this one in one statement, right? It's not like we can always add the same number from here to get to here and then add the same angle to get to there. That's not going to work, right? So we can't include that one. That one doesn't, we can't combine it with anything. It doesn't have anything that it's separated from by pi or like pi over 2 or something, so not much we can do there. That one we're just going to have to leave as pi plus 2 pi n, where n is an integer. That's really all there was to that one. Mostly just figuring out what the angles were and then adding multiples of 2 pi. And optional at the end, we can simplify 2 of those rules into one nice rule. Okay, so moving on to written response number 3 here, part 1, part A. Okay. Students in a math class are creating and exchanging encoded messages with a partner. All right. So given that 630 different pairs of students are possible, algebraically determine, so again, using math and manipulation and showing our steps, right? Algebraically determine the number of students in the math class. Okay. So we can kind of see, hopefully, that this has something to do with perms or comms, right? we're trying to figure out if this many pairs of students are possible. We're trying to figure out how many students were there in the math class overall, right? Well, let's think about this, okay? Pairs. First, let's decide perms or coms. Pairs. Does it matter, right? If I have, Alice and Bob, is that a different pair than Bob and Alice, right? No, definitely not. That's still the same pair, right? So it seems like order doesn't matter here. Alice and Bob is not a different pair of people than Bob and Alice. That's still the same pair of people, okay? So we're definitely dealing with combinations, not permutations, okay? And if it's a pair, what does that mean? How many are we choosing, right? How many different ways can we choose? How many people? Well, 2, right? That's how you make a pair. You choose 2 people out of the group. If I was going to group you guys up to work on a question, I'd choose 2 of you and pair you up, okay? So pair just means we're choosing 2, okay? So what do we got so far? We've got that we're using combinations and we're choosing groups of 2. What are we actually looking for? The number of students in the math class, right? Well, that's how many options there are to choose from. From how many students, if we choose groups of 2, right? How many students must we be choosing from if we find that there are 630 different possible pairs? Okay, so if we think about that, that just means n choose 2 must equal 630, right? N choose 2 must equal 630. So how do we solve for n here? Well, don't forget n choose r, right? There's an equation associated with that, an equation that actually makes a ton of sense because there are n factorial ways to arrange n objects. We don't care about the order of the ones that are not chosen. So that's n minus r. If we're choosing r out of n, then n minus r represents the ones that were not chosen. But then we also don't care about the ways those r things that are chosen are arranged for a combination because order doesn't matter. So we also divide by how many ways there are to actually arrange those r things, right? So we're choosing from n total, okay, n factorial ways to arrange those. Don't care about the order of the things that weren't chosen, but also don't actually care about the order of the things that were chosen. We just want to know how many different ways can we select 2 things. But we don't care about, Alice Bob versus Bob Alice. Those are considered the same outcome for us. So that's why we divide by the number of ways to arrange the 2 things we chose, right? Alice Bob, Bob Alice is not 2 outcomes, it's 1 outcome. So since there's 2 ways to arrange them, divide by those 2 ways because we don't care. They're the same thing for a combination. Okay, well, look at this, folks. We can set up an equation pretty well here. If n choose r equals this stuff, then n choose 2 equaling 630 tells me that means n choose r is just 630 here. N is n. We don't know what that is. We're trying to figure it out. But we know that r is 2. So n minus r factorial is n minus 2 factorial. And again, r is 2. So divide by 2 factorial as well. And this is an equation we can start solving. Now, we can't do much with it while there's these factorials, right? Especially since we don't know what n is. But whenever working with factorials, right, especially when they're dividing by each other, it's often we'll be able to cancel them out by kind of expanding it out, right? And then seeing if we can cancel. So remember, all the factorial is multiplying by every integer below it, one at a time. So 4 factorial just means, for example, 4 times 3 times 2 times 1, right? 3 factorial is 3 times 2 times 1. So n factorial in general, if we think about what that means, n factorial is just n times the next number below it, n minus 1, times the next number below it, n minus 2, right? Times the next number below it, n minus 3, and then, so on and so on and so on, okay? And every bigger factorial contains smaller factorials within it. So just to go back to my example, 4 factorial, yes, equals 4 times 3 times 2 times 1. But do we see how we could think of 4 factorial as 4 times 3 factorial? Because 3 times 2 times 1 is just 3 factorial, right? We could even think of 4 factorial as 4 times 3 times 2 factorial. That's just 2 factorial. And that fact often lets us cancel some stuff out. So I'm going to start expanding n factorial, keeping in mind that we're dividing by n minus 2 factorial. So 630 is just equal to n factorial, but let's start writing out the first couple parts of n factorial. It's n times n minus 1 times n minus 2. And I'm actually going to stop there because I'm keeping in mind that I'm dividing by n minus 2 factorial, right? So this is just, it's n times n minus 1 times n minus 2. And what comes after this is just n minus 2 factorial, right? Next it would be n minus 3, n minus 4. It's just n minus 2 factorial from then on out. Divided by n minus 2 factorial times 2 factorial. And why that's so handy is that, look, n minus 2 factorial, n minus 2 factorial cancel out, and we're left with 630 equals n times n minus 1 over 2 factorial. And 2 factorial is just 2 times 1, or 2. So 630 equals n times n minus 1 over 2. All right. So if I multiply both sides by 2, I get that 1,260 equals n times n minus 1. Okay. Now, at this point, again, we could kind of state some stuff. We could write a quick sentence and say, so we're looking for 2 consecutive numbers that multiply to 1260, and the larger of those 2 is our n, right? Because we can see this is just a number times the number 1 below it. So we could explain that, explain our logic, and then try some numbers, right? Maybe 30 times 31, 31 times 32. Honestly here, though, we can also just do this as a quadratic and solve it completely algebraically. Since they did say solve it algebraically, I would lean towards doing it that way. It's not like it's much harder. In fact, it might even be equal or even easier in some cases to just solve this as a quadratic now, right? If there's an n minus 2 here, then it gets harder because we have to solve a cubic. But here it's just a quadratic, right? We're just back in Math 20 now at this point. Because what we're saying is that 1,260 equals, well, n times n is n squared, and n times negative 1 is negative n. So 1,260 equals n squared minus n. See what I mean? We're back in Math 20. We've got a quadratic. If we bring everything to one side, right, we'll have stuff equals 0. So I'm just going to subtract 1260 from both sides. N squared minus n minus 1260 equals 0. And hey, right, if I can write this as 2 factors multiplied together, then it's pretty quick and easy to figure out what n has to be to make it equal 0, because we just have to make either of the factors equal 0. So maybe not the easiest product sum in the world here, but at least it is a product sum. We don't have to do decomposition because our a value here is 1. So we really can just ask ourselves what 2 numbers multiply to negative 1,260 and add to negative 1. All right, now I'll admit that's not super easy to think about. Multiplies to 1260. I don't know the factors of 1260 off the top of my head, but we can kind of have a starting point to think about because we know they have to add to negative 1, right? Meaning that 1 is positive, 1 is negative, and they're separated by 1, right? So we could try some things out, right? It might take a little bit of trial and error, but, you know, we're aiming for about 1,200. So we're trying to get, 30-ish times 40-ish. Probably the answer lies between 30 and 40, right? Because 30 times 40 would be 1,200. So try a couple out, a little bit of trial and error. But what you end up landing on is that if we do negative 36 times positive 35, we get 1,260. And if we do negative 36 plus 35, we get negative 1. So those are our 2 numbers. So we can rewrite this as n minus 36 times n plus 35 needs to equal 0. And again, this is why we solve by factoring. It makes it super easy to see, right? this thing times that thing equals 0. Well, the only way to multiply two numbers and get an answer of 0 is if either of your numbers were 0. So now we can find the solutions, the things that make this equation true pretty quickly, because it will be true if n minus 36 equals 0, so if n equals 36, and it will be true if n plus 35 equals 0, or in other words, if n equals negative 35, just subtracting 35 from both sides. So two possible solutions for n. Except, don't forget what n represents here, right? Do not put two boxes around these and say they're both solutions without taking a second to consider what n represents. N represented the number of students we had to choose from, right? So, can we have 36 students to choose from? Absolutely. That makes sense. That's a solution, right? Can we have negative 35 students to choose from? No, right? That doesn't make sense. We can never have negative options to choose from, certainly not negative students. So keep in mind, written response on a diploma, I would probably not just do this, right? Show the marker why you're doing what you're doing. Give some reason as to why that's not a solution. Again, doesn't need to be like a full paragraph or sentence or anything, but just something like, can't have negative students. Can't have negative number of students, right? And so say this is an extraneous solution. We didn't do anything wrong in finding it, but we have to reject it for the reason that it just, in the real world context of this problem, it doesn't make any sense, right? So there are 36 students in the class. There we go. And again, I encourage you, if you want to go look at in the later pages in this document, they'll show you student solutions to this. They'll show you the marking guide, so you can kind of see, where did students lose marks, right? How do I not do that? What do I look out for? That kind of thing. Okay, and the final question on this diploma, part B of written response number 3. We did it. We're at the end. So a student is asked to encode the word factor by replacing each letter of the word with a different math symbol. There are 10 math symbols available. The student creates a key, a list of his letter symbol replacements, and gives it to his partner to use to decode the word. Now, in very important terminology here, okay? Explain. Explain does not mean just calculate, right? Explain means show what you're doing. So if you look at the official Alberta education definition, which I just seamlessly paused the video and went and got. I'm sure you didn't even notice. Just kidding, you definitely noticed. But I got the official definitions of what all these terms mean, right? What do they mean when they say explain? Well, look at this. Make clear what is not immediately obvious or entirely known, right? Give the cause of the reason for. Make known in detail. So that doesn't mean just throw some numbers on the page, right? For example, I'll kind of spoil this one for you. Here's what our solution ends up being, right? Here's what the actual math ends up being. 10 times 9 times 8 times 7 times 6 times 5. Or at least that's one way to approach it, okay? And that equals 151,200. Guess how many marks you would get for that? At best, 1 mark. Because think about it, right? Have you, by doing that, by writing that out, have you made clear what was not immediately obvious? Imagine if I gave you that, right? Imagine if I, as your teacher, said, how do you solve this question? Here you go, right? And I didn't explain it any more than that. Why are we doing that? Why does that make sense, right? You would say, you would definitely not turn to your classmates and say, wow, he really made clear what was not immediately obvious, right? That's clear now. No, definitely not, right? Now, again, you don't need to go back to grade 4 math and explain every single concept to them, but from a math 30 level, right? Show them that you understand why you're doing what you're doing, right? Make clear what is not immediately obvious. I don't know that it's immediately obvious that we need to do 10 times 9 times 8 times 7 times 6 times 5 times 4. Sorry, stop at 5. Okay, right? I don't know that that's immediately obvious. So it doesn't take much. You can go look, like I said, you can go look at the student sample solutions. I'll just show you one really quick here, right? You can go take a look at these. Oh boy, maybe this was a mistake. There we go, right? And you can look and you can see, when did students get full marks? When did they not quite get full marks, right? This student lost a half mark because it includes a partial explanation, right? So things like maybe they didn't explain why order doesn't matter. I think that's probably what their problem was here. Sorry, why order does matter, right? They did their best. They explained, right? They said there's 6 letters in the word factor, and for each letter there's 10 math symbols. To get the number of keys, I will start with 10 choices multiplied by 1 less each time, because 1 math syllable cannot be 2 letters, right? That's great. Looks like probably what they're missing, though, is why are they using permutations, right? Why does order matter here, right? This student also looks like they lost 0.5. It doesn't explicitly address that this fact that symbols cannot be repeated, right? So that's what they're missing there, right? They didn't mention that the symbols can't be repeated, okay? So fully explaining why they're doing what they're doing, right? Why 10 times 9 times 8 times 7 times 6 times 5 times 4, okay? Those kinds of things. So just reminding you that those are there. You can kind of look through. This person got 2 marks, okay? Their explanation, they've got quite a bit of explanation there. But like, look what they said, right? 10 math symbols to choose from. 6 letters in the word factor. So 6 symbols need to be chosen, right? We're choosing 6 symbols from 10. And the order we choose them doesn't matter. But then again, later they say after choosing the letters, I need to arrange them to each represent a letter in the word factor. Because each letter is unique, the order I arrange the symbols now matters, right? I will arrange the 6 symbols so each one matches a unique letter, okay? So again, okay, they're taking a different approach there, but that's the idea, right? We want to explain. We want to make it clear why we're doing what we're doing when explaining. So if I go back to that question now, just want to take a quick detour to look at those and remind you that they're there in a good resource, okay? Explain how you would determine the number of different keys that can be created for the word factor, and determine the number of possible keys using your strategy. So a student, we're encoding the word factor by replacing each letter of the word with a different math symbol. There are 10 math symbols available. The student creates a key, a list of his letter symbol replacements, and gives it to his partner to decode the word. So let's just start. I mean, for me, I would explain first why I'm about to use permutations or combinations, right? I'd say that the order that they're selected in does matter. The order I arrange them, I should say, does matter, right? Order does matter as a different arrangement of symbols would create a different code, right? Would create a different code. So must use, permutations. Okay. It also, we can't have symbols repeating here, right? Because factor, every letter is unique, right? Every letter, one thing we could add here, every letter in factor is unique. So no symbol will be used more than once, right? If I make F some symbol, I can't use that symbol again for A, C, T, O, or R because it already represents F. So no symbol will be used more than once, right? Therefore, when we, select, when we assign one symbol to a letter, that's not what I meant to write, our remaining options for symbols is reduced by 1. That's not a great sentence in terms of English, but what's happening, right? If I choose a symbol for F, I can't choose the same symbol for A. So I have one less symbol to choose from for A, right? And then I have 2 less to choose from for C because I've already assigned one to A and one to F. So let's now talk about, in our explanation, explain why we're about to do the math we're about to do, okay? There are 10 symbols to choose from. And 6 letters in the word factor. Okay, so by the fundamental counting principle, right, where our order matters here, okay, there are, again, no repeats. So there are 10 options for F, 9 options for A, okay. We could just say by the fundamental counting principle, right, we need to calculate 1, 2, 3, 4, 5, 6, right? We have 10 options here, 9 options here, 8 options here, 7 here, 6 here, and 5 here. Okay, so 10 times 9 times 8 times 7 times 6 times 5 gives me 151,200, right? And we could even annotate this a little bit. We could say, right, 10 options for F. And then no repeats. So 9 remaining options for A. Okay, and we stop here because we're only encoding 6 letters, the 6 letters in the word factor, right? Stop here, only 6 letters to encode, right? We have explained what was not immediately obvious here, right? So the key points, if you look through the student solutions, the things you'll see that students lose marks for, it's things like this. It's just taking for granted that they're going to understand order matters, right? Again, you don't need to explain like grade 4 math to them, but explain math 30 math to them, right? That's what they want to see. Can you explain math 30, right? So think of, did I learn this in math 30? Then I should probably explain it, okay? We learned in math 30 that if order matters, we kind of have to treat it a bit differently, right? And why? A different arrangement of symbols would create a different code. So we can use permutations here, right? Again, especially if we were going to pull out this formula, which it's totally possible to, we could actually use NPR and use 10P6, right? All of this explanation stuff here, if I explain that and then I use this formula, that would probably get full marks because I'm showing why I'm going to use 10P6, okay? Things like the things students lose marks for, right? Things like not explaining why does it go from 10 to 9 to 8 to 7 to 6, right? Ask yourself, would you have known this before you took Math 30? If not, you should probably explain that, right? That's what they want to see. They want to see that you can demonstrate the learning outcomes for Math 30. So if it's something you learned in Math 30, you should probably explain it. You don't need to explain why, like, this equals 151,200. They know you know how to multiply, right? So stuff like this. Every letter in factor is unique. No symbol will be used more than once. So when we assign one symbol to a letter, it's gone, right? We can't reuse it, okay? And then why do you have 6 blanks here, right? Would you have known that before you took Math 30, right? Maybe, but Again, would everyone before they took Math 30? Probably not. So explain it, right? There's 10 symbols to choose from. Now we've explained why we put a 10 there. And there are 6 letters in the word factor. Now we've explained why we have 6 blanks here, right? And then by the fundamental counting principle, right, we're kind of just referencing what math is backing us up here. We need to perform this calculation. Okay? So that's one approach to this one. Explain what you're doing. Make obvious what was not immediately obvious. Show your work, explain what's going on. So I do encourage you to take a look for any of the written responses at the sample student solutions. They're down. If you scroll through more of this document, you can see them. But it's an interesting thing to see, right? What kinds of things did students lose marks for? Helps you understand, oh, okay, so I got to be careful not to do that. Or that's a mistake I sometimes make, so I'll have to be on my toes. But there we go. That is the diploma.